Good morning, everyone. Welcome to the day two of the Physics Frontiers 2024. So after yesterday's interactive sessions and insightful presentations, so we look forward to fruitful discussions today also. So today we have amongst us my mentor, Dr. Rupjyoti Gogoi, Tezpur University. So I'd request our convener sir to kindly introduce her to the audience. Convener sir, over to you.
Thank you, Dr. Thapa. So I welcome Dr. Rupjyoti Gogoi from Tezpur University as our plenary speaker of second day of this national conference. So I just want to introduce Dr. Gogoi, madam. Dr. Rupjyoti Gogoi obtained her PhD degree from Guwahati University in physics. Her research interest is in astronomy, astrophysics, and particularly observational astronomy in the infrared, ultraviolet, and X-ray range of electromagnetic spectrum. She has been a faculty member at the Department of Physics at Tezpur University since 2011. She is a visiting associate of IUCAC, Pune since 2013. She is the member of Executive Council of Astronomical Society of India for the session 2022-2025. She has published many research articles and conference proceedings in many prestigious journals. So, on behalf of the organizing committee, I welcome you, ma'am.
Thank you so much. Am I audible?
Yes, madam.
Okay, so can I start sharing my screen?
Yes, ma'am.
Okay. Is my screen visible to everyone?
Yes, ma'am, it's visible.
Okay, and also it's full screen, right?
No, ma'am, it's not full screen as of now. I think you need to share the entire screen, ma'am. Just now.
Okay, that's the
Share
problem.
share the entire screen.
Yeah. Okay, I'm redoing it. It's not happening.
Is there an issue with the connection or something?
Should not be. Okay, I am just trying to share the PDF file. I hope that will work.
Okay. Okay,
is it okay now?
Yes, ma'am.
Okay.
That's fine.
So, is there some cut in the bottom?
Yes, a bit cut is there actually. There's a bit. I don't know. Yes, now it's fine.
Is it fine now?
Yes, ma'am. Now it is fine.
Okay. So, can I proceed like this?
Yes, please, ma'am.
Okay.
Yes. Please.
Okay.
Thank you.
Okay. So, thank you for the nice introduction. So I'm going to speak about the origin of diffuse far ultraviolet background radiation in galaxies. First of all, I would like to thank the organizers of Physics Frontiers 2024 for inviting me to deliver this talk. I'm really very happy to be a part of this conference. And also I should say that it's a very positive sign that a lot of researchers from across the globe have contributed their research work to present in this conference, Physics Frontiers 2024. I must congratulate the organizers for organizing the event in such a successful way. So the work about which I am going to present here, it's a collaborative work. You can see the list of collaborators here. Dr. P. Shalima is from Manipal Center for Natural Sciences under Manipal Academy of Higher Education. Then Dr. Gautam is from North Guwahati College. Ulok is my PhD student. He submitted his thesis very recently and he is awaiting his FIPA. He is also teaching in Cotton University. Barina was my master's dissertation student. He has contributed to some portion of this work. Currently, he is in MCNS Mahe. Well, so in the title, as you can see this word diffuse and background. So I'm going to talk about the diffuse background sky. Now the meaning of diffuse background sky is that I'm not going to speak about the stars in the sky. I'm going to speak about the sky minus the stars. Means from our sky, we just throw away all the stars. Then what remains is the background. And I'm talking about that background. So there is no star in the sky. That's why it is diffuse. And when I say the sky background, when we observe the sky background with the help of ultraviolet detector, then we observe a very faint glow that we call as the diffuse galactic light or DGL. It's not that this glow is observed only in the ultraviolet range. The same glow is observed in other wavelengths too, like in infrared or microwave. But in this talk, we will restrict ourselves only to the ultraviolet glow of the sky where all the stars are masked. Now the image which you see here, this is called as the diffuse FUV sky map. It was created by Jayant Modi from IIA Bangalore in 2014. He used data from Galaxy Evolution Explorer, shortly called as Galaxy mission, to create this diffuse sky map. So it is very widely appreciated and used by researchers from different parts of the globe. Now, in the central portion of this image, you see this black color because this portion was not observed by the spacecraft. Because of the obvious reason that in the galactic plane, all the UV emitting stars are there, and that's why the bright starlight may damage the detectors which are on board the spacecraft. That's why this portion was not observed by the Galaxy mission, and this portion which you see in white color, it actually corresponds to the darker patches of the galaxy which correspond to the dust particles which are there in the galaxy. And in both the hemispheres, you see a glow in orange color or in slight reddish color. This is the diffuse ultraviolet sky background about which I am talking. So what you can see here is that this diffuse ultraviolet sky background is quite uniform in both the hemispheres. That's why this is sometimes called as uniformity puzzle also. So we are talking about the origin of this diffuse ultraviolet sky background. What we will do is that we will try to understand one component contributing towards this diffuse far ultraviolet sky, and that component we call as the dust scattered light. So dust scattered light means the bright UV emitting stars in the galaxy, they are emitting UV radiation which is being scattered by the dust particles which are there in the galaxy, and therefore we see this faint glow. And this is one primary contributor towards the diffuse far ultraviolet sky. Similar mapping is also observed in near ultraviolet. Now we will just concentrate on the first component, that is the scattered light, but it doesn't really mean that there are no other component contributing towards the diffuse FUV sky. There are other components as well, some other components which are having galactic origin, and some other components which are originated outside the galaxy, which we call as extragalactic background light. But in our discussion, we will just talk about the first one, the dust scattered light. In our research group, what we do is that we try to see to what extent the dust scattered light can explain the diffuse far ultraviolet background radiation. Now, as I have mentioned about these dust particles in my earlier slides, I would like to give a formal introduction of the dust particles in a galaxy. Now, when we look into the night sky, we see a lot of stars, of course. Then when we think what might be there in between two stars, then the first impression is that the space is empty, but actually the space is not empty. Rather, it's filled with a medium, which we call as the interstellar medium, shortly ISM. Now, ISM has different components like interstellar gas, dust, cosmic rays, electromagnetic radiation, magnetic field, gravitational field, dark matter, and there might be some other components as well. Now, in the ISM, by mass, 99% is gas. When I say gas, gas may be in ionic, atomic, or molecular form. Predominantly, it is hydrogen. Then a significant amount of helium is also there, and a very little amount of other heavier elements, which we call as metals in astronomy. Then 1% is dust. Dust may be sand-like or it may be soot-like, and it is, I can say that dust particles are tiny pieces of solid particles composed mainly of carbon, silicon, and oxygen. Now, how much portion of a galaxy is dust? To understand that, I would like to refer to a typical Milky Way type of galaxy. We know that we are dwellers of a spiral galaxy called Milky Way. Now, in a typical Milky Way type of galaxy, 1/6 of the total galaxy mass is baryonic, means whatever we can see in the form of star, planet, or everything around us. In that 1/6, just 1/6 is the ISM, and in the ISM, 1% or even less than 1% is dust. So you can imagine that dust is a very minuscule portion of a galaxy. Yet it is very powerful. How powerful it is, we can understand from this single figure here. So here along the y-axis you see the flux, and along the x-axis you see the wavelength. This portion of the curve is because of the light which is emitted by the stars in the galaxy. So this is because of the stellar emission we are getting this part, and this portion is because of the emission by the dust particles which are there in the galaxy. So how the dust particles can emit light? Because they are heated by the ultraviolet light of the O and B type stars, and therefore they produce a thermal emission, and that emission we can observe only by using infrared eyes. That's why to study this portion we need to have infrared detectors. So you see that more than 50% information about a particular galaxy is hidden behind the thick layers of dust which is there in the galaxy. So it's such a minuscule portion of a galaxy, yet it is very powerful. And therefore, to have a total picture of a galaxy, we just cannot ignore this minuscule fraction of that galaxy. To have or to study intrinsic galaxy properties, we need to account for the effects of dust which is there in that particular galaxy. So here I am showing you some beautiful dust patterns. Here you can see some dust lands, dust ring, and this is just to convince the audience that all galaxies are dusty. So believe me or not, dust is there in all the galaxies. What type of dust is there and how much dust is there, that will obviously vary from galaxy to galaxy, and also within a particular galaxy the nature and characteristics of dust will vary from location to location depending on the environment. Well, so talking about the composition of dust, they are primarily composed of elements that are abundant in the universe and in the interstellar matter. So the candidate constituents I can say as carbon, oxygen, magnesium, silicon, sulfur, iron, etc. 28% of dust mass is in carbon. When I say carbon, it may be in the form of solid carbon like graphite or diamond, or it may be in the form of hydrocarbon like polycyclic aromatic hydrocarbons. Then 72% in other compounds like silicates or oxides. And this is the typical structure of a dust grain. It has a central core surrounded by an icy mantle, and then it has a surface, the surface which can act as a chemical factory because simple organic molecules or compounds can form on the surface of the dust grain. Just like here, you can see that two hydrogen atoms are combined to form the hydrogen molecule. So dust facilitates the formation of molecules also. Now it is very important to understand the formation, transformation and destruction of dust inside galaxies. The life cycle of cosmic dust is very closely related to life cycle of stars. We know that stars take birth in star forming nebula. When I say star forming nebula, we understand that we refer to thick regions of gas and dust, and beneath these dusty layers of gas and dust, new stars or baby stars are taking birth. Once a star is born, it will spend its life for some time as a main sequence star, and towards the end of its life it will either become a red giant or a red supergiant depending on its mass. A sun-like star will become a red giant. If it becomes a red giant, then it will shade its outer layers into the interstellar medium in the form of a planetary nebula. Thus, the stellar material which were created inside the star during its lifetime, it will be released to the surrounding in the form of stellar wind. A spectacular death in the form of supernova explodes as a supernova, then it will inject the stellar materials into the surrounding space. Thus, a dying star will enrich the interstellar medium with raw materials for the next generation of stars to form. And the process continues. The materials which are being released by dying stars, they will again accumulate to form a star forming nebula, and the whole cycle will be repeated. Well, so in this slide, I will try to explain the effects of dust, which is important to understand the work which I am going to present here. So here we are having some astronomical objects, suppose some stars, a few stars we are considering. Then this is a cloud. I can say this is an interstellar cloud having some dust grains here. Now, when the electromagnetic radiation emitted by the stars pass through this cloud, what will happen? The dust grains which are there in the cloud will scatter the blue light. Why? Because the wavelength of blue light is comparable to the size of the dust grains. Therefore, blue light is scattered very efficiently, and the red portion will manage to pass through this cloud. Therefore, when we observe these stars from the other side, then these stars will appear redder. As you can see, these red dots, they are actually stars, which are hidden inside a dust layer. So this is called as reddening. And when we observe this interstellar cloud from this side, then we will see that the cloud itself is glowing as a very beautiful blue reflection nebula. Okay, so both the sides, they have a story to tell us. Now, scattering and absorption of starlight together is called as extinction. Extinction is a very important tool in astronomy. Whatever we study in astronomy, we have to correct for the extinction, we have to correct for the reddening. That's why the study of interstellar dust is actually very important. We cannot just ignore the dust which is there in the galaxy. We have to understand it very clearly. Now, reddening depends on the line of sight, because if there is more material along the line of sight, then there will be more reddening. Similarly, interstellar extinction will also depend on the line of sight. Every line of sight will have its own extinction law, and extinction also varies with the wavelength. You can see here how extinction varies with the wavelength. And also we see a prominent pump over here, which is called as the 2175 angstrom pump. The presence of this pump is attributed to the presence of polycyclic aromatic hydrocarbons in the interstellar medium. Now, here I'm showing you the comparison of the extinction curve for three galaxies. One is for our own galaxy, Milky Way, then for our neighboring Magellanic Clouds, LMC and SMC. So here also you see that the extinction curve is different for the three galaxies. So every galaxy will have its own extinction law, and even inside the same galaxy, extinction will depend on the location, depending on the environment. Now here also we see this pump, 2175 angstrom pump. It is attributed to the presence of polycyclic aromatic hydrocarbons. These are essentially collection of benzene rings. Two or more aromatic benzene rings are fused together, which we call as polycyclic aromatic hydrocarbons. And sometimes these PAHs form clusters, which we call as very small grain. Well, so now I will try to explain the dust scattering model which we are using. I will try to explain in very simple words. Here in the blue color, we see a cloud. This is an interstellar cloud where we have dust grains. So these are the dust grains. And we have a star over here. The star is of course emitting some light. In the dust scattering model, we consider bright UV stars. That's why we consider O and B type stars only. Now the star will emit a photon. Suppose the photon will interact with a dust grain, which is here. And as a result of the interaction, the photon's effective weight will be reduced by a factor, which we call as albedo. And therefore, the albedo may vary in between 0 and 1. And after this interaction, the photon will take a new direction. This scattering angle, it will depend on the Haney-Greenstein scattering phase function. I mean, that is our assumption that the photon will take a new direction, which we are calculating in our model by using Haney-Greenstein scattering phase function. Now, you can see that the process will continue. There will be a lot of stars here. There will be a lot of dust grains also. And therefore, the process is not that easy. It's little clumsy, but I mean, the modeling is not that difficult because we are considering only the ONB type stars. And I mean, when we count how many ONB type stars are there, then it's like a few thousand stars only. Okay, so this model we can use in two ways. One, single scattering model, where we restrict the number of scattering suffered by a particular photon into one. Means each photon is allowed to suffer scattering only once. That we call a single scattering model. And if we allow the scattering to continue until it either leaves the area under consideration or its intensity drops to a negligible value, then it is called as multiple scattering model. So whenever we have optically thin medium, then we can go for single scattering model, and whenever we have optically thick medium, then we prefer to go for multiple scattering model. And very often what we do is that we do a comparison of the results between the two. Now, in the Henny-Greenstein phase function, you see another factor Z. This is called as the phase function asymmetry factor. This Z actually tells us whether the scattering is isotropic back or forward. Okay. So, this is the sample, imaginary sample. Our sample is like this only. We have a few stars, ONB type stars, and then we have some dust grains. So, what we need in our model is that we need information about the stars. Sorry. So, this information we extract from some star catalog, and then we need information about stellar spectra, which is also easily available. Then we need to assume something about the dust distribution, and then the dust optical constant. We believe in Henny-Greenstein phase function as shown in here, and then we model the scattered intensity. What we do is that we select stars randomly, we let scattering continue depending on whether we are going for a single scattering model or multiple scattering model. We vary albedo and phase function asymmetry factor, and we estimate the output intensity so that it matches with the observed intensity. And the observed intensity we take from different observations like Galax, Fuse, Voyager, Astrosat, etc. So this is basically a parameterization. We find the best fit parameters. Well, so for the very first time in our group, we used the dust scattering model for Orion Nebula, which is a star-forming nebula in our own galaxy Milky Way. Now, here this red cross, it denotes the Orion center, around which you see these stars as green spheres. Then you see these gray spheres here. These are the dust locations. So we considered a 10-degree radius from the Orion center, and then we modeled the scattered intensity. And for our model, the parameters were found to be 0.7, albedo was found as 0.7, and the phase function asymmetry factor was found as 0.6. And these are same irrespective of location of the dust particles. And in this work, we also estimated that the FUV light scattering is predominantly from the foreground dust that provides for at least 84% of the scattered radiation. So after applying the dust scattering model to Orion, we tried to use the same model to some other galaxies like LMC and SMC, but those results I am not showing here. But very recently, we applied the model to an external galaxy called as Homburg 2. I would like to show some results from Homburg 2. So, This is the multi-band image of Homburg 2. This is a dwarf irregular galaxy, just like the Large Magellanic Cloud and the Small Magellanic Cloud. Now, when we discuss the interstellar medium of a dwarf irregular galaxy, then it is quite different than a spiral galaxy. In a spiral galaxy, ISM is structured. It has a definite structure. But in case of dwarf irregular galaxies, it is quite patchy. But why we study dwarf irregular galaxies? Because this type of galaxies were there during the early universe. And that's why when we study dwarf irregular galaxies, we get information about the structure and evolution of galaxies in the universe. So that is one agenda of studying the interstellar medium of dwarf irregular galaxies. So here I am showing you the multi-band image of Homburg 2. Here this blue colored portion, this is the FUV light. For FUV, we use data from our own, our multi-wavelength satellite AstroSat. As you know that is India's first dedicated multi-wavelength satellite AstroSat. So using ultraviolet imaging telescope, shortly UVIT data from AstroSat, we obtained this FUV in blue color here. Then for the infrared information, we use data from Spitzer Space Telescope, which is NASA's infrared mission. So the green color over here, it shows the IR emission, and this contour, it represents the integrated H1 map taken from things. So for Homburg 2, we created the FUV diffuse map like this. This work is going to appear in PASP soon. And for this dwarf irregular galaxy, Homburg 2, we found the best fit albedo and asymmetry values as 0.2 and 0.5. Details about this Homburg 2 will be discussed by my collaborator, Vivek, whose talk is scheduled this afternoon, I guess. He will also talk about the correlation of UV and IR, because this kind of dust scattering model is always complemented by a study of correlation between UV and IR, because that gives us some idea about what kind of dust population is there in the galaxy. Well, so I would like to end with some concluding remarks. So as I have mentioned that we are trying to apply this dust scattering model to different regions of different galaxies. We consider locations near star forming region, and what we have realized is that we need multiple models with different dust populations. We have seen that a general set of assumptions for size distribution and composition of dust grains is not applicable for all locations of the same galaxy. Even for a given galaxy, depending on the environment of a location, we need to change the size distribution and dust population. So in future, we plan to propose multiple models, and that will be more insightful. Then also we plan to do combined UV-IR modeling of scattered and thermal emission from dust grains. That will be helpful to have correct information about the dust grains which are there in that particular location. Also, as we know that the scattered radiation is mostly polarized, that's why implementation of polarization in dust radiative transfer model is another agenda which we keep for our future work. So with this, I would like to conclude. And before concluding, I would like to introduce my students. These are my past and present PhD students. Dr. Gautam and Ulok, they are involved in this work. Gautam did the Orion work, and Ulok did the Homburg 2 work, and both of them are involved in the modeling of NMC and SMC. Pranjupriya is in APC Paris doing her second postdoc. Rukia is in South Africa doing her first postdoc. Ansuman has recently defended his PhD thesis, and he is recently joining IUCAA Pune for his postdoctoral research. And these are my ongoing students, Ritik, Swagatin, Snigdha. And I would also like to advertise that Department of Physics, Tezpur University is involved in promoting astronomy research and education through workshops, schools, meetings. Very frequently, we used to organize workshops, meetings, and we are organizing another one in October from 23rd to 25th. We are organizing Northeast Meet of Astronomers. We will circulate a flyer very soon. So I hope to get a lot of response from the astronomy community of Northeast. And finally, I would like to thank the audience with a quotation from Carl Sagan. So thank you very much. Thank you.
Thank you, madam, for your nice and informative speech. So it's now open for discussion and interactions. Audience may ask any queries or questions.
If I have a question actually.
Yes, please.
Yeah. Yes. So you mentioned about you talked about so it might be a naive question. So how do will cosmic rays play any role in the distribution of interstellar dust or something like that? Will it play any such role? Cosmic rays?
Cosmic rays in the distribution of dust.
Yes, actually. Because you mentioned about
yeah.
if there are if a supernova if exposed at some distance and if there will be some particle high energy particles moving towards, so it will interact with the ISM, right, nearby ISM somewhere. So
Correct,
how will it affect it, or how will will it affect the distribution or some of the properties of the dust, something like that?
You mean that supernova or the cosmic rays?
Any the high energy particles, like from maybe cosmic rays, or it might be.
Yeah. So, like, of course, in the distribution of radiation, it will play a role. I mean, it should play a role. I am also not very sure, but in the distribution of particles, I'm not very sure, because like dust grains and cosmic rays, like if there are no other facilitators nearby, I mean other agents are not there, if there is only dust population, I mean only dust grain and only cosmic rays, then I don't think cosmic rays can play a role in the distribution of particles. But of course, in the distribution of emission, I mean, whatever radiation we see, there it can play some role.
Okay. And okay, that might happen, right? And one more thing, like about the will there be any effect, like the magnetic field of will there be any influence of magnetic field on the dust or something?
Yeah, of course, yeah. Magnetic field, like, see, the thing is that, I mean, the situation is not as simple, right? Because when we study about some region which is far away from us, we do not have any clue. So, like, we do some very naive assumptions. We are also not very sure about the assumptions, but of course this magnetic field will play some role. I mean, these dust grains, they are like sometimes they are ionized, they will be magnetized, so of course the magnetic field will play some role. So like if we want to have a very robust modeling, then we need to include everything. Actually, we need to take into account the magnetic field also. That will actually give a very robust picture, but that is not very easy because of lack of information.
I can understand.
But actually we are trying to include as many input parameters as we can. Like in future, I don't know how much we will be successful.
Okay.
Yeah.
Okay. Thank you so much. Thank you so much, Freddy.
So any other questions from the audience?
You can also like contact me over email. My my mail IDs are there in the department web page. So you can just write some email. If you do not want to ask now, then that's fine.
Hi, I have a question. Can you hear me?
Yes, Sargnik strategy, right?
Yeah.
Okay.
So how accurate is the single scattering model?
Yeah, that's a good question. So, as I said that if we have optically thin medium, I mean the dust number density is less, then we can use single scattering model. Otherwise, we have to go for multiple scattering model. But the region about which I was talking, Orion and this Homburg too, there we saw that single and multiple scattering, they actually do not differ much. We can easily go for single scattering model. And another thing I would like to say here is that, of course, this whatever modeling we are doing, we are trying to account for the dust, I mean, contribution of the dust scattered light in the observed sky background in the ultraviolet, of course. But as I have mentioned in my second slide, there are other components. And in future, actually, we have to see the contributions from other components as well, which we have not done till now. Does it answer your question?
Yeah,
Sagnik?
thank you so much. Yeah,
Okay,
thank you.
thank you.
So if there are no further questions,
Okay.
Okay, I think the conveyor's
let us
voice
thank
got
our
cut. Okay, yeah. I
speaker.
think you're
So thanks a lot, madam, for your time and accepting
Thank
our
you.
invitation.
Thank you so much. Thank you.
Thank you, ma'am. Thank you, ma'am,
Thanks a
for
lot, madam.
joining, and
Thank
we
you.
hope to invite you to Bhawanipur Anchalik College sometime
Yeah,
in the
I'll
future.
love to visit your college. I'll
Surely,
wait for
ma'am.
your invitation. Yeah.
Surely, ma'am. Thank you so much, ma'am. Thank you so
Okay.
much for your
Thank
time,
you.
ma'am.
Thank you. Yeah.
Okay, let us move to the next session. So I request Dr. Vivek Baruah Thapa, Assistant Professor of Physics, Bhawanipur Anchalik College, to chair this session. Dr. Thapa, are you there?
Yes, I'm here. So, okay. Actually, there has been a change in plan, actually. So, Dr. Rupjyoti Gogoi was supposed to chair the session, but due to some last minute notice, he had to cancel it. And fortunately or unfortunately, I have to chair the session. So the sequence of the presentations will be in such that first Bhanu Prakash Pant will be presenting, and then the Kardarish Purba. I think she's here. Kardarish, are you there? I guess.
Yes, Vivek, I'm here.
Yeah. Hi, Kardarish. Again, Anil Kumar is here, I suppose, and then Gautam Saikia, yes, and followed by Kamal, Partha, Biplab Sarkar sir, Ashish, and Lisa. Okay, so Let me first invite Bhanu Prakash Pant from IIT Jodhpur to kindly present his talk. Yeah, Bhanu, please. You are not audible, Bhanu, I suppose. You are not audible. Is it? No, it's not. Just no, it's not working, Bhanu.
Can you hear me now?
Yes, now it's fine.
Now it's fine. Okay, good.
Yes.
So let me just share the screen first. Okay.
Yes, please. Yeah. Yes.
Yeah. Let me
Just
make it
go
full
to
screen.
the...
Good?
Yes.
Okay.
Please.
Yeah. So good morning, everyone. I'm Bhanu Prakash Pant from Indian Institute of Technology, Jodhpur. Today, I am going to talk about my work, which is constraining ALP parameters with invisible neutrino decay using the ice cube observations of NGC 1068. So basically, what I'm going to talk about is the dark matter candidate, which is ALP or axion-like particles, and how it can be, probed by the decay of the neutrino, which has been observed from this NGC 1068 NGC 1068 Seyfert galaxy. So this is just the outline of my presentation. First, I'm going to give a brief introduction. Then I'll talk about the axion-like particles and then current bounds on its mass and coupling constant. Then the aim and objectives of this work, the brief of the work done, and then finally I summarize my work. Okay, so when you were a child, you were studying that everything surrounds us are made up of matter, and then these matter are made up of molecules, and then these molecules are then made up of atoms, and inside these atoms there are atomic nucleus, and then there are electron clouds. Then when you study later, you find out that this atomic nucleus is again are made up of neutron and protons. And then these neutron and protons are also not the fundamental entities, but they are made up of more fundamental entities, which are called quarks. And we have different type of quarks like up, down, charm, strange, top, bottom. And these quarks are interacting via these bosons, which is called a gluon, which is kind of a quanta for the strong interaction. And then there are other particles which we call leptons, like electron, muon, tauon, and their neutrinos and antineutrinos. So this basically more or less, these fundamental particles more or less made up what we call now the standard model of particle physics. But through observations, what we found that this is not the complete story. What we see, the universe that we see made up of only 5% of this ordinary matter that are in the standard model. The rest 68% of the universe is made up of dark energy, and then the rest 27% of the universe is made up of dark matter. So the physicist basically introduced many imaginary friends in this dark matter case. In this dark matter case, and this is the zoo of these dark matter candidate or the imaginary friends that we have introduced so far. My work is based on this little this little guy sitting here, which is called axion-like particle, and this is right now my best friend with whom I'm just doing all this my work. Okay, so what are axion-like particles? So axion-like particles are basically these pseudoscalar bosons. Pseudoscalar means that under the parity transformation, they don't change. Their mass range is very enormous. Basically, they spans like 10 to the power minus 22 to 10 to the power minus 3 order of magnitude. That is, we don't know exactly the mass. it could lie anywhere between 10 to the power minus 22 to 10 to the power minus 3 electron volt. And these are other masses of the other dark matter candidates that lies in other ranges of the other ranges. They are heavy dark matters also, like WIMPs and sterile neutrinos and so on, like primordial black holes, etc. So what happens is that these axion-like particles, they show a remarkable property of converting into photons in the presence of external magnetic field. So you can see here the Feynman diagram, and axion-like particle interacts with the external magnetic field and then converts into a photon. This is the coupling constant, and this is the axionic field. So we can write a Lagrangian describing this process via this relation here. This is basically the coupling constant here, which is at the vertex, and this is the axionic field, and E and B are basically the magnetic field and the electric field. We tried various methods to search for these axion-like particles in the laboratory by reactor experiments or astrophysics. The main advantage of the astrophysics experiments is that we cannot replicate these extreme environments and the energies at which these astrophysical sources work. So that is basically allows a new window to search for these axion-like particles. Okay, so what should we expect since we are looking at the astrophysical source? So what should we expect in our data when we look at the source? So since I just mentioned that in the presence of magnetic field, these axions basically converts into photon. So what happens is that when an astrophysical source is very far away or very, very distant, and if it's emitting energy in the sub-PeV range, which is of the order of 10 to the power 15 electron volt, it interacts with the low energy background photons like extragalactic background light or cosmic microwave background, and then undergoes pair production. So basically what happens, any gamma rays that you see from the distant source will basically get exhausted due to this pair production method. But if these hypothetical axion-like particles exist, then they will convert into photon. Basically these photons, the reverse can, is also true. The photons can also convert into ALPs. So what happens is that some of the photons, or fraction of photons, converts into an ALP, and since these ALPs are dark matter candidates, they basically are weakly interacting, so they will not interact with photons or matter much. So they will just circumvent this absorption process, and then they again, reappear when they enter into the Milky Way. So due to the galactic magnetic field, these axions will then again convert into a photon, and then they reappear in our gamma ray observations. So this is what is the basic idea to probe these axion-like particles in astrophysical sources. We basically look for excess of gamma rays at the ranges of energies where there are chances of the absorption in a conventional method. Okay. So this is the whole idea. So what are the current astrophysical bounds? This you can see here, this picture, the various sources people have used to constrain the mass of the axion-like particles and the coupling constant. So for example, the Markarian 421 NGC 1275 supernova, which is the only supernova we have observed yet, and quasars and pulsars and so on. I would like to just focus on this one particular basically experiment, which is called the CERN Axion Solar Telescope, or CAST, which you can see here. This is a laboratory experiment which is designed to detect axions from the sun. I am audible, right?
Yes, you are.
Oh, okay, fine. I just want to make sure.
Yeah.
So this is just a laboratory experiment.
Bhanu, sorry to interrupt. Can you be quick a bit? You have like 4 or 5 minutes in your hand.
Oh, yeah, sure.
Yeah, sure. Okay.
So which is kind of a laboratory experiment which is designed to detect axions from the sun, and it has basically given a limit. So on the coupling and axion mass, which is this limit or shown by this shaded region. So any mass or coupling above this is excluded. So if we have to provide a new constraint, then it has to be below this cast limit. So our main objective is basically to look at this target window where there are more chances of constraining this mass and coupling constant. And how are we going to do this? We take few extragalactic sources at high redshift, and then we look at the very high energy gamma ray observations and look if there is any spectral modulation in their observations. So these are just magnetic field environments where the possible conversion can take place. It can take place in the jet region of the blazars. It can take place in the intergalactic medium. It can take place in the galactic region. So these three are the main or dominant regions where this convergence can take place. Since is a Seyfert active galaxy, so which basically means that we cannot see its jet, and also we cannot see the center massive black hole because it is obscured by the dust, as Professor Gogoi just mentioned in her talk. But we do observe neutrinos from this source by the IceCube Observatory in November 2022. And the energy range of the neutrinos were 1 TeV to 15 TeV. We also observed gamma rays in the band of 0.1 to 300 GeV by the Fermi-led satellite, but we didn't observe any gamma rays in the tera electron volt energy. So my work is basically based on the decay of these neutrinos that we observed and to probe these axion-like particles. So since neutrino comes in three flavors and there are corresponding three mass eigenstates of these neutrinos. So what I did is that I assumed that the heavier neutrino, they just decay into a lighter neutrino with the emission of these axion-like particles. If this happens, then the number of neutrinos changes by this relation when they propagate a length L effective, and the flux of this ALP neutrino that we should observe at the detector is given by this relation, and the probability of production of this ALP is given by this relation. So this is just sort of kind of an illustration. The neutrino comes in and they just decay into an axion-like particles here, and then these axion-like particles, this enters into this galactic magnetic field, and then they again converts into a photon and can be observed by the Fermi-led satellite. Some fraction of it will decay, some fraction of it will not decay, and they can be observed by the IceCube Neutrino Observatory. So this is the whole idea of my work. What I did is I used two benchmark values. I first assumed a neutrino flux at the source by this model, and then I assumed decay lifetime of these two neutrinos masses, nu2 and nu3. And I assumed that the new one, which is the lightest mass eigenstate, to be a massless. Then I just did a simple likelihood analysis. That is, I assumed that these ALP are sitting on top of this conventional flux. And I did a simple chi-square analysis with observed data. And then to put a constraint, I rejected all chi-square values which is above the 3 point, which basically goes above 3.84. Since there is only one degree of freedom, which is just the order of magnitude of this flux. So this is what I have obtained. This is the basically exclusion region I have obtained, and I can exclude masses of ALP less than 2 into 10 to the power minus 9 electron volt, and I can exclude the coupling constant above 1.37 into 10 to the power minus 11 GeV inverse. Corresponding to this coupling constant and mass, this is the gamma ray flux I have observed, which is shown in the dashed line of magenta dashed line. And these brown dot dash line are basically the conventional flux that one should observe from the in a conventional scenario without assuming any axion-like particles. So we can see that basically with this mass and coupling constant, we cannot see any excess or any spectral modulation basically in the data if the mass and ALP lies in this range. These are some sources of uncertainties that could affect this constraint. Like if we change the neutrino flux, then we find that this constraint changes by this small region here, which is already ruled out. We can change the galactic magnetic field model, and we can see that this changes only the mass range, but not the coupling constant range. We can choose a different neutrino lifetime, and we see that neutrino lifetime basically don't affect the constant that we have obtained in this work. This is basically the ELP flux, or the flux if we consider this particular neutrino flux to put the constant, which basically corresponds to this exclusion region. But it has already been ruled out by the cast experiment.
Bhanu? Yeah, sure.
Just one last minute. This is the final slide. Yeah. So
yeah, sure.
So since we have calculated the flux from a single NGC 1068 source, we can make a cumulative flux from all the sources which are like NGC 1068, and we find that this again lies very below as compared to the extragalactic background flux that we have obtained from the Fermi-Lat satellite. So basically the ELP induced flux, it cannot provide any access either in the diffuse gamma ray flux also. So to summarize, I have excluded this mass and coupling constant, and we find no significant effect in the gamma ray flux. Also in the diffuse gamma ray flux, the effect was very less significant or subdominant. So yeah, so that's all. Thank you very much for attention, and yeah, thank you.
Yeah, thanks, Manu. Thanks for the insightful talk. So the platform is open for questions. We can take a quick 2-3 questions from the audience. Yeah, you can unmute and directly speak. Okay, so Bhanu, I have a quick question.
Yeah.
Okay, so you mentioned about ALP. So what do you think about ALP candidates as a dense matter equation of state, like a part of being dense matter equation for in neutron stars, basically?
Yeah. So
how do you?
So what happens in neutron star? Okay, so it could happen so that the neutron, since it's very massive, basically neutron star, the density is basically very high. So it can capture the dark matter by multiple scattering. So at the center, basically, we can have accumulation of the dark matter. And if this dark matter is axion-like particles, what could happen that since it's the dark matter that will be accumulated at the center could be in the mass range of GeV. Okay, so that dark matter can decay again into photons. Okay, but then these photons can again then recombine, and due to pair production can produce fermions, E plus or E minus or mu plus or mu minus. So inside the neutron star, if this dark matter decays and then again produces E plus or E minus, then these are fermions basically you are introducing into the equation of state. So that may change some of the properties, or maybe the mass relation or the MR relation or something like that. But it should happen if it decays inside the neutron star. If it decays outside, then obviously it's not going to change anything.
Okay. Thanks for the nice.
So I have so if it decays inside the neutron star, so how can it be a dark matter candidate? I mean, it will not be the stable one?
Yeah. So
sorry, by the way,
that's why I said that dark matter candidate has to be in the GeV range, because we can have the dark matter could be anywhere. I mean, we can have
otherwise it cannot decay. I mean, if the mother particle is lighter than the daughter particle, then it cannot decay.
Yes. So if the dark matter mass is in the like nano electron volt, obviously it's not going to decay. But yeah, but the ALP, heavy ALP is could lie also in the heavier side. They can also be in the GeV range. What I did, what I showed was in the lighter ALPs, ultralight ALPs. But the ALPs could also lie in the higher mass range, and they could decay and they could produce, photons or so on. Yeah.
So I have one more nice question. Like the ALP masses are quite lighter. So how can they? I mean, it's just neutrinos don't fall in the dark matter candidate as due to their mass constraint. So how ALP still can be a viable dark matter candidate with such smaller masses?
Yeah, so basically, what's the dark matter in the sense that we basically cannot observe it. That's the that's the main thing. In the case of neutrino, we can somehow basically observe it by few, if not directly, we can then indirectly also. We can sterile neutrinos are there. They are the candidates because we cannot observe them. So
they also have bounds like below keV, we cannot consider them as a dark matter candidate. So
yeah,
there's a certain bound.
Yeah. So this is also an upper bound. So what we showed kind of an upper bound. So for ultralight ALPs, the upper bound is like the mass, it could be in the 10 to the power minus below 10 to the power minus 6 electron volt, which is very light. We cannot. We cannot see any observation through them. We cannot have. We have to be, by other means we have to probe them, and this is one of the way to probe them.
Okay. So in in your Feynman diagram, you have shown that the reverse production of ALP from the photon decay, I guess. So yeah.
No, it's not a decay. It's a kind of oscillation. So it's similar to neutron
oscillation. Okay.
Yeah.
So so what triggers the production of ALP from this photon when photon propagate and then they oscillate into Axion ALP? So what triggers it to be?
Trigger in the sense, it's kind of like via exchange of this photon. This you can consider this like a virtual photon. Which basically so it's you can look at it like a real photon, and you can see this interaction happening via this virtual photon. So that's how you can look at this interaction. Trigger in what sense, I don't understand. What do you mean trigger? It's kind of an interaction, and through since the interaction requires some kind of a mediator, so you can look this particular photon as a kind of a virtual photon, which basically acts like a mediator for this interaction to happen.
Okay.
Going to the literature and then answer.
Yeah. You can email me also. It's in the any questions. If has any question, you can email.
Okay. Thank you. So let's thank. I think there are no more questions. So let's thank this speaker. Thank you, Bhanu, for your beautiful talk. So next we have in line Kardarish Kurba. So Kardarish, are you there?
Yes, Vivek.
Yeah. So please, Kardarish. So please, please share your screen and then. You have to share your entire screen, okay? Or it will screen will be frozen.
Yeah. Is it visible now?
Yes, your screen is visible. You can do it. Oh, it's gone again.
It's gone.
Yeah, it's gone.
It's coming now.
No,
or not?
It's not coming now actually. Just try again to share your entire screen.
Yeah. Is it visible there?
Yeah, now it's visible. You can do it in full screen mode.
Then, oh, now it's not working.
It is gone again.
Gone again. You have to share your entire screen. Let me remind you again. Gone again. So, Kadarish, have you emailed your presentation to
PDF?
the?
No.
Yeah. Okay. Please email this to
Okay,
Physics Frontiers, and I
just
can share it here. Yeah, just email will do. Just email it right now. Okay. So after that, Anil Kumar, are you available now? Anil Kumar.
Yeah, Vivek, I'm available.
Yeah. So Anil, please share. So Kadarish, you can, in the meantime, you can email that the presentation to Physics Frontiers. We can schedule your your talk just after Anil. Okay, will that be fine?
Yeah.
Okay, fine then.
Yeah,
Okay,
that's fine.
Anil, can you please share your screen?
Yeah, I'm
proceed.
sharing. Is there any background noise?
No, there's no such background.
Okay.
Please share your screen, and then we can proceed for your presentation.
Is my screen visible?
No, it's not. It's not yet. So, are you finding some difficulty?
No, when I'm clicking to share, it is giving me options: use system desktop capture, use system window capture. What I have to select?
Windows desktop, I guess, the entire one. Share entire screen, basically.
I think we have to make the presenter host. Then only they will be able to share the screen.
Actually, I have made the actually. Okay, let's try with that. But it was going fine up till now. Okay. So Anil, I am making you the host for. So I'm making you the host for some time. Okay. So you can just if it's you can just share your screen now.
Okay. Okay.
So Anil, you can do the same thing now. Actually, same thing as.
Actually, it is Ubuntu 22 update problem. So I'm
okay, yeah, okay, fine then.
I will send you.
Sister send me. So again, we go back to Kadarish Kurba. So I have received your presentation. So I'll be presenting it now, Kadarish. Okay, and you can.
Yes, yeah, please do.
Yeah, so it's visible, right? It's visible, I suppose. So full screen mode. Yeah. So is it fine? Yeah. So please move ahead and let me know when to change the slide. I'll change it accordingly. Okay.
Okay.
Sure.
Yeah. So should I share my video also? Or?
Sure. It's so it is fine. You can share. Yeah.
Okay. So good morning, everyone. I'm Kateris Kulpa, a PhD student from Cotton University. So today I'll be talking about the period amplitude relation of diffuse orbital Cepheids in the Magellanic Clouds from the models and observations. So can we go to the next slide.
Yeah.
Yeah, so these will be the outlines of my talk. I'll start with the introduction, methodology, discuss the results, and come to the summary of the work. So this is the variability of the different classification of variable stars. However, the my object of interest are mainly pulsating stars, and that also mainly classical Cepheids. So I have shown like in the comic slides these pulsating stars. Can we go to the next slide, Vivek? Yeah, these are pulsating stars in this variability tree, and also mainly Cepheids in this tree. Yeah. Go. So classical Cepheids, they are readily pulsating stars, which occupy a narrow vertical band on the right hand side of the HR diagram. This is also called as also known as the instability stream. So yes, next slide please. So this image is in the image of one of a classical Cepheids, which is the brightest one in the Milky Way galaxy, also known as RS Puppis. So classical Cepheids, they have these the properties with the mass variation from 2 to 15, and they also pulsate in their fundamental mode, first orbital mode, and other multimode also. So the classical Cepheids in the Milky Way are metal rich. However, the classical Cepheids in the Magellanic Clouds are relatively metal deficient compared to the Cepheids in the Milky Way galaxy. These Cepheids are also known as standard candles, by which we can measure the distance to the Cepheids, and also so here I've shown you this the light curve of a different class of different types of Cepheid variables pulsating in the fundamental, in the first overtone and second overtone. So we can see here that each of these classes, the light curve, the shape of the light curve is different compared to the other one. So by looking at the light curve, we can absolutely say that this class of variables are fundamental first overtone or second overtone. So since in the I have mentioned in the beginning about the Magellanic Clouds, so this the left hand side represents the large Magellanic Cloud, in short LMC, and the other one is the small Magellanic Cloud, or the SMC. Both together they are also known as the Magellanic Clouds, and also they are also known as the satellite galaxies of the Milky Way galaxy. Look, which are about the LMC is about 49 kiloparsec from the Milky Way, and SMC is about 62 kiloparsec from the Milky Way galaxy. So Cepheids are important objects in astronomy because they obey a well-defined period-luminous relation, which is discovered by Henry Leavitt. The period-luminous relation is the correlation which shows that the correlation of the luminosity of a Cepheid with the period. The longer the period of the Cepheid, the brighter the star is. So Cepheids are important objects in astronomy, as I've mentioned, because they obey a well-defined period-luminous relation. From the period-luminous relation, we will know the distance to the star, and knowing the distance to the star will open up us to another a broad properties, such as the structure of the galaxy and the universe in general. They are also serve as first rung in the extragalactic distance ladder, and thus they play a very important role in the determination of the Hubble constant. So in this work, we have also modeled the light curve of Cepheids using the publicly available software known as MESA. So the main inputs that goes into the MESA are mainly the mass, luminosity, effective temperature of the star, and also the chemical composition of the target galaxy that we are interested to study, and also the additional input parameters which are we take are these convection parameter sets, which are given here: set A, set B, set C, and set D. These are we have taken these convection parameter sets from the MESA documentation paper, and we have taken these as it is without any changing in this value of these convective parameters. So I think there's a slide before this. Yes, so first we compute the linear analysis of those grid of models that we have taken, and from the linear analysis we get the growth rate and the linear period of the models, and we choose those models in which the growth rate of the first orbital mode is greater than the fundamental mode, because that is the main mode, that is the main aim of this study. And from the linear analysis we found that convection set B and D, they produce good number of first orbital models. So when we so the main common parameters in these two sets is the inclusion of the relative cooling parameter. Maybe this relative cooling parameter plays an important role in the position mode of the models. So after we get the information from the linear analysis, we continue with the nonlinear analysis. Next slide, please. Yeah, so in the nonlinear computation, we compute the model for about 4,000 pulsation cycle, and we check that the model must satisfy the criteria that the model that these parameters that have shown here in the plot, that is the variation in the amplitude and the pulsation period, and also this um, yeah, and also this fractional growth rate of fractional growth rate of the model vary by 0.01 in the last 100 pulsation cycle. So in addition to that, we also perform period O4. So for the observations, we have taken the data from Orbital 4, which is available in VI band, for Gaia DR3 in GNTRP, and VMC in YGKS band, that is the near infrared bands. And for all these observation data, we have corrected for extinction using the red ring map from Scoron 2021. So here I have shown you one of the representative of the light curve that we have computed using the models. These gray dots are the one obtained from the observations, whereas these red lines are the one we obtained from the models in different bands. So we can see here that the models are able to reproduce the observations using this MESA RSP for these input parameters that I have shown here, Z, M, and L, and effective temperature. So this is the period amplitude distribution of the first orbital Cepheids obtained from the observations for the LMC and SMC in V band. So these period amplitude represent we fit are represented using a 2 Gaussian fit. Can we go to the next slide, please? Yes, so from these two Gaussian fits, we can see that the mean of this Gaussian fit for the LMC is about 0.298, and and the second Gaussian fit is 0.383. And in comparison with the SMC, we see that that the first Gaussian fit, that is the blue one, it is comparable to the second Gaussian fit of the LMC, which shows that the SMC Cepheids are contains stars of higher amplitude, and they also shows they are more evolved stars compared to the LMC. So these are the amplitude distribution obtained from the models. So what we have done here, we have applied this. We have been this the entire distribution in this period bin size, and then we also slice it in different small size. Then we obtain the mean of each bin size and then plot it here, so that we can beautifully observe the trend of this amplitude distribution. And we can see that just it is well known in the literature that for the empirical period amplitude distribution, that as the wavelength increases, the amplitude also decreases. So it is interesting to see that even the models also are able to show that trend, that as the wavelength increases, the period of those light curve are also decreases. This is true for both LMC and SMC. So I have, as I have said earlier, this is the amplitude for the observations in different bands. So as we can see here, that as the amplitude, so we have also made a comparison of the period amplitude distribution between the models and the observations. These gray dots are the one obtained from the observations, and these colored ones are the one obtained from the models. So from this comparison, we can see that the models that we have obtained from MISA-RSP, they produce this light curve with higher amplitude compared to the observations. Although we can see some overlap between the models and observations at a certain period bins. So the input physics and the convection parameters seems to have play a very important role in the amplitude in the amplitude of the light curve. So the detailed investigation of how to the detailed investigation of how to change these convection parameters, so that we can get the so that we can get the amplitude of the models to agree with the observations, will be subject of our future work. So I leave you with the summary. So thank you for listening.
Thanks, Garish. Thank you very much. So the platform is open for questions, one or two quick questions. You can unmute and just ask your question. Okay, so if there are no questions, so I have one small question. Okay, so you mentioned about the input parameters for MESA, right? So there, I did not see anything about the magnetic field input as an input. So, and then on slide number 18, you have showed us that the light curves that you got from the computation aligns well with the observation. So, does that mean that magnetic field don't affect much the variability or something like that? Or what do you comment on that? Yeah, regarding the effect of magnetic field on the variability?
I think these are pulsation models that we have computed using RSP, right? So I don't recollect at the moment that we have magnetic field as one of the input parameters. Yes.
In one of the slides, you mentioned about like this one, like you mentioned the input parameters. There I didn't see, like you mentioned about temperature, you mentioned about something, but you didn't mention about the magnetic field. That's why I was curious that why will not magnetic field affect?
Yeah. So I think we don't include magnetic field as one of the input parameters that goes inside the RSP for this pulsation. Yes.
Okay, fine then. Okay, so if there are no more questions, then let's thank the speaker. Thanks, Kadarish. The beautiful talk. Okay, so I will stop sharing the screen now. So so next we have Anil Kumar. So Anil, will you be able to share your screen, or should I do it?
You please.
Let the screen, right? Okay. Let me just share the screen. You have already mailed this to me. I can see it. Okay. So it's already here. Yeah. Okay. Just, yeah. The screen is visible, I suppose. Yes, it's visible.
Yes.
Screen mode.
So good morning, everybody. So this is study of non-radial oscillations in newly born stars with effects of phase transitions from nuclear matter to quark matter. So next slide, please. Yeah. So when a star, this is basically the life cycle of a star. When a star is formed, like this is protostar, if it is massive at the end of its life, so it will go through a super red giant. And if it is a small star, like less than 8 solar mass star, then it will be a just red giant. And for a red supergiant, there will be a supernova will be there, and at the end there could be a black hole or neutron star can be a remnant, depending on the mass of this star. So when this supernova explosion happens, basically there is a inner core inside the massive star. So this is a iron core in approximately thousands of kilometers radii. So when this a time comes when radiation pressure is not enough, and this supernova explosion happens, the matter, this core shrinks due to the immense gravity, and the infalling matter collides with this core. This is a very dense core, and this iron matter, iron nuclei, means proton neutron comes out of the nuclei due to the high density. So this infalling matter, when collides with this dense core, there is a immense shock wave, and this is basically the supernova, and there is a resultant neutron star. So here we will consider only the case of a neutron star. So yes, next slide, please. So when neutron drift happens, means there is only neutron star. Initially, it has a size of radius of almost 20 to 30 kilometers, like that, and it is very hot. And YL is the fraction of leptons, like electron plus neutrino, divided by the total number density, baryon number density. So initially the entropy of the star is very high, like 2 to the 2 or 3, like that. And radius of canonical 1.4 solar mass star is like 20 kilometers. And then after with time, this radius, this size of the star decreases, and there is a possibility that quark matter, strange quark matter, may appear inside the star. Quark matter is basically the deconfinement of nuclear matter. Nuclear matter is composed of up and down quarks. When they come out of the neutrons and protons, there is a deconfined quark matter. So, but quark matter is up and down is not stable. Appearance of strange quark matter makes it more stable. So there are two possibilities that with under certain circumstances, there could be a hybrid star at the end product, or there could be a total strange star. The total bluish star is at the end, at stage 3, is a strange star. The Y nu is the fraction of neutrinos. There are no neutrinos here. and it has a radius almost 10 to the 15 kilometers. And if it is a hybrid star, then there could be a core inside the star. So next slide, please. So accordingly, we have to construct a equation of state for this scenario for all the stages. So pure nuclear matter, we consider the RMF model for the equation of state. This Lagrangian is written here. So these are the mass of nucleons. There are mass of nucleons and Mn, and different sigma, omega, and rho mesons are the mediators between these nucleons. And energy density and pressure of this nuclear matter or baryonic matter can be written like this. And for quark matter, next slide, please. Both of these equation of states we have constructed at a finite temperature. For strange quark matter also, we have to construct equation of state at finite temperature, means not equal to 0. Vector bag model, like we consider here the vector interactions, repulsive vector interactions, and this constant B plays a very vital role in the equation of state. So this is just a free parameter, but if there is a strange star, we have particular window for this bag parameter. Means in that stability window, the strange star could be possible. Outside this, there can be neutron star. So energy density and energy density and pressure of quark matter can be written like this, and this F and these are the Fermi functions at finite temperature. So in between, there could be a mixed phase in the while the transition from nuclear matter to quark matter. This is a smooth transition with Gibbs construction. So as we know from a first order phase transition, pressure, a chemical potential, and temperature should be equal in both the phases. So here we can say some conditions like charge neutrality conditions. This chi is the volume fraction of the quark matter with respect to the total volume. So first one is the charge neutrality condition. Second is the energy density of that in that region. And this third one is the baryonic density of the matter. Yes, next, please. Then we have taken the different entropy per baryon. Like for the first scenario, as we have seen in that the third slide, that we can take entropy per baryon like 2 to 3 per baryon. And the fraction of electrons or fraction of leptons was higher at that time. So we have taken YL as 0.4, 0.3, and we have constructed the equation of state. Equation of state, basically the relation of pressure and energy density. First case in the stage 1, we can see that these are the different curves. Those are showing the equation of state. And the second stage, when there is quark matter there. And in the third stage, there is a possibility that strange star is also taken with the dashed curves. And in the third stage, there are no neutrinos. It is neutrino-free case. And we can see that with the pressure get increases with entropy and lepton fraction also. So next, please. Next slide, please. Next slide, please. So at the different stages, we have seen that at the stage 1, 1.4 solar mass has radius of almost 20 kilometers in the range. So here we can see that some of the equation of states are at stage 1 are satisfying, like at 1.4 solar mass having radius of almost 20 kilometers. At stage 2, when there is a small core of quark matter, this and lower entropy and lower lepton fraction, the size of the star decreases, and it comes like for 1.4 solar mass comes into the range of like 15 to 20 kilometers range. And at the stage 3, when it is a strange star, it has a very small radius, like because strange stars are more compact compared to the neutron stars or hybrid stars. Hybrid stars has a envelope of nuclear matter around the strange quark matter core. So here the radius of these are the different temperature at different stages. So at first stage, when there is pure nuclear matter, we have studied the effect of entropy and this lepton fraction. So with entropy, this temperature increases. And in the second case, when there is a small strange quark matter core inside the star, this temperature with number density. Number density means we are going deeper inside the star. The temperature at the surface is low. As we go deeper, once it is increases, and in the mixed phase region, it decreases due to the latent heat. Consumption of energy in form of latent heat, and again it increases in the quark matter core. And in the non-radial oscillations we study here. Non-radial oscillations, these are just the perturbation from the equilibrium. When star is in equilibrium, there could be some perturbations, and in case of Cowling approximation, first is the symmetric and static body metric, and we solve the for fluid perturbation as given by the zeta. And for fully ZR scenario, there are perturbation in the space-time matrix also. And then we solve the Einstein equations to find the solutions and find the frequency. Next slide, please. And so F mod frequency, when we solve those equations, when there is no node, means those are the fundamental modes of oscillations. Those are F modes. And at the different stages, we have studied the F mode oscillations. So these are having the frequency in the range of like few kilohertz, like 1 or 1.5 kilohertz. So these can be detected by future telescopes like Einstein telescopes or Cosmic Explorer, like that. So frequency, no, please keep on the F. Thank you. So F mod frequency, we can see that at stage 2 increases a bit because star becomes compact when there is some presence of quark matter core inside there. So at the end, at stage 3, if it is a hybrid star, then its frequency could be higher compared to a strange star. So strange star, we have considered, as I mentioned, fixed values of Beck constant. So accordingly, to the maximum value of B, this strange star curve is plotted for F mode. And next slide, please. For P mode also, P modes can have more than one or more than nodes. So from the calculation of full GR calculations, this is done in Cowling approximation. So here we calculate the P mode frequencies. So at the stage 3, we can see that this P mode can easily distinguish at for the 1.2 or 1.0.8 like masses stars. It can easily distinguish the hybrid star and a strange star as a remnant. So next slide, please. Now we come to the conclusion that if in future F mode get detected by the future generalistic telescopes, then F mode can distinguish means F mode by the observation of F modes. We can just after the supernova, we can say that if there is a remnant quark star or a hybrid star, if means there will be a peak. Can you go to please previous slide? F mode slide. So means we are moving with time here. Stage 1 is at the very starting. At the stage 3, you can see that with time there, if it is a hybrid star, then the frequency of F mode will be higher compared to the strange star. If it makes a strange star, then there will be a peak in the F mode frequency. Next. No, thank you. If P mode get detected, then they can easily distinguish, but those are having very high frequency compared to the F mode, so they are difficult to be detected. Thank you.
Okay, thanks Anil. Thanks for the talk. So the platform is open for questions, 1 or 2 quick questions. So if there are any, kindly unmute and. Okay, so Anil, I have one quick question. So in the construction of equation of state, basically, so you only took the constant entropy approach. Why didn't you take the variable dependent and entropy approach?
Actually, that makes the situation more realistic, and we can vary the entropy also, but that need dynamical simulations. Means either we can keep temperature constant, but that is not a realistic case as compared to keeping entropy constant. And that is the scenario. If you want to vary the entropy inside the star, that will vary small, but we need dynamical simulations there to create a perfect scenario for the supernova explosion.
Okay, so you're mentioning that the temperature variation is the reason, like you took
yeah, if you go to a temperature graph, can you go to?
Yes, sir. Here, right?
Yeah, here. If you keep the entropy constant, then this graph increases. Means those are realistic things. Inside the neutron star, temperature is increasing as we are going deeper.
Okay, fine then. Okay, okay. Thank you, Anil. Okay. So thank you for the talk. So next we have, I guess, Gautam Saikia. Dr. Saikia, are you available here? Dr. Saikia?
Yes, I'm here. Can you hear me?
Yes. Can you please share your screen? I don't know. There was problem with Kardarish and Anil's. I can. Yeah, you can share your screen, right? Okay.
You can see it?
Yes, I can see it. Okay. Please. Yes.
Right. So good morning, and first of all, many thanks to the conveners of this national conference for organizing such a wonderful event, and for this opportunity to share some of our work here. So my name is Gautam Saikia, and currently affiliated to Nazionale College, and today the title of my talk will be Mapping a N11 star-forming region in the Large Magellanic Cloud. This work was mainly done by Anshuman Borgohain from Tezpur University, and in collaboration with Shalima from Manipal and Dr. Rupjyoti Gogoi, who is our supervisor, PhD supervisor, also from Tezpur University. So as you can see in the background, this is an image of the Large Magellanic Cloud, which we can actually see with our naked eyes in the southern hemisphere. This is a very interesting spot for astrophotographers and astronomers alike. And before going into the subject matter, let me quickly refresh or introduce you to the Magellanic Clouds. So the name Magellanic Clouds, please don't let it confuse you. These are not exactly clouds, but actually satellite galaxies to the Milky Way. There are two Magellanic Clouds, the LMC, the Large Magellanic Cloud, and the Small Magellanic Cloud, which is the SMC. So these are basically rotating around the Milky Way galaxy, and you can see this in an all-sky map of the galaxy, where they're located exactly in the southern hemisphere, the right-hand corner. And these galaxies have a history of tidal disruptions, which are occurring due to gravitational interactions among these two LMC and SMC galaxies, as well as with the Milky Way galaxies. So originally, it is speculated that the LMC and SMC were, in fact, spiral galaxies, dwarf spiral galaxies, but due to these tidal disruptions, they are now seen as irregular dwarf galaxies in the local universe. So along with the Andromeda galaxy, which is our closest galaxy, and the Milky Way, these two make up a part of the local group of galaxies, which is basically a gravitationally bound system. Now, the interest in studying the Magellanic Clouds peaked mainly due to two reasons. First, because we cannot exactly see the central portion, the galactic plane of the Milky Way, because of the presence of a large amount of extinction. There is a lot of dust and there is a lot of star formation which is going on there, because of which we cannot see the complete picture of the Milky Way. Instead, if we go to the southern hemisphere and look into the sky, we see the LMC and SMC, which have actually lower metallicities as compared to the Milky Way galaxy, which means that they are metal poor environments and they resemble systems which were there when early galaxies used to form. And they have an intermediate stage of evolution, which makes them quite interesting. Now, going deeper into why they are important for study. So this graph you have already seen earlier this morning. So this is an extinction curve of the Magellanic Clouds as well as the Milky Way galaxy, which was produced from observations. So these two galaxies, first of all, they're very close to us. The LMC is only 50 kiloparsec away and the SMC is only 60 kiloparsec away. In addition to that, their orientation, that is their inclination angle to us, is almost face on. That is almost like 30 degrees inclination, which helps us study these galaxies in a very resolved manner for both gas as well as dust studies. That is kinematics, dynamics, anything we want to study, we can study. Moreover, since they have low metallicities as compared to the Milky Way, and these low metallicities actually resemble high redshift galaxies, say galaxies which are beyond redshift of 1. So since we do not have access to very far off galaxies which have these metal poor environments, we can actually use some models which we have, try to apply these to the SMC as well as LMC, and then interpret results which we are getting for high redshift galaxies using these results. And one very interesting feature, as you can see from this graph here, is this bump here, the peak, which is seemingly absent in case of the SMC, the small Magellanic Cloud, but is present in case of the LMC and the Milky Way galaxy, which has been attributed to different things, mostly the absence of graphitic carbon or PAH, the polycyclic aromatic hydrocarbon molecules. So the topic of study here today is the large Magellanic Cloud, which is the LMC. As you can see from the beautiful picture here, the LMC still has residual bar. So it is speculated to be a spiral dwarf earlier, and now it is an irregular dwarf galaxy, but it still has this bar in the center, and it has a very low metallicity as compared to the solar metallicities, solar neighborhood, with a good face-on inclination angle, as you can see from the diagram. And two regions which have been marked here, the 30 Doradus and the N11, are actually prominent star-forming regions within the LMC. So star-forming regions basically means they are H2 regions, which have very intense environments, and a lot of processes, astrophysical processes are going on within it. And since these advantages are there for the Milky Way for the taking, it is ideal for investigating these large-scale galactic dynamics and evolution of different ISM phases, let's say the neutral ISM, the H2 regions, and so on. So there have been many recent studies. Of course, over the last 3 decades, there have been different studies on the Magellanic Clouds, but recent studies have shown that there is a good correlation between the high mass star formation and the distribution of H1, that is the neutral hydrogen, and CO clouds in the LMC. Moreover, the column density of molecular hydrogen is correlated with star formation, because whenever stars need to form, the clouds need to collapse, and it needs a very high density, and this can only accumulate only when the clouds has cooled down. So basically, molecular hydrogen can only sustain in temperatures say less than 100 Kelvin. So the molecular hydrogen is directly actually related to the star formation. There is more molecular hydrogen, meaning there is more star formation rate which is going on in a galaxy. Now the 30 Doradus being more prominent and the most massive H2 region in the LMC has been studied by numerous telescopes in the recent past, but the N11 has played second fiddle to it, mainly because it is this second in size to the 30 Doradus nebula as the second largest H2 region in the LMC. So this N11 region has different names depending on nomenclature and who named it. So let me quickly tell you the motivation behind this word, why we chose to map the N11 region. So basically, the gas nebula or the dust, houses which are considered to be the birthplace of stars, they dominate the atomic and molecular reactions which occur purely in the gas phase, but depending on the different galaxy types, say if it is spiral galaxy or an irregular galaxy, and as well as the location within the galaxy, if it is in the inner disk, outer disk. So very different star formation rates can be seen, even though the amount of gas is the same. So that it depends on the local effects which control how the star formation occurs in different phases of the ISM. Now, the low abundance of these metal poor galaxies like the LMC and the SMC, low abundance of dust, what it means is that the UV photons which are coming from different stars and high energetic sources, they are easily able to permeate into longer distances within these galaxies, which causes the destruction of molecules. And maybe because of that, we get lower, CO and hydrogen luminosities, which makes it difficult to determine the molecular hydrogen content within any galaxies. So what we are trying to do here, we are trying to take a sample of early OB type massive stars towards the N11, star forming complex. And then we are trying to infer how much hydrogen column density is there in our line of sight. That is our aim here. Let us take a closer look into the N11 complex again. So you can see from the figure here, the N11, it is actually located somewhere in the northwestern region of the LMC, and it spans a elliptical shape of about 25 by 21 arc minutes across the sky. And in the center, you can see actually a super bubble cavity which is there, and it is targeted by mostly X-ray telescopes like the XMM Newton, the E Rosetta, and others, because it was formed due to a supernova remnant, and there are strong stellar winds which are occurring within this structure. In addition to that, it is surrounded by intense star clusters. As you can see, the four prominent ones being LH9, which is located here, LH10, LH13, and LH14. These are OB star associations mainly. So we have selected our sample of OB stars from this region itself. And the brightest among them, the N11B, this one, is also funnily known as the Bean Nebula because of the shape it resembles in the pictures. Right. So how we calculate the column densities? First of all, it may sound very simple and trivial that there is so much hydrogen. It is one of the most abundant molecules in the universe. So why don't we just directly measure it? So what the problem exists is that it lacks a dipole moment, and in molecular clouds which are cooler as compared to the surroundings, the energy or the temperature is too low to excite them into quadruple vibrations, and hence we cannot directly measure the molecular hydrogen. Instead, what we do is we look at for the rotational transitions for the next most abundant molecule, which is the CO, and the CO is used as a tracer of molecular mass in a galaxy. Now there are different available literature. A lot of work has been done in this area, but the consensus is that this formula, this equation you see here, is usually used for the calculation of molecular mass density in a region. So there is something called the XCO conversion factor, which varies from region to region. So we have used the one from Galamed's 2016, and then there is this WCO, which is taken from the CO maps, which are directly observed using different telescopes. So here we have used the Planck CO maps to calculate the WCO, and then for calculation of the extinction and radiation, we have simply used a catalog of 1750 massive OB type stars in the LMC, which was actually observed by the Spitzer Space Telescope back in 2009 during its SAGE survey. The SAGE survey was done especially for the Large Magellanic Cloud, keeping various star formation objectives into mind. So the total hydrogen column density which we get is a mixture of the neutral hydrogen and the molecular hydrogen. And since the distance of the N11 region is about 55 parsecs from us, we have taken these stars and then calculated their distances using this Poisson formula and extinction, and then we have put them in a 3D distribution, like how far they are located in our line of sight, and then we have made different bins. Say from 20 to 30 kiloparsec there are some stars, then 30 to 40 kiloparsec there are some other stars. Finally, what we have done for each of the bins, we have taken these bins as a 2D surface and tried to calculate the overall column density, what will be what it will represent as a single dot here in this variation you see along the line of sight. So after fitting all these things, and then after plotting the variation of neutral hydrogen as well as the molecular hydrogen, which you see here, this maps which we got are actually smaller in size than the total area of the N11, which is mainly because what we had, the CO maps or the stars which we had used for the distribution, they were concentrated at a very small area in the central region of the N11. It did not, we did not go for more recent surveys. That is one of the drawbacks of this work, which we are working on right now, say the Gaia survey, which has a lot more data. And what we have seen from these initial results is that the trend which we see is the neutral hydrogen is actually decreases steeply as we move away from our Milky Way galaxy towards the N11 region. And once we have separated the atomic and molecular hydrogen using the CO maps, we also see a decrease from 25 to 45 kiloparsec steeply, and after 45 kiloparsec the values actually decrease at a slower rate with increasing distance. So what our results indicate is that these hydrogen column density which we have seen is mostly in the foreground, and the stars which we have taken are also limited due to our view which we have taken, the catalog we have taken, which we plan to increase in the near future and take a larger sample for much better dust maps. So we're using this simplistic method of calculating the hydrogen column density. So this is mostly what I wanted to share with you today. Any comments and suggestions are welcome. Thank you so much.
Thank you, Dr. Saikia, for the beautiful talk. So the platform is open for questions. We can take one or two quick questions if there are any. So, Dr. Saikia, I have one quick question. Okay, so you mentioned about low metallicity in LMC collecting.
Yes.
LMC. So it might be a naive one. So what is the reason? What do you think? What can be the reason behind the low metallicity in the LMC?
Low metallicity, there are different
from that.
Sorry.
What can we infer from that basically, from the low metallicity?
Right. So low metallicity basically means, from what I understand, is that the content of dust is much lower in these galaxies actually. So if the dust content is low, and what will happen is these photo dissociation regions which are there, the high energetic X-ray sources or the gamma sources, they'll easily penetrate these galaxies, and they'll lead to the destruction of most of these high metals, the molecules which are available easily in these galaxies. So once these metals are destroyed, obviously the metallicity goes down. That is what I have read.
Okay.
Yes.
That's fine. Thank you. Okay. Are there any questions then? The question? Okay, so if there are no questions, let's thank the speaker.
All right. Thank you so much.
Thank you so much. So next we have Kamal Krishnanath, Niger, Orissa. Kamal, are you there?
Am I audible?
Yes, you're audible.
Okay, I will share my screen.
Yes.
So is it visible?
Yes, it's visible. It is in full screen mode.
Is it full screen or?
Yeah, yes, it was present as slideshow.
Yes.
Yeah.
So first of all, thank you. I would like to thank the organizers for providing this opportunity. So first I will start with the motivation behind this talk. The title is the universal relations for a generic family of neutron star equation of states. So as we know, for the black holes, we have one theorem called no-hair theorem. So it states that an isolated non-charged black hole can be entirely described by their mass and spin angular momentum. So in other words, if a progenitor or a progenitor star or a massive star collapses, to a black hole, it is unmeasurable. The matter the matter content which was in the progenitor or the equation of state is unmeasurable. So of course, black hole is a singularity, but the for the extended objects like neutron stars and quark stars, this type of universality was not expected. However, recently we have found that this type of universality does exist. So these I love Q relations are an example of this type of universality. So what I or love or Q stands for here is the I is the moment of inertia, love is the tidal love number, and Q is the quadruple moment of the compact object. So why these relations are important? Because of their insensitive nature towards the equation of state of matter. So observing any one of the this parameter or observable will lead us to the values of the other parameters. So in this way, they are they are significant. And how we let's see what type of tests which have been done until recently. So these universal relations were largely been confined to a limited set of tabulated equation of states or polytropic equation of state. So what we are trying to do here is we are trying to construct a very generic family of equation of states. But they must follow two sets of data. One is the theoretical limits and other is the observational constraints. So why we are doing this? Because in the entire density regime of matter, so we know the nature of the matter up to a certain density. In this case, the nuclear saturation densities. So this BPS or CET you are saying, this band, we actually know a lot of details, and even at asymptotically high densities, at 40 times the nuclear saturation densities, we also know the theoretical limits to the equation of state of matter. But in the intermediate region of the of densities, this is still unknown, and we don't know anything about the state of matter. So what we do in this this intermediate region, we try to create some toy models using the adiabatic speed of sound as a parameter. So we arbitrarily make several segments, and using the adiabatic speed of sound, and of course we keep we let it to follow the thermodynamic constraints, thermodynamic values. So and it should not violate the causality. And then we subject it to the two sets of data which we are talking about earlier, like the theoretical constraints and the observational data. So then what we do, we linearly interpolate these segments. So regarding the observational constraints, there are two kinds. One is the data from the NICER. So it provides the radius constraints for different masses. And the other is the LIGO, where we get a constraint on the dimensionless tidal deformability. So imposing these two sets of data, we led to the construction of this equation of states. And these are the figure on the left is the equation of state and the family of equation of state, and the right side it is the mass radius curve. So we have also highlighted a recent observation of a very heavy mass neutron star. So we have also highlighted the maximum mass of a different spectra. So that why this differentiation in the spread in the equation of state for different range of maximum mass states that maximum mass is a property of equation of state. So if we know the mass distribution of a star, so the value of moment of inertia and quadrupole moment are known. But to find the value of the tidal love number, we need to solve the diagonal part of the Einstein equations along with the perturbative element. So once we solve that, so we get the values of all three parameters theoretically, of course. So now if we plot these parameters with respect to mass, so we can see the similar spread which we saw while plotting the mass radius curve or the equation of states. And it is understandable because they individually are dependent on the state of matter. But however, if we plot them against each other, you can see suddenly the spread is almost gone and it's minimal. And if we plot the same data and do error analysis through a fitting function, so we can see that the spread is gone and they don't separate out depending on the maximum mass. So this is an inference like why these universal relations are not dependent on equation of state of matter. So this error analysis also says that there lies a maximum deviation beyond which we consider that these equation of states will no longer remain universal. So we consider this 5% tolerance limit. Hello? Yes?
2 or 3 minutes left.
Okay. So here we consider that this 5% tolerance limit is the definition for the universal relations. So next, what we consider some extreme cases where in one scenario the speed of sound remains monotonous in the interior region, and it after that it gradually decreases at asymptotically high energies to the value of 1/3, which is the conformal limit. And second, also we consider the speed of sound gradually increases monotonically, but reaching the limit of 1/3 at asymptotically high densities. So we also categorized on the basis of whether the data is obeying the observational constraints or not. So what we see here, that given these extreme situations, if they are following the observational constraints, they too follow the universal relations. So here you are seeing this. And if we consider the equation of states with extreme nature and they don't follow the universal, they don't follow the observational data, and they start deviating from universality. The deviation can be seen to be 10% or more for typical lambda range of 60 to 800 in the tidal love number. So what we see here, like these observational constraints seem to keep this group of neutron stars well within the tolerance limit. So there, what we can infer here, that there exists a correlation between the observational constraints and the universal relations, or the universality in neutron stars. So in terms of a back calculation approach, these universal relations can serve as a tool to identify the equation of states that could follow the observational constraints. So what are the future prospects then? So more number of observations which are coming in the future. So this data can successfully constrain the spread in the equation of states even more. So, and these universal relations will be a big help in these scenarios. So thank you. And any questions?
Yeah, thank you so much for the talk, Kamal. So the platform is open for questions. We can take 1 or 2 quick questions. You simply unmute your mic and speak. Okay, Kamal, I have one quick question. So in the equation of state construction, basically, so how did you take care of the here how did you take, these are ad hoc equation of states, right?
Yes, yes.
Okay. So how did you take, so did you take into consideration any phase transitions, like first order phase transitions?
No,
the,
no. In this
no.
case, we have only considered the smooth equation of states.
Okay. And do you think
presently, actually, we are working on that equation of states with first order phase transitions. Yeah.
Okay. And do you intuitively think that this will affect the universal relations, or it won't?
Intuitively, I feel like that it will break because yeah. So we'll see.
Basically, basically the parameters of the universal relations, the moment of inertia, the tidal permeability are dependent on radius, I guess, right?
Yes. Yes.
Okay.
Yeah.
Okay. Thank you so much for the clarification.
Yeah.
Okay,
Thank you.
Okay. So if there are no further questions, let's thank the speaker. Thank you, Kamal. So we move on to the next speaker, Parthapratim Nath from Cotton University. Partha, are you there?
Yes.
Yeah. Yes. Please share your screen, and we can proceed to the presentation. Yes, your screen is visible. Yes, it is visible. You can just.
Okay. Hello, everyone. As I would like to thank the organizers for giving me the opportunity. I am Parthapratim Nath from Cotton University. The title of my talk is the study of a traversable wormhole using a suitable embedding function in isotropic matter field. And this will be my plan of talk. So wormholes are basically the solutions to Einstein field equations, which act as a bridge or tunnel-like structure that connect two distinct points of the same spacetime or two different universes. The tube-like structure is asymptotically flat on both sides. The Einstein field equation is shown in the diagram below. The left-hand side of the equation represents the geometry of or the curvatures of the spacetime, while on the other hand, the right-hand side defines the stress energy momentum distribution. So basically, this equation dictates how stress energy momentum determines the curvature of spacetime. One of the major property of the wormhole is its truth, which is defined as a two-dimensional hypersurface of minimum area, where the radius is minimum. The concept of wormhole was first studied by Einstein and Rosen in 1935. Their solution had some connections to the earlier work of Clem, who for the first time constructed the isometric embedding of the Schwarzschild solution. But his solution later had some stability issues. This figure represents some constructed diagrams of wormhole, which are basically theoretically constructed from their properties. While who was the teacher of Einstein first proposed the concept of matter in connection with the electromagnetic theory. He used the term one-dimensional cube to describe his findings. But later, is termed them as drain hole, and after that Wheeler named them as zeons and predicted the shape of the wormhole. Finally, Wheeler and Misner gave the name wormhole, and their solutions were transformed into Euclidean wormholes by many other physicists. Again, traversibility is also a very major feature of wormholes. If anything that enters through one side of the wormhole and it can exit through the other side, then we will term the wormhole as a traversable wormhole. But in order to become traversable, it should not contain any kind of singularity. The concept of traversable wormhole was first put forward by Keith Thorne and his graduate student Morris with the introduction of truth, which is a basic property of wormhole. they later formulated the basic theories and conditions regarding the traversable wormhole. The matter content of any kind of traversable wormhole needs a very different kind of matter, which is known as the exotic matter, and which can lead to the violation of all known energy conditions such as null energy condition, weak energy conditions, strong and dominant energy conditions. There are many speculations regarding the behavior of exotic matter. Some postulated that it may be a candidate of dark matter, which may cause the repulsion inside the wormhole, so that the throat remains open. But till that, no physical evidence of any kind of exotic matter has been found. So physicists tried various methods to minimize the use of exotic matter. Volume integral quantifier, thin cell wormhole are some of the famous propositions that quantify the total amount of energy violating matter. Again, many background theories were also developed, such as Kaluza-Klein gravity, mimetic gravity, FR gravity, FT, FQ gravity, Einstein-Cartan theory. In this modified theory, the matter inside the wormhole may satisfy the necessary energy condition, but the effective stress energy tensor containing higher order derivatives of Ricci scalar is responsible for the violation of null energy condition. In this work, we have considered the famous Morris-Thorne wormhole as shown in the equation 1. This equation contains two functions, which are phi r and br, which represents the redshift and shape function of the wormhole. Now, the temporal component of this metric, that is the term e to the power minus e to the power 2 phi, should not be equal to 0, because if it is equal to 0, then it will indicate the presence of a singularity. So we have to find the function phi r in such a way that the temporal components remain non-zero everywhere. We will assume this metric is a solution of the Einstein field equation as shown in equation 2. Now, solving the Einstein field equation for this matrix, for the Morris-Thorne wormhole matrix, the field equations can be calculated as shown in equation 3, 4, and 5, where rho defines the energy density and PR and PT represent the radial and tangential pressures respectively. Now, if we consider the energy momentum conservation law, then we can form a hydrostatic equation, which is shown in equation 6. This this shape function Br has to satisfy a set of conditions as shown in equation 7, 8, 9, 10, and 11, where the R0 represents the radius of the throat, which should be the lowest value of the radial coordinate R. The radial coordinate R decreases from negative infinity to a minimum value R0 and then increases from R0 to positive infinity. Here the equation 7 represents the minimality of the throat, while 8 and 9 represents the asymptotic flatness of the spacetime, and 10 and 11 represents the flare-up conditions. Now, at a constant time, we consider a slice of the space-time at theta equal to pi by 2. From this, we can find the embedding function ZR, which is shown in equation 12. Again, this embedding function also has to follow certain conditions, which are shown in equation 13, 14, and 15, which are related to the flare-out and stability conditions of the wormhole. Now comes to our wormhole model. here. And now to obtain the shape function BR, we propose a general embedding function which is shown in equation 16. This embedding function contains three parameters A, C, and D. Now, using the viable conditions of the embedding function, we found two relations among the three parameters, which are D equal to minus C or D equal to minus C minus 1. But if we consider D equal to minus C minus 1 condition, and by using it, if we calculate the shape function, then the formulated shape function may violate some of its stability conditions. So here we will consider only the relation D equal to minus C. Now, if we use this embedding function, then the shape function BR can be obtained, which is shown in equation 18. The obtained shape function satisfies all the necessary conditions. Again, the first derivative of the shape function should be less than 1 at the truth, from which we found that the value of C must be a positive number. So since we have formulated the shape function, our next task is to form the redshift function. In order to obtain the redshift function, we will assume that the pressure is isotopic, that is, the pressure is equal in all directions. So, using this condition, the hydrostatic equation that we have derived earlier can take the form as shown in equation 19. Again, we will use a state equation where pressure equal to omega times the energy density. Now, using all these conditions and using field equations, the redshift function is calculated, and which is shown in equation 24. Since the form of redshift and shape functions are found, now by using this we can further simplify our field equations and investigate the energy and stability conditions. These are the embedding diagrams of the wormhole constructed using the proposed embedding function. We have shown these plots for various values of A and C. From the plots, we can see that these profiles flare out slowly as both A and C increases. Similarly, these are the 3D profiles of the wormhole, again for various values of A. And this figure 4 justifies that the constructed shape function satisfies all the necessary conditions. Now, by using the field equation, we have investigated all the energy conditions. Null energy conditions is the lowest of all the other energy conditions. From figure 5, we can see that only for the case D and F, the null energy condition is violated, which means for the
sorry to so you have can you sum it up in 2 or 3 minutes?
Okay.
Yeah.
For the combinations of parameters as shown in D and F, if throat is filled with exotic matter, which stabilizes the wormhole. This statement can be further realized from figure 6. As you can see that the wormhole satisfies the flare-out conditions only for D and F combinations. But for all the other cases, the value of exoticity function zeta is negative. So here is our results and conclusion. Here we have obtained a traversable wormhole solution by proposing a general embedding function which has some 3 parameters. We have reduced or constrain those parameters by imposing the basic requirements of a traversable wormhole. Out of all the combination of parameters, C greater than R0 and A greater than 0, or C greater than R0 or A less than 0 are the best choices of parameters. For these combinations, the wormhole violates the null energy condition as well as obeys all the flare out conditions. The violation of null energy condition confirms the presence of exotic matter inside the throat, which is necessary to stabilize the wormhole in the general theory of relativity. These are some of my references. Thank you.
Okay, thank you so much, Partha, for the talk. So the platform is open for questions. We can take one or two quick questions since we're a bit running behind schedule. Yeah, we can take one or two quick questions from the audience. Okay, so if there are no questions, so let's thank the speaker. Thank you, Partha. Okay, so next, Dr. Biplab Sarkar from Tezpur University. Yes.
Hello.
Yeah, hello. Yeah, you can share your screen and
Yeah. So I have shared the entire screen.
It's not visible yet. Yes, now it's visible. Yes.
Okay.
You can do it in full screen mode. Then yes.
Is it full screen now?
Yes, yes. It is full screen now. Let's see.
Should I start?
Yes, please.
So thank you very much for giving me the opportunity to present my work in this conference. I'm Dr. Biplab Sarkar from Department of Applied Sciences, Tezpur University. So here the title of my talk is Simulation Techniques in Accretion Physics, and basically in the outlines I'll be presenting the introduction, and then I'll try to explain the importance of simulation in astrophysics. I'll discuss some of the simulation techniques in astrophysics. I'll discuss also some of the simulation codes, application, and conclusion. So one thing I would like to admit is that this is a review work, and me and my students, we are new to simulations, but we are trying to get into simulations. So basically this is an effort in that direction. So what is accretion? So accretion, as you know, is a very common process in astrophysics by which the mass of a body grows. So, and since angular momentum is invariably present in astrophysical matter, so disk accretion is quite common. So accretion often happens through a disk, and the studying the accretion process gives us information about various important characteristics regarding the accreting object, such as the spin and the mass of the accretor. And also accretion is the most efficient way to extract gravitational energy, and it is the primary mechanism by which we get high energy emissions in the universe. So in this diagram I have presented an artistic picture of a low mass X-ray binary system, which consists of a neutron star or a black hole as the accretor, and this is accreting from a companion star, which is a regular star. And since angular momentum is present in the accreting matter, an accretion disk is formed, and the accretion disk matter gets heated up, and we can get high energy emissions from the accretion disk. So now let's discuss what is the importance of simulation in astrophysics. So the accretion process is a highly complicated process. So solely studying accretion through the theoretical models alone cannot give us the complete picture. So it is very important to study the accretion physics through the development of sophisticated numerical simulations. Now, till date, quite significant advancements have happened in the field of numerical simulations, and these computational tools allow researchers to model the complex nonlinear dynamics of accretion flows, where we can include the effects of magnetohydrodynamics, radiative transfer, as well as general relativity. In fact, studying accretion through numerical simulations is a must in accretion in astrophysics nowadays, and it allows us to through computer simulations, it allows the researchers to make numerous predictions, which then later can be verified with the observational results. So now let's come to discuss the simulation techniques. So first is hydrodynamic simulations. The well-known equations of hydrodynamics, which are the Euler equation, the continuity equation, the energy equation, these are the standard equations of hydrodynamics. So in hydrodynamic simulations, the fluid is treated as a continuous medium and with a well-defined macroscopic properties. Suppose the velocity, pressure, or density of the flow at each point is considered, and this hydrodynamic simulation, it basically solves the equations of hydrodynamics. That means the continuity equation, Euler equation, and energy equation, these are solved. So various numerical methods are used to solve this hydrodynamical equations. Suppose we have the finite difference method, finite element method, finite volume method, and the particle method. One important class of hydrodynamic simulation is the smoothed particle hydrodynamics, and in this approach, you know, in this approach, a particle method is used for compressible hydrodynamics. So the concept of fluid is replaced with the set of points in smoothed particle hydrodynamics, and thereby a Lagrangian approach is used. So basically, we know there are two types of time derivatives in fluid dynamics. One is the Lagrangian and one is the Eulerian. So in Lagrangian approach, we move along with the fluid element, and then the time evolution is studied. So I would like to present some results. For that, I want to describe so basically the results I will be presenting will hold for black hole accretion. So a coordinate system is used for the accretion disk. So basically the cylindrical coordinate system is used. At the center of the cylindrical coordinate system, the accretor lies, and then in the XY plane we have the thin accretion disk. So keeping this in mind, some results I will be presenting. For example, this paper by Upasana Das and Pratik Sharma in 2013, they have used hydrodynamic simulations, detailed hydrodynamic simulations of accretion to study the varying viscosity prescriptions. So another paper which has used smoothed particle hydrodynamics is by Das et al. 2014, published in MNRS. So these are a couple of the results. So suppose the Mach number, that means the ratio of the flow radial velocity to the sound speed, how it is varying in the radial direction in the accretion disk, how the angular momentum is varying, that has been shown. And also in this particular plot, bottom right, we see the particle approach. Since this is smoothed particle hydrodynamics, this is the particle approach is used, and we can see how the distribution of particle is happening. In the Z is the vertical direction and R is the radial direction. So this is a vertical cross section of how the particles are in the steady state. What is the distribution of the smoothed hydrodynamic particles? So these simulations allow us to study the time evolution of various flow variables. Suppose how the shock location is varying with time is shown in this particular plot, or how the cooling is happening in the shock. So we can see that the shock location is varying more or less sinusoidally with time. The cooling, that means the Bremsstrahlung cooling mechanism by the electrons, how it is varying, or how the mass outflow rate, if some mass is coming out of the accretion disk, how the outflow rate is varying with time. So those time evolution we can study. This is also a simulation result where the time evolution of the shock location or the cooling rate or the outflow flux has been done. We have studied this in the Fourier domain. So this is the power versus frequency. So basically this particular variations, we have taken the Fourier analysis, and then we can see various quasi-periodic oscillations sort of behavior. So some broad peak features we can find. So these are known as QPOs, and these are highly important because these are regularly observed with observational data. When we study real astrophysical X-ray data, we see these, and with the help of simulation also we can reproduce this and to get a better understanding of the processes in the accretion disk. Another technique is the magnetohydrodynamic simulation. So which in magnetohydrodynamics, we deal with magnetized fluids in the accretion disk and jets. And MHD simulations also, they give us valuable understanding of how magnetic fields influence the dynamics and the energetics of the accretion flow. There are numerous techniques in MHD flows for simulating MHD flows. For example, the finite element method, finite volume method, the adaptive mesh refinement techniques. There are now a couple of methods. Also, slowly, the general relativistic effects have also been included in the magnetohydrodynamic simulation, and thereby it is called GRMHD. General relativistic hydrodynamic simulations have also been developed, which have given us a improved understanding of how the active galactic nuclei. So these are AGN are the active galaxies. How the jet production and its dependence on the black hole spin, this has also been studied. So Pluto is a widely used magnetohydrodynamic course, and this is a paper by Singh, Okuda, and Akhtar into 2021, where again they have studied the black hole accretion flow with the help of the code Pluto, and the accretion, this is the vertical cross section of the accretion disk, and here the different color coding, they have shown the how the density is varying in the different regions of the accretion disk, as well as the arrows, they are giving the velocity vectors of the accretion flow. How the velocity vectors are moving is shown by the arrows. Again, we have the radiative transfer simulations. So we know that the radiation, it will interact with the fluid, and thereby the temperature and dynamics of the fluid are expected to be affected due to the radiation. So then what is the correlation between the observed radiation emitted by a black hole or neutron star and its surrounding? That means the accretion disk. This can be explained by the radiative transfer theory. And so these radiative transfer simulations are also highly important to study stellar atmosphere, radiative shocks, and it can give us crucial understanding about the formation of spectral lines and about the composition of astrophysical objects. And this is another result by Gogoi et al. Published in MNRS in 2014, where they have studied the black hole accretion flow with the Monte Carlo total variation diminishing simulation. And so here again the velocity vectors have been shown, and the color show the normalized density on a logarithmic scale. So with the color coding, they have shown how the density is varying. So, and we can see also, since the radiation is included, the zigzag path show how the photons are moving in the accretion flow. This is shown by this purple color zigzag path.
Dr. Sir, sorry to interrupt. You have 2-3 minutes. Can you submit?
Yeah, I'll quickly conclude it. So the simulation code. So I would like to quickly show you some. In these links, if you go, you can get a list of simulation codes. For example, so if you go to the first link, we will go to this web page, awesome astrophysical simulation codes. There are a number of codes are listed here. The description, the language, repository, and also reference papers we can get. Also, the different, suppose the Pluto, I was talking about, the Pluto uses finite difference, finite volume, and Eulerian approach. So the different codes, what approach they are using, we can see from here. Also, what is the physics, hydrodynamics, MHD radiation, also general relativity, if it is used or not, we can get from here. So I would like to come to the applications. So basically, simulations reveal a lot about the instabilities, turbulence, and angular momentum transport in the accretion disk. It tells us about the jet formation and evolution. Or jet launching mechanism we can study very well with simulations. Also the how the outflows and mass loss, they are affecting the accretion this we can study. Also how the evolution of galaxies happen, that and how the mass falls into the central region, that also we can study. So this is the conclusions. So simulation techniques are have become very important in accretion physics research, and they give us a very powerful tool to understand the complicated dynamics of the accretion process. And in this review, I have tried to highlight the importance of numerical methods in advancing our knowledge of accretion phenomenon. And I want to convey the message that future research in this exciting field, more interesting results we can expect. So these are some of the references, and thank you very much.
Thank you, Dr. Sarkar, for the wonderful talk, wonderful review. So the platform is open for questions. We can have 1 or 2 questions. Participants, you can just unmute and ask your question. Okay, so I have one question, Dr. Sarkar.
Yes.
So you mentioned Pluto, right? Pluto.
Yeah.
Does Pluto take into account the shocks from like in the MSc simulations?
Yeah, definitely. And if you may refer to this paper, seeing the reference is given here. And in fact, shocks have been studied in this particular paper and in other papers also. And shocks and accretion are very well studied in numerical simulation.
Like the magnetically different shocks, they are taken care of in Pluto, right?
Yes. Yes.
Okay.
So in this particular paper, they basically explored the effect of resistivity. So ideal MHD ignores the resistivity effects, but if resistivity is there, then magnetic fields will decay, and how that is affecting the dynamics of shocks have been explored in this particular paper.
Okay, thank you. Totally look into it. Okay, so are there any other questions? Okay, so thank you, Dr. Sarkar, for the talk. Now, so the session, so there is a small change in the schedule. So this is the end of session 1 basically. So now the session 2 will start. So the session 2 will be chaired by Dr. Jaikhomba Singha from University of Cape Town, South Africa. So Jaikhomba Singha, he is here in the list.
Yes, Vivek, I'm here. Am I audible?
Yes, you're audible. So Jaikhomba, let me briefly introduce him to the audience. So Jaikhomba Singha is a postdoc at the University of Cape Town, South Africa. So he, prior to joining his postdoc, he did his PhD in nuclear, in basically in astrophysics, astronomy, astrophysics, particularly studying the pulsar timing. So he has been a core member of the Indian Pulsar Timing Array, as well as now a member of the International Pulsar Timing Array. So Jaikhomba, so the stage is yours. You can kindly chair the session. So the next talk is by Astronomy Baruah. Okay.
Yes. Am I audible?
Yes, Jaikhomba, please proceed to chair this session.
Yeah, thank you so much, Vivek. So let's start. So Astronomy Baruah. So we will start. So I will give you a warning at 8 minutes. So yeah, go ahead.
Is my screen visible?
Yes, I can see it.
Okay.
Oh, just one small. So prior to joining this one, so I have made Jaikhomba the host. Okay, Jaikhomba, is it fine with you?
Yes.
So I'll make you the host, and you can yeah. Yes, please.
Okay. Hello, everyone. Today I am going to present my review work on the topic relativistic accretors and high energy X-ray view. My collaborators are Lisa Devi and Dr. Biplab Sarkar. So, what is accretion? Accretion is the infalling of materials onto a massive object. This is an essential process in the universe which powered different astronomical objects like AGN quasars, microquasars, etc. This theory is based on principle of gravity. there are two types of accretion. Spherical accretion, it occurs when matter falls onto a central object from all directions, such as in the case of protostar or a compact object. Next, disk accretion, which occurs when matter falls onto a central object forming a rotating disk. This type of accretion is commonly observed in binary system, active galactic nuclei, and protoplanetary disk. Here in the disk accretion, the infalling matter spirals inwards due to the gravitational attraction of the central object and forms an accretion disk. The disk is heated up by friction and emits radiation in various wavelengths. Accretion theory is applicable to wide range of astrophysical objects. Next, we are interested in X-rays. So X-rays are electromagnetic radiation with shorter wavelengths than wavelengths of UV light with energy 10 to the power 2 eV to 10 to the power 5 eV. X-ray production requires highly energetic particles or very high temperature, about millions of degrees. In case of astrophysical X-rays, they are primarily generated during three processes. First one is thermal Bremsstrahlung emission. At very high temperature, about greater than 10 to the power 6 Kelvin, gases get ionized into electrons and positive ions. In that ionized media, when electron encounter with a positive ion, they mutually interact and lead to a net acceleration of lighter electron and occurs X-ray emission. So next one is synchrotron emission. So X-rays are generated when an ultra-relativistic electron spirals around magnetic field lines. Such fast-moving electrons with a range of velocities experience the electromagnetic Lorentz force and they get accelerated enough to emit high energetic radiation. Third one is inverse Compton emission. Here, ultra-relativistic electrons collide with low-energy photons to produce X-rays. So next, different relativistic accretors. So first is compact object. Compact object is divided into two parts, white dwarf and not white dwarf. So in cataclysmic variable, there is a white dwarf, and in case of not white dwarf, we get X-ray binaries. X-ray binaries are of two types, high mass X-ray binaries and low mass X-ray binaries. And high mass X-ray binaries have two subparts, pulsars with rotating neutron star, black hole candidate, and black hole candidate. In case of low mass X-ray binaries, we get burster with neutron star and black hole candidate. So next, there is a more powerful accretor. It's called active galactic nuclear. And active galactic nuclei is a galaxy's exceptionally bright central region dominated by light released by dust and gas falling into a black hole. So it has a luminosity of more than 10 to the power 44 arc per second. Actually, we are interested also in X-ray binaries. It is of two parts, low mass X-ray binaries and high mass X-ray binaries. In low mass X-ray binaries, we can see the accretion disk through which accretion occur, and there is a companion star which have a mass less than equal 1 solar mass that evolves and swells to red giants feeding into the compact objects. You can trace the old star formation history in low mass X-ray binaries. And in case of high mass X-ray binaries, accretion occurs through stellar wind. Here the companion star is a massive O or B type star, and you can trace recent star formation history in the high mass X-ray binary. So X-rays from black hole. Here is a companion star. So from the companion star, matter falls onto the accretion disk and to the this compact object. At this location, where the accreted matter falls is called hotspot. So intense X-ray emission is released from the inner region of the accretion disk where it falls onto the collapsed star. The X-rays come from the area around the compact companion where the infalling material is heated to very high temperature. So next, accretion disk corona models. So what is ADC? ADC is a hot optically thin cloud of electrons with temperature exceeding about 10 to the power 9 Kelvin. The hard component is generally thought to be originated in corona through Compton upscattering of the soft photons from the accretion disk. Despite decades of numerous studies, there are still no consensus on the detailed geometry of the corona. So here I am presenting four possible corona geometries. First one is Lampo's corona model. So this model assumes that the corona locates on the rotation axis of the black hole above a standard thin disk that extends to the ISCO, which may also correspond to the base of the Z. So next, sandwich corona model. This model proposes that the corona is the atmosphere above the inner part of an optically thick accretion disk. Next is a spherical corona model. So this model assumes corona is the inner hot flow that lies between the inner radius of the accretion disk and the black hole. Meaning that the accretion disk has to be truncated at certain radius. Next, toroidal corona model. So this model suggests the presence of a powerful magnetic field that circles around the disk like a torus, which is amplified by turbulence within the disk. Due to strong magnetic influences, the disk would be thicker for a given radius and accretion rate. So next, X-ray spectra. So the emission spectra of radiation exiting from the corona is markedly different from the spectrum of the radiation entering the corona. Since the number of times that the photon is scattered determines its energy as it exits the corona, Comptonized emission spectrum can be approximated by this power law. And
sorry, Ashish, you have 2 more minutes.
Okay. So X-rays are often displayed as photons received per unit time, per unit detector area, and per photons energy. So next, stochastic variability. So stochastic variability are of 2 types. We can get broadband noise and quasi-periodic oscillation. So quasi-periodic oscillations are created by stochastic process. Therefore, they are not strictly periodic, and as a result, they show up in a power density spectrum as a broader peak that covers a range of frequencies. And in case of broadband noise, they cover wide range of frequencies, and their characteristics depend on accretion rate. And the next, measuring of black hole spin. So here you can see the measuring of black hole spin at it actually revealed from a 6.4 keV X-ray emission line caused by fluorescence of cold iron atom. Here in the top panel, you can see the 2 to 10 keV emission spectrum, which follows power law as already stated in previous slide. In bottom panel, you can see the most prominent 6.4 keV iron K line. This iron line first discovered in several Asians by Ginga mission. Later by a Japanese satellite called ASCA demonstrated broadening of this line, indicating speed of 0.2 c. However, broadening was found to be asymmetric due to gravitational redshift. So the fluorescent iron lines from material near the black hole would appear at lower energies than fluorescence line from material further away, make line profile asymmetric. So 6.4 keV lines allows us to measure black hole spin because the last stable orbit of a spinning black hole is smaller than for a non-rotating one. So with this, I want to conclude my presentation with 5 concluding remarks. So I have touched how relativistic accretors come into picture, different compact X-ray sources, how we get X radiations, X-ray spectra, and related models, black hole spin measurement. So these are my references. Thank you.
Thank you, Ashish, very much for the nice talk. So, do we have any questions here in the list of participants? Please unmute yourself and go ahead. Okay, if not, Ashish, can I ask a small question in regarding your plot in slide 11? Slide 11. So in the top plot, so what kind of power law spectrum is this? So it doesn't look like a linear power law. So
it is actually this power law.
Okay. So this is still linear, right? But the plot, the fit that you make to the plot, it doesn't look so linear. So what is the gamma? What is the typical values of gamma?
Actually, this I have not seen this gamma value. Probably 0 to 1.
Okay. So and what? So what do you? So this what kind of stochastic process do you associate this to?
Stochastic. Actually, in this process, we can see the inverse Compton scattering in the accretion. In X-ray binaries, we can get the quasi-periodic oscillation and broadband noise. So actually, completely we cannot get the information about stochastic processes occurring in the QPO exactly.
Okay. Okay. Thank you so much for the nice talk. Yeah. So the next speaker is, let me just check, is Lisa Devi. So are you here, Lisa Devi?
Yes. Am I audible?
Yeah. So you are slightly feeble, so maybe you can increase your volume and go ahead. I can hear you, but I think
Is it now?
slightly. Yes. I can hear you fine. So maybe you can. Your screen is still sharing. So yeah. I can see your screen now.
Is it visible?
Yes, please go ahead.
Okay. Hello everyone. I am Lisa Devi. I'm from Department of Applied Sciences, Tezpur University. Today I'm going to present a review on accretion disk outburst and stability analysis. So these are the outlines of my presentation. In introduction, I'm going to talk about accretion disk outbursts, like what are accretion disk outbursts and how they occur. So accretion disk outbursts are recurring events observed in various astrophysical systems like X-ray binaries and cataclysmic variables. These outbursts are characterized by sudden increase in luminosity. Various instabilities in the accretion disk produces this kinds of outbursts. To study this kind of outburst, we need time-dependent models, which help us to incorporate the time evolution of the disk. In figure 1, it is a pictorial representation of a recurrent nova outburst. So this figure 2 is the X-ray light curve of black hole X-ray binary A062000 observed in 3rd of August 1975. Here, the X-ray intensity is given in multiples of Crab nebula intensity, and the time axis is given days, since Julian days. Here the outburst, first the outburst is a rapidly rise shape and a slower exponential decay. So we can say that in various outbursts, the shape of the light curves varies, and the recurrence time or the shape of the outbursts are not strictly periodic. They varies from burst to burst. Following the outburst, there is a period of quiescence, and before another outburst occurs. So these outbursts are the results of various instabilities in accretion disk. These instabilities again depends on various time scale, which we can characterize as characteristics time scale. There are 3 types of characteristics time scale: dynamical time scale, thermal time scale, and viscous time scale. Dynamical time scale is the shortest time scale. It is the amount of time that these particles require to move around the accreting object in a single Kepler orbit. And the thermal time scale is the amount of time required for viscous dissipation to develop the disk annulus thermal energy content. And the viscous time scale is the longest time scale. It is the time takes by the disk fluid to move substantially in a radial direction. So the hierarchy of this time scale leads to different kinds of instabilities in the accretion disk, which we will discuss in the next slide. So the thermal instability occurs when the rate of heating is out of step with the rate of cooling. In this non-equilibrium situation, the disk is subjected to thermal instability, and the growth time of this instability is called as thermal timescale. Similarly, if we introduce a perturbation adding a small mass to a disk annulus, if the perturbation grows in mass, then we say that the disk is viscously unstable. And if the perturbation doesn't grow and come back to its original position, then we say that the disk is viscously stable. Here, the condition, equation 1 gives the stability condition for a disk to viscously stable, or otherwise, disk is said to be viscously unstable. So in the thermodynamic cycle instability gives us the idea about thermoviscous instability. Here, the partial ionization process of hydrogen due to thermal instability results in sudden luminosity variation in the disk. Here, hydrogen is mainly in consideration because hydrogen is the most abundant element in the accretion disk. So this mechanism causes the outburst of dwarf novae and X-ray transients. To explain the thermolimit cycle instability, we have the S-shaped curve. This S-shaped curve reflects the essence of thermal viscous instability. In the high state, this is H2 state, the hydrogen is fully ionized, but in low state, H1 state, the hydrogen is in neutral. They are stable branches, thermally and viscously stable branches, but in the middle state, hydrogen is partially ionized. This state is unstable against thermal and viscous instabilities. So this is the schematic thermal equilibrium curve in dwarf novae disk. Now, if we consider a disk ring where m dot in is the mass inflow rate to a disk ring and m dot out is the mass outflow rate from the disk ring, then we have in H1 state, the mass inflow rate is greater than mass outflow rate, and the surface density profile as well as the disk mass will increase until a maximum density sigma A is reached. Here, the sigma A is the maximum density. After reaching the maximum density, this ring jumps to H2 state. Here, the H2 state, in H2 state, the mass inflow rate is less than mass outflow rate, and as a result, the mass this mass decreases, and this continues until a minimum surface density sigma B is reached. Then from H2 state, this jumps to H1 state. So the rapid oscillation between this H2 state and H1 state occurs. The rapid oscillation between this H2 state and H1 state results various instabilities in the accretion rate and results to outburst. So the concept of local and global instability is now into consideration for study the instability in accretion disk. An unstable disk which cycles between a hot high viscosity state and a cool low viscosity state can be explained by the limit cycle evolution, which we have discussed earlier, and it gives rise to dwarf nova and soft X-ray transients outbursts. So the limit cycle evolution. Yes?
Excuse me, you have 2 more minutes.
Oh yeah. So the limit cycle evolution takes place if this ring is unstable, but if the remaining portion of the disk is stable, then here comes the concept of global instability. So it is possible for an accretion disk that is thermally, viscously, and locally unstable to shift and become globally unstable. So there are 4 main phases of a global limit cycle. Here we have considered the idealized light curve of a dwarf nova. This idealized light curve of a dwarf nova has 4 phases: the rise to outburst, transition into outburst, and fusion. So each phase has a corresponding characteristics time scale. The rise and decline phases are very short, and the outburst time is intermediate, and the fusion time is long. So this is in a quasi state when there is a very high mass accretion rate throughout, and the surface density profile increases here, and this becomes luminous, hot, and highly viscous, and this is known as the outburst state of the disk. In the outburst state, the disk loses mass and the surface density profile decreases, and the outburst phase comes to an end. After some, and the disk ring goes makes a transition to quiescent state. In quiescent, state, the mass accretion, disk ring starts accumulate mass, and therefore the surface density profile increases. And at quiescent state, at some point when surface density is in excess to some critical surface density, then the disk undergo a hot state, initiating a heating wave which spreads quickly within the whole disk. Again, results in sudden increase in luminosity and giving rise to outbursts. And this cycles repeats until the next burst occurs. So in conclusion, the study of accretion disk outburst and stability analysis techniques is important to understand the dynamic processes occurring in astrophysical systems. And by examining the stability of accretion disks under various conditions, we can unreveal the underlying physical processes that govern their evolution and the relation between the stable and unstable regions. Moreover, the stability analysis approaches is very important in anticipating the behavior of accretion disks and analyzing how responsive they are to shocks. So these are the references. Thank you.
Thank you, Lisa. Do we have any questions from the participants here?
No.
Yes, Ashish, please go ahead.
Yes, I have one question.
Yes.
How the viscous dissipation is taken care of in this case?
Yes, viscous dissipation is taken care of in this term.
Yeah, I did not get it completely. Like, is it any any schemes are considered, or like is it already?
No, it is the standard accretion disk viscous dissipation, which is the rate at the rate at which the mechanical energy is converted to thermal energy. This is the viscous dissipation we have taken into account.
Yeah, for that, do you have any parameterization for that one? Because it seems to be not like a.
Yes, we have a few
linear
equations. Yes, we have the equation. I have not included here where the viscous dissipation rate is included. I have only considered this equation 1. So we have equation where viscous dissipation change with respect to time of viscous dissipation is taken into account.
Okay, thank you.
Thank you.
Okay, I think we can stop here. Thank you, Lisa. Let's move ahead to the next speaker. So the next speaker is Mami Deka. Are you here, Mommy?
Yes.
Yeah, so maybe you can share your screen and go ahead.
Is my screen visible?
Yes, I can see your screen.
Thank you.
Yeah, please go ahead.
Hello everyone. I am Movideka, a PhD student from Cotton University. First of all, I'd like to thank the organizer for giving me this opportunity to share some of our recent findings. In this presentation, I am going to mainly present on a new approach which we have used to study the structural parameters of galactic bulbs using Rayleigh stars. This is artist's impression of our Milky Way. The first picture is the fashion view of our Milky Way, and the second picture shows the Asian view of our Milky Way. And what is the galactic pulse? Okay, the galactic pulse is the central region of our galaxy that forms a spheroidal cloud of stars with a triaxial structure, and it extends a few kiloparsecs above and below the sky plan of the sky. What makes the galactic pulse truly fascinating is its rich stellar composition, housing a diverse mix of both population 1 and population 2 stars. And yet, despite its cosmic significance, it is the least understood part of our galaxy. Why is it so difficult to study the pulse? Well, because it is shrouded with stellar clouds and it is enveloped with a substantial amount of gas and dust. However, the good news is that in recent years, our technology has got much better, and we have figured out ways how to look through all that dust and gas. And astronomers have made some exciting progress in this field. Okay, now the main questions are, when we talk about the central region of any galaxies, we often encounter the term pulses. And these bulges can take two distinct forms, spheroidal, often referred as classical bulges, and bar-like structure known as pseudo-bulges. The canonical understanding of how these two types of bulges form is very intriguing. Classical bulges are believed to have originated through early mergers. In contrast, pseudo-bulges or bar-like structure are thought to evolve differently, emerging from a process known as buckling instability over extended time scale. Recent studies about the galactic bulge have revealed that Milky Way bulge has dynamic characteristics of pseudo-bulges. However, when we examine the age and chemical composition of this central region, it tells us a different story. The data suggests that the pseudo-bulge-like structure has formed very rapidly in a manner consistent with classical bulges. This intriguing contradiction challenges our current understanding of bulge formation in galaxies. It raises questions about the mechanism at play in Milky Way's central region, how they might differ from the typical expectation associated with pseudo-bulge formation. Okay, so far the galactic structure of the galactic bulge has been studied using several populations, mostly population 2 stars. These are R&D stars, Myras, Type Cepheus, and Red Clam star. Most of them are radially pulsating star, and they follow a period luminosity relation, which makes them excellent distance candle. So once we have individual distance to these stars, we can then trace out their distribution in their host region. In this presentation, in this work, we have used RLD stars, and we have developed a new approach to study the galactic bulge structure. Okay, for the data, we have taken the light bulbs of RLDs from OGLE database. They have recently released around 78,000 light bulbs of galactic RLD stars. And what are RLD stars? They are low mass pulsating stars, and their pulsation period ranges from 0.4 to 1 days. And they pulsate both single and multi modes. But for our interest, for us, the single mode RLD stars are more useful, and they lie in this region in between these two red lines. This is known as the instability strip. Okay, here some example light curves of different variable stars, and this one is the one is for RLD stars. Okay, when we collect the data from this OGLE survey, the data is not free from foreground and background star, and we have used this diagram to remove this foreground and background stars. And this is the equations which we have used to estimate the distance for these stars. I will not go much into details due to time constraint. And we have got this distance distribution, and from which we have got an approximate distance from our sun to the center of to the galactic center. And this will go as prior for the method we have developed here. And first we have transform this distance into Cartesian coordinates, and they look like this in the Cartesian plans. And okay, now we'll move to the approach we have developed. First of all, for our method, we need density models, and we have used three density models: exponential function, Bessel function, and Gaussian function. And these density models will go as input to the likelihood function, and the likelihood function is central to our methodology. And what do? We first
Mommy, you have
use
2 more minutes. Sorry.
Okay, this yeah, I'll finish it. This likelihood function we first optimize using optimizer, and this is known as here we have used this LBFGS method, and this will give us an initial estimate of these parameters, and further we refine this parameter and obtain the uncertainties based on this MCMC method. And this is the posterior distribution. This is one example of the posterior distribution we have obtained from our work. And as we have choosing three density models, here we have to find one best fit model. For this, we have used these two criteria to find the best fit model. And the best fit model, these two criteria prefers this exponential model, which is given this parameter of the galactic bulge. The first one, R0, is the distance to the galactic center, and it is quite in good agreement with previous studies. And then theta is the angle between the galactic plane to the line joining the sun with the galactic center. And this theta varies depending on the metallicity of these RLED populations. And lastly, we have looked into the axis parameter. This gives us information about whether they trace the bar-like structure or spheroidal structure. As we can see that the B by A and C by A ratio is almost similar. So this distribution of RLEDs, they trace the spheroidal structure of our galaxy. Okay, this is my summary. Thank you.
Thank you very much, Mommy. Do we have any questions from the participants here?
Yes, I have one small question. Thank you for the presentation. Just I wanted to know that how you have considered the axis symmetricity of the Milky Way in this case, because you were going dipping down into the central region, so that will be, I think, more prominent in that case. And also
yes.
about the X-shaped bar you have mentioned. So have you encountered anything like that using your approach?
Yes, X-shaped structure is mainly revealed by the metal-rich stars, and as RLE stars are metal poor, we were not expecting X-shaped structure. We have also looked into that, but we have not got any evidence of X-shaped structure with RLE star. And for axisymmetric, we have considered here only this spheroidal structure. We have not looked into that yet, but this is a very good question. We'll really like to look into it.
Yeah, okay. And also some in some recent galaxies models, there are like some pulseless evolutions are also considered. So as you have already mentioned that like metal poor cases, so do you think that there could be some effect of something like that, or is it just like a general assumption that the already pulse is very well defined for our galaxy? What do you think?
This bar or bulge-like structure above. Am I getting it correct?
Sorry?
Are you asking about like our Milky Way, the central region of our Milky Way is a bar-like structure, for a bar-like structure or bulge-like structure?
No, I'm saying that in some galaxy models, not related to Milky Way, but some nearby satellite galaxies like dwarf galaxies, and they have also proposed some bulge-less models, like without bulge also the galaxy is evolving. So my question was that in our Milky Way, mostly in generally we consider it like a well-defined bulge in that case. So as you have mentioned, like a metal core cases of the stars. So do you think that something like this type of possibilities may occur also, or is it well?
I think metal core stars follow quite a thick distribution in comparison to metal-rich stars. So for our galaxy, it's quite evident. We have a central bulge region. From this,
Do you have any more questions from the audience? Thank you, Devashish. Maybe I can follow up with one quick question, although I don't think we have much time. So, Mami, can you just let me know once again? So you were using the distance distribution as the prior for your Bayesian model, right?
yes.
So so are you sampling over all the other parameters, and that is the only prior that you're using? How many number of degrees of freedom do you have in your model? How many parameters are there?
In this models, we have 5 parameters, this distance from galactic center to our sun, and then we have used the excess ratios and the inclination angle, and those are based on previous literature. This is like informative prior.
Okay.
We are using informative prior, and the data we are using this XYZ from this RRD distance distribution.
Okay. So okay, and when you are using the 3 different models which you used, so and then you are using AIC, BIC as the criteria. So does both the AIC and BIC criteria give consistent model selection?
Yes, it is.
Okay. Thank you so much.
Thank you.
Thank you, Mami, for the nice talk. Let's move ahead with the next speaker. So the next speaker is Meshwa Garnet Gurba. If you're here,
yes, I'm here.
Yeah, can you please share your screen and?
Okay, sir.
Yes, I can see your screen. Please go ahead. Yeah.
So good afternoon, everyone. My name is Vishal Garnet Gurba. I'm a research scholar under the supervision of Dr. Wisdom Ahmed. So the title, the paper presentation that I'm going to give is on Maxwell equation in spherically symmetric black holes with phantom global monopoles. These are the outlines of today's presentation. First of all, let us know what is Maxwell. As you all know, Maxwell equations are a set of 4 fundamental equations that form the foundation of classical electromagnetism, describing how electric and magnetic fields interact and propagate. These are the 4 Maxwell equations. They are the Gauss law of electricity, Gauss law of magnetism, Faraday's law of induction, and Ampere's law. So Maxwell equation in flat spacetime and curved spacetime. Maxwell equation in flat spacetime, it describes electromagnetic phenomena without considering gravitational effect, while Maxwell equation in curved spacetime, it accounts for the curvature of spacetime due to the gravity, modifying the equations to fit within the framework of general relativity. In flat spacetime, Maxwell equations take a concise form in spherically terms of electric field E and magnetic field B vectors, charge ρ and currents J. So Maxwell equation in curved spacetime are expressed by using tensor notation and involve the electromagnetic field tensor of mu, the electromagnetic covariant derivative del mu, and the electromagnetic tensor J mu. So black hole, as you know, black hole is a region in space where the gravitational pull is so strong that nothing, not even light, can escape from it. This boundary beyond which nothing can escape is called the event horizon. So in our study, we'll do a spherically symmetric black hole, that is a type of black hole that is perfectly spherical in shape and has the same properties in every direction. This means that the black hole looks the same from any angle with no variation in its appearance or behavior when observed from different directions. So the most well-known example of a spherically symmetric black hole is the Schwarzschild black hole, which is a solution of Einstein equation of general relativity. Phantom global monopoles. Phantom global monopoles are a combination of global monopoles and phantom fields. They are the theoretical objects in cosmology and high energy physics that arise in certain models of scalar field theory with a global symmetry. These arise when a scalar field with a global symmetry undergoes spontaneous symmetry breaking, resulting in a topological defect. Here, topological defects are specific types of structural irregularities or discontinuity that can occur in various physical systems, including condensed matter physics, cosmology, and even certain types of material. These defects are characterized by unique topological properties that can have important consequence for the behavior of physical fields and particles in their vicinity. So example of these topological defects are cosmic string, domain walls, monopole, and vortices. So the importance of the study. Maxwell equation in this context of black holes is influenced by phantom fields and global monopole. It's important for several reasons. That is theoretical advancement in electromagnetism and general relativity. That is, it combines Maxwell equation with the space-time geometry of black holes and phantom global monopoles, provide a unified framework to study the interplay between electromagnetism and gravity. It also explores the objects like it helps to explore the consequence of exotic forms of matter and energy, which may have negative energy density and unusual gravitational properties. Studying these interactions, it will help us to understand the potential modification to black hole properties when exotic fields and topological defects are present. Implication for astrophysics and cosmology, the behavior of this electromagnetic field in the presence of phantom global monopole could also provide insight to the gravitational effect that influence the formation and evolution of cosmic structure. It can also identify the unique observational signature, such as specific radiation patterns or gravitational lensing effect, and can also help in the detection and study of black holes that is influenced by phantom fields. It also probing quantum theories, that is, when solving Maxwell equation in this context, it allows testing prediction from these advanced theory, potentially leading to new discoveries or constraint on theoretical model. It also developed numerical and analytical techniques that is contributing to broader scientific and technological progress. Now, coming to the objective. In this objective, a main objective is to study the electromagnetic field behavior in the context of spherically symmetric black holes with phantom global monopole. In particular, when there is a single different topological defect curvature of space-time, we get exact formulation for the Maxwell equation and the electromagnetic field tensor in the framework of global monopole spacetime by means of thorough investigation. Well, crucially, we will show how the addition of this topological defect, such as the phantom parameter, causes changes in the electric and magnetic field and produce electromagnetic waves that are not the same as those seen in Minkowski's flat space. Within this,
sorry, Meshwa, you have 2 more minutes.
Okay, sir. Within this context, our study attempts to provide light on the intricate interactions of electromagnetic field, topological defect, and gravitational effects in curved spacetime. So, coming to the methodology, here we analyze the Maxwell equation in this black hole with phantom global monopole. The line element is given by this equation 1, where m is the mass, eta is the energy scale of symmetry breaking, and psi is the term describing kinetic energy. If psi is equal to 1, it represents an ordinary global monopole. If psi equal to -1, it represents an the phantom global monopole. Here, using this metric tensor G mu nu and eta AB, and selecting the general co-moving observer velocity U mu as h mu nu, the coordinate tetra is given as follow in equation 2. So in order to convert into spherical coordinates, we select Q0 equal T, Q1 equal R, Q2 equal theta, Q3 equal phi, so that E1 equal ER, E2 equal E theta, and E3 equal E phi. So the electromagnetic field tensor FOI in non-coordinate basis is given by this equation 3. So here, if we, so electromagnetic field tensor F mu nu in the background of this spherically symmetric black hole, we use this above equation in coordinate basis. That is, we use this equation 3 and 2. In this equation, we got this equation 4 and 5, which is the contravariant form and the covariant form. So, and after that, we derive the Maxwell equation. That is, we substitute the equation 4 in this equation. That is 1 by root minus g del partial derivative mu root minus g f mu nu equal g mu, where g is the determinant of the metric tensor g mu nu minus this square root g root minus g is the absolute value of the determinant of the metric tensor. So if we substitute that equation 4 in this equation, we will get a set of vacuum electromagnetic field equation that is given in equation 6, 7, 8, 9. Here, nu is equal to 0, 1, 2, 3 respectively, and Fr is equal to this equation. After that, we substitute equation 5 in this equation, that is this electromagnetic field tensor. We get a set of source-free equation, which is given by this equation 10, 11, 12, and 13. So from equation 6 to equation 13 express a first order differential equation governing electric and magnetic field in both spatial and temporal coordinates within the context of a global phantom global monopole. It is noteworthy that the electromagnetic field tensor and the Maxwell vacuum equation are influenced by the presence of this phantom global monopole characterized by the parameter psi.
So, sorry, Meshwa, the time is running. So, can you please wrap up?
Okay, I'm complete.
Yeah.
Okay.
Sorry.
So in this work, we have investigated electromagnetic wave equation in the topological flaws framework in the vacuum of free space. We have derived Maxwell equation for a phantom global motor as I've shown in equation 6 to 13. Solution to those differential equation we use by the approach of separation variable methodology. Interestingly, we discovered that the parameter psi affect both the electric and magnetic field. And from that, it is clear from a comparison with Minkowski space that this parameter introduced alteration to the electric fields, providing fresh information about how topological flaws affect electromagnetic wave behavior. So here I conclude my presentation. These are my references. Thank you.
Thank you, Meshwa. So maybe a very quick question if we have from people, from the participants. Okay, if not, maybe we can proceed and people can ask Meshwa later offline. Thank you so much, Meshwa, for the talk.
Thank you so much, sir.
Yeah. Maybe let's proceed. So the next talk is by Arvind Pradhan. If you are here, can you please share your screen? Are you here? Yeah. Okay, I can see.
Yeah, I'm sharing my
screen. Yeah, please go ahead.
So is my screen visible?
Yes. Yeah, please go ahead.
I hope my audio is clear.
Yes.
Yeah. Okay. So hello everyone. I'm Arvind Pradhan. I'm a PhD scholar in Department of Applied Sciences, and I work under the supervision of Dr. Biplab Sarkar. So the title of my talk is Spectral and Temporal Properties of GX13+1 observed with astroset. So these are the outlines of the talk. Introduction, here I will briefly give an idea of X-ray binary. Then I will talk about the neutron star X-ray binary. Then I will talk about the motivation behind this work. And I will give a preliminary results, as the work which I'm going to present is an ongoing work, and I will conclude the talk. So now talking about X-ray binaries, this system are a binary or a two-star system consisting of a compact object, which can either be a neutron star or a black hole, accreting a mass from its companion, which is usually a main sequence star. The figure 1 gives an artistic impression of an X-ray binary, in which this represents the compact object, and so in the process of accretion from this companion star, there is a formation of accretion disk which prominently emits in X-ray. So depending on the mass of this companion star, they are further categorized as low mass X-ray binary and a high mass X-ray binary. When the mass of a companion is less than 1 or less than or equal to 1 solar mass, they are referred to be as a low mass X-ray binary. And if the mass of the companion is greater than or equal to 10 solar mass, they are referred to as a high mass X-ray binary. So beside that, depending on the companion star present, compact object present, they are further categorized as black hole X-ray binary and neutron star X-ray binary. Since GX13+1 is a neutron star X-ray binary, I will be briefly discussing about neutron star X-ray binaries. So neutron star X-ray binaries, it is found that in the plot, so-called hardness intensity diagram, which is a plot of a hardness to the intensity, that these neutron star system are of a two type, namely atoll source, as shown in the figure 2 left side, this one, and the jet track source as shown in this plot. So as you can see that in the left side, this is a HID of a atoll neutron star source. So in this HID, it is further divided into an Iceland state and a banana state. And in this jet type track source, it is further categorized as a horizontal branch, normal branch, and a flaring branch. So now the motivation behind this work is to perform the spectral and timing analysis, and we will be computing this lag and RMS of the variabilities observed in the PDS. And we will be employing the method which is proposed by this Gerg et al. 2020 in order to investigate this energy-dependent nature of this variability. So I'll be briefly discussing about Gerg et al. So as per this Gerg et al., it gives an idea about the radiative mechanism responsible for the production of this variability in the system. So this model is based on the assumption that there is some truncated disk at some radius away from ISCO, and there is some hot electron plasma in between this ISCO and the truncated disk. So the soft shift photon from the truncated disk, they get Compton upscattered. As a result, the hard photons will be produced. So in the process of this production of this X-rays, there is some variation in the physical perimeter, leading to a production of these variabilities in the system. So as per, so we will be trying to incorporate this model to understand the variability seen in this system. So now talking about preliminary results. So we will be using the data of an AstroSat mission. So we will be using the detectors like LexPC and SXT. So this is the light curve of LexPC and SXT. LexPC, which works in 3 to 80 keV, whereas SXT works in 0.3 to 8 keV. And this is the color diagram of the GX13+1. So this GX13+1 is one of the interesting source, as initially it was thought to be one of the bright atoll source, but later on it was found that with the help of this HID and CCT, it was found that they are a jet type source. As you can see in CCT, that it is clearly seen that the source is normal and a flaring branch. And now talking about here, it's a HID of a GX13+1. So we will be performing this flux spectroscopy. So using this technique, we have segmented this HID into 4 sets, set 1, set 2, and set 3, and set 4. And we have performed separate spectral and timing analysis for this all sets. So this is the spectral analysis of the associate data of SXT and LexPC. So we have fitted this spectra with the help with the model of constant, which is for the calibration constant of two detectors, and TBAPS for the interstellar absorption, THCOM for accounting the thermal quantization, and this black body for the B body red for black body, and plus Gaussian, as we have seen some Gaussian feature in the spectra. So yeah, so this is the timing analysis where we have fitted the PTS with a multiple Lorentzian in an energy range of 3 to 80 keV, and we saw these prominent humps in all these sets, and we extracted the lag and RMS spectra for these humps, and for so these spectra were this one is from set 1 and this one is for set 2. Similarly, this PDS is of set 1 and this PDS of set 2. So similarly, we extracted or we plotted the RMS and time-lag spectra for those set 1 and set 2, and we model it with the help of a Gerg technique, and we found that the model in which there is a variation of fractional scattering along with the heating rate and the inner disk temperature with some time delay, we were able to fit this lag and RMS, and and so the heading towards conclusion, so far we conclude that through spectral analysis we found the radius of a neutron star in the range of 22 to 38 kilometer, which was quite consistent with as per the Savadra et al. As in their paper, they said the mass of the neutron star is more than 16 kilometer. The value of NH and gamma was also consistent with this Giridharan et al., as they have also used this associate data. So far from our analysis, we saw that the variation of this spectral, as I said, the fractional scattering, along with the variation of this inner disk temperature, the variation in the heating rate, with some time lag, perfectly fitted this RMS and time lag spectra. So from our analysis, our analysis reveals that this variation responsible for production of those humps in the PTS was initially introduced as a variation in a heating rate, then it followed by the change in the inner disk temperature, as we saw the negative phase in this negative value of phase in our analysis. So these are the references. Thank you. Hello.
Thank you very much, Arvind. Thank you for keeping things in time. Do we have any question from the audience?
Yes, I have one small question.
Yes, go ahead.
Yeah.
Thank you for the nice talk. Just I wanted to know that how this time lag is calculated. I did not catch that point.
So they are basically different subroutines we play. So what we do is, as you can see here, that for different energy ranges. Hello, is there?
Yes.
Yeah. So we make these different energy ranges. Okay. So we check for different energy bands. So where this there is at different energy ranges, where there is a lagging at that energy range.
Okay, so the time lag is in terms of energy you are calculating.
Yes.
Okay, thank you.
Okay, so do we have any more questions? If not, thank you very much, Arvind. Let us move ahead with the next speaker. The next speaker is Shri Bhattacharji. Please, if you are here, can you please share your screen and go ahead? Shri Bhattacharji.
Yeah, hello. Can you hear me?
Yes, I can hear you. You're slightly
Yeah.
feeble, so maybe can you
Okay.
increase your volume?
So, is it okay now? Hello?
Yes, please go ahead.
It's fine. Okay, thank you. So, hello everyone. I'm Shri Bhattacharjee from the Department of Applied Sciences, Tezpur University. So, working under the supervision of Dr. Biplav Sharkar. So, I'm going to talk about today about this presentation entitled Spectrotemporal Study of the Atoll Source GX9+9 observed with AstroSat. So, the contributors for this work is Dr. Biplav Sharkar from Tezpur University and Arvind Pradhan from TU. So, this is the brief outline of my presentation that I'm going to talk about. So, this is about the X-ray binaries, and as of now, we have already gotten a brief idea about what the X-ray binaries are. This is an artistic impression which is showing the companion and the compact object and the mass accretion flow and forming the accretion disk around the compact object. So I hope I don't have to more dig in about this. So the source we have used for our work is GX9+9, which is a neutron star low mass X-ray binary. And my previous speaker has already mentioned nicely about the types of the neutron star X-ray binaries, which can be a ZRAC source or can be atoll source. So since this type of this source presses a C-like structure in the HID diagram, so these source belong to the atoll type sources. So these are the few characteristics of the source. Like this was discovered in 1967, and it mainly observed in the bright source state. And Herzen-Ur 1988 reported the orbital period of the source to be 4.19 R. So let us come to the motivation for our work. So in this work, we will utilize the broadband energy coverage of AstroSat, which by combining the two instruments of AstroSat, that is the LAX-PC, which works in the hard energy X-ray range, and SXT, which works in the soft energy X-ray range. And we will combine these two instruments, and we will perform the spectral evolution to understand the evolution of the source by using the method flux resolve spectroscopy. So in which we will differentiate or segment the HID into different flux levels and will incorporate the spectral and timing analysis in each of the segments separately. So from the timing analysis, we also aim to understand the radiative origin of the observed variability of the source. So this is the observation we have used. So for this source, AstroSat has only one observation. So we have used that observation, and from that observation, we have used the LAX-PC 60 simultaneous data for the spectral analysis. And for timing analysis, since SXT is not very good in the timing, SXT does not have very good timing capabilities, but LAX-PC has very high timing resolution of in the order of microsecond. So we will be using the LAX-PC data for the timing analysis. So this is showing the AstroSat light curve. The upper panel is showing the LAX-PC light curve, and the middle panel is showing the SXT light curve, and the bottom panel is showing the light curve of the source combining the AstroSat and SXT, combining the AstroSat and SXT data where both of the instruments were operational. So we will use this simultaneous data for the spectral evolution, but for the timing analysis we will use the LAX-PC data. So this is a very brief literature review from the we have collected from the earlier studies. Like various models have been used to describe the spectrum for this source, like the power law, the disk BB, and the B body, and the Gogoi, Sulfur, and Gilfanov 2007, and also IDEA 2020 have used RXT data to understand the spectrum of the source, and this AstroSat data has been previously used by Chatterjee et al. 2023, and they have reported some of the spectropolarimetric study of the source. So let us jump to the spectral analysis for the source. So this is the hardness intensity diagram. So the y-axis represents the hardness ratio, which is the X-ray photon count ratio in the energy range of 6 to 20 keV over 3 to 6 keV, and the x-axis is the total intensity or the total counts in the whole energy range of 3 to 20 keV. So for the flux resolved spectroscopy, we have segmented the HID into the, as represented by 3 different colors, into 3 flux levels: flux level 1, 2, and 3. So in the 3 flux level, we have performed the spectral analysis, and after using various models, we have obtained that the model which combines the thermal componentization component with the multicolor black body component, it gives the best fit spectrum for this observation. So this is a representative best fit spectrum of this source for which is showing the best fit spectrum for the flux level 3. This is the list of the best fit parameters we have obtained, and from the TBAS, the interstellar observation, we have obtained the NH value, and the thermal componentization model component provide us with the electron temperature and the fractional scattering value, and the disk PV we have from the disk PV component we have obtained the inner disk temperature and the disk normalization value, from which we are able to calculate the inner disk radius of the source. So let us come to the timing analysis. So we know that TDS is a good way to detect the variability of the source. So there are mainly 2 types of variabilities which are mainly seen in the X-ray binaries, that are the quasi-periodic observation, quasi-periodic variabilities, and the broadband noise variabilities. So here we have obtained a broadband noise variability at around 0.07 hertz, and now we will discuss investigate the origin of such kind of variability we obtain in this source. So to investigate that, we have incorporated the model of the model introduced by Garg et al. 2020, which is nicely explained by the previous speaker, Arvind Pradhan. So just quickly we can mention about that model. So this model basically uses the more relevant parameter or more physical parameters, like in place of the optical depth, like in place of the power law index, we use the optical depth, which is and both are interrelated by this equation, and in place of the electron temperature we use the heating rate of the corona, and so on. So this basically take into account the fact that the observed spectra incorporate all the changes in the spectral parameters, so that we can define the change in the spectra due to the change in the spectral components. So on using that this model, we have tried various combination of the spectral parameters, and which
Sorry, Sweet, you have 2 more minutes.
Sure, I'll wrap it up. So we have tried with various combination of the spectral parameters, which may lead to the prediction of the origin of such variability. So after trying with many combination, we have come to the conclusion that this kind of the variability we are obtaining here might be due to the change in the fractional scattering and the inner disk temperature, because it was more able to picturize or explain the model, since we are getting a good reduced square here on the combination of these 2 spectral parameters, whereas in the during the combination of the other components or the spectral components, we were getting very high reduced chi-square values. So here also we obtained that the heating rate is increasing with the increase of the X-ray flux, which also shows or explains that the source is transitioning to the harder state from the softer state. So this is the fitting we obtained, or the model using this model. The blue data points are the observed fractional RMS, whereas the black solid line is the model we have fitted with the data points, and we can see that it is able to explain the obtained fractional RMS variability. So let us just conclude this presentation here. So we have compared the spectral parameters with the earlier reported parameters, which are, and we can both are consistent with each other, and we also estimated the inner disk radius of the source, which is around 14 kilometer, and where we have considered the inclination of the source and the distance of the source to be 40 degree and 10 kpc respectively. And from the energy dependent timing properties, we estimated that the obtained variability is causing due to the change in the energies, temperature, and the fractional scattering fraction. So this is also a ongoing work, and a few analyses are yet to study, and we will include in the book chapter later. So these are the list of references, and thank you.
Thank you so much, Sri. So, do we have any questions from the audience here? If not, Shri, I have a very quick question in the last, in the conclusion slide. So you have quoted a number. So, the inner disk radius. So is this the first time you are quoting this, and have there been already some numbers quoted in the literature of the inner disk radius?
Yeah, there is in the literature, but this source is actually very not very well studied. So those are also not very well estimated. So we are trying to figure it out.
Okay, so what is the kind of error bar that you see in the ones in the literature? Is it worse? It is as
No,
good
it
as
is
yours,
not
or is it
worse.
slightly worse?
No, not worse. It is almost likely this only.
Okay.
Yeah.
Thank you very much for the nice talk. So do we have more questions from the audience? Yeah, if not, thank you very much, Shri. Let us go ahead with the next speaker. So the next speaker is Devashish Hazarika. So, Devashish, if you're here, can you please share your screen and go ahead?
Yes. Yeah. Is it visible?
Yes, I can see your screen. So, go ahead.
Okay. Okay. Good afternoon, everyone. Today I'm going to present an ongoing work titled Chemical Tagging and Abundances of Variable Stars in the S+. I'm a PhD student at the Institute of Astronomy and Planetary Sciences. And in this work, actually, let me put some background first. In the recent, after the success of Gaia satellite mission, and that we have observed that it is confirmed under the lambda CDM cosmology that the galaxies that we observe today are formed through the merger of some smaller structures. After the Gaia success, it is like in the recent years, the growing evidence of these interactions, and in particular, the accretion of the massive satellites has been found by studying the dynamics and the chemical patterns of the Milky Way stars. So when we talk about the evolution history of the Milky Way galaxy, then the decoding the past, as I have mentioned here, is challenging. But the stellar atmospheric chemical abundances that remain unaffected by the dynamical evolution of the stars, and that can serve as a valuable indicator to discern the origin of the specific populations, and also can tell us about the accretion processes. So this figure is showing like how complex the whole process is. So we need to have very good spectroscopic data for each and every stars to have the chemical accuracy in the chemical abundances, and to study this type of events. But when it comes to the variable stars, that especially with the short period variables, that is the period less than 1 day, that challenges the spectroscopy, because to obtain this type of chemical abundances, we need very high resolution spectroscopy. And for those short period variable, it's like a trade-off between the high resolution and the short-term pulsations. It's because for the high resolution spectroscopy, we need to have very high our long exposure timing, and sometimes it exceeds the pulsation period. That is one challenge. Then another challenge is like determining the center of mass radial velocity is like a challenging thing, because to plan the spectroscopy exactly at some certain phases, we need to have the correct information about the radial velocity, and that comes from the pulsation model. So this is like a conversion process. So we need to look for some alternate robust automatized method so that we can predict, or we can use these methods to obtain the chemical information for this type of variables. So in this study, actually, we aim to determine the chemical abundances of the variable stars using the S+ survey. This is an ongoing survey known as the Southern Photometric Local Universe Survey. It is a Chilean survey, and we are planning to use the data of the S+ for the work. And the another aim is to position them within the Milky Way components to decipher the origin and dynamical evolution of our galaxy. So let me give a brief introduction about the S+. So S+ is mapping the southern sky with an aim to cover around 9,300 square degree when the survey will be completed. And it has one main survey and other 4 sub-surveys. And the telescope is at the Cerro Tololo Inter-American Observatory at Chile. So the specialty of this S+ is that it has like 5 SDSS like wideband filters and 7 narrowband filters. And the specialty of the 7 narrowband filters is such that it is located at some prominent spectral lines, for example, calcium triplet, H-alpha, etc. So this narrowband informations can be translated to the prediction of the abundances for this type of stars. So in this study, actually, we utilize the data, that is the internal data release 4 of the S+, and translated these magnitudes to 66 color combinations, and that internal data release 4 actually covers 3,000 square degree and within a 5 years of time span. So in the initial stage, what we have done is that we have cross-matched that whole catalog with the known variables so far, and we obtained around 38,000 variables, but with some quality cuts, we obtained the final figure as a 35,000 variables. And for that database, we have some stars which are not variables, but which have very well observed spectrums in Lamost, Apogee, or the Gala. So we have utilized those data as a training set for the for a random forest regressor and a cost-sensitive neural network architecture, where we have put some 7 layers. With the first layer is just collecting the data, and another 5 layers are mapping them to in a non-linear complex way, and then the last layer is assigning them to the levels. And then with some post-sensitive learning algorithm were added to that neural network feed-forward models. And we have seen that the accuracy varies due to variation in the trained data resolution and the fiber sizes, because the spectroscopic data we are taking from the Lamost, Apogee, and Gala are having different resolution. One is having medium, another 2 are high resolution, and also they have very different fiber sizes. So that also gets reflected in the accuracy scores. And mostly we saw that the cost-sensitive neural network actually outperforms the random forest, and with an accuracy improvement up to greater than 6%, except some chemical abundances. And we, based on those predictions, we selected the predicted abundances which have like more than 80% confidence score. So this is the typical testing of the predicted versus the true values, which are mostly seen to be linear. And this is the distribution of the chemical abundances for those variable stars. And as in the first figure, we can see here that we have a range from very metal poor stars to the metal rich stars in this case. And we have here is the cut for the we can use actually these information for selecting different components of the galaxy. So similarly, we have the alpha element abundances here as well as the other abundances. So when we combine this together with different combination of the abundances, then we can see that the giant and supergiants and the dwarfs can be segregated from the figure of the effective temperature and the log G, and that also gets reflected in the other distributions. So we use this information to separate different components of the Milky Way based on the chemical abundances. And here we can see that there are a few halo stars. We have more stars in the thin and thick disk, and there are 27 very metal poor stars, which metal poor variables in this case. So in this, these are like some interesting stuff. So we are trying to study also the dynamics of these very metal poor stars, considering the axisymmetric Milky Way potential. But there are also some limitations of this type of potentials, because we could not incorporate the perturbations due to the spiral arms of the Milky Way in this case. But anyways, for this initial study, we have seen that for the eccentricity cases, we can see that the orbits are distributed from circular to the elliptical shape, and also we have the estimations for the perigee and apogee and the perigee. And similarly, we have tried to estimate the energy budgets and to see that if they have some accreted origins from the nearby satellite galaxies, or are they in situ formation in the Milky Way. So we are still working on this part and hope to complete in this work. And now concluding the summary and future work, it's like the spectroscopy for the short period variables are very challenging. So estimating the
Sorry,
chemical
Devashish, you have
abundances.
sorry, you have 2 more minutes, and I hope it seems like you're almost
Okay.
going to be finishing. Yeah.
Okay. So the summary also has the estimating the chemical abundances of 35,000 variables based on the colors. So that could be considered as a cheaper alternative to the spectroscopy, because now the big telescopes are coming, like LSST, ELT, or the JWST, where we cannot have like a very long durational observation of one star or one object. So in this case, the single epoch data could be considered and to estimate these type of things, and that could be a cheaper alternative to spectroscopy. And that we also have performed the chemical tagging of the variable stars in the Milky Way to look at it at various components, and the dynamics of the very metal poor variables are still undergoing. So with this, I conclude, and thank you.
Thank you so much, Devashish. Thank you for keeping things in time. So do we have any question from the audience here? If not, thank you very much, Devashish. I think we are running very much late according to schedule. So let us go ahead with the next talk. Thank you so much for your talk.
Yeah. Thank you.
So the next speaker is Jatsnasri Bora. If you're here, can you please?
Actually, hi, Jaikhomba. There will be a small change in the schedule. So,
Yeah.
Nasiba Parvin will be presenting now. So, it is rescheduled. Jatsnasri's talk is rescheduled. So, Nasiba Parvin, are you here?
Yes, am I audible?
But your voice is very, it's very, there's static or something in the background.
Okay. Is it clear now?
It's clear, but it's too loud actually. Lower
Okay.
the volume, then it will
Maybe you can decrease your volume.
Decrease the volume, and then you can, yeah. So now you share the screen.
Yeah, we can go.
Yeah, please. Jaikhomba, please carry on.
Yes, Nasiba, please go ahead.
Yeah.
So is my screen visible?
Yes,
Yes, it is
sure.
visible. Please go ahead.
So good afternoon, everyone. I am Nashiba Parvin from, Dibrugarh University. I just want to hide this, but
No, we can only see your presentation, so I think it's fine.
So yeah, the topic of my presentation is gravitational lensing features around a black hole covered in axionic hair. And basically what we know about gravitational lensing is that it is a very magnificent phenomenon where, magnificent phenomenon where image formation occurs due to the deflection of light as it passes through the curved space-time of gravitational field of massive objects. Here we can see it is an artist's rendition of the phenomenon of gravitational lensing. To observe the effects of gravitational lensing, astronomers mostly look for a relatively close massive object, often a cluster of galaxies, behind which a distant galaxy is located. And as we can see, due to the curved space-time of the gravitational field of this massive galaxy cluster, the light rays coming from the distant galaxy gets curved while reaching to the observer on Earth. And as a result, we are able to obtain Einstein rings, which are as we can see here, the curved ring is actually the distorted image of the distant galaxy, and the center is the galaxy cluster. So this phenomenon was first observed in 1919 during a solar eclipse by Arthur Eddington, Frank Dyson, and Charles Davidson, while they were trying to measure the bending of light coming from the stars in the highest star cluster around the sun. However, and it led to the first experimental verification of Einstein's general theory of relativity. However, the first experimentally lensed object was the double quasar, which was detected by Walsh, Carswell, and Wayman in 1979. And they suggested that it was a single object which appeared as a double image due to an intervening galaxy, which acted as a lens. But again, to obtain complete Einstein rings, it was to obtain such a appropriate combination of galaxy clusters and distant galaxies aligning properly to observers on Earth. It is the probability is very low. So we usually observe distorted galaxies in the form of arclets or partial Einstein rings. This image is one of the recent images captured by JWST and released by ESA in December 2023, where we can see the partial Einstein rings or arclets, and as the center we can obtain we can see the massive galaxy cluster. So in recent times, and not exactly recent times, the last few decades actually, there has been many issues and limitations have come to light, which led to the need for extensions of GR. So basically, modified theories of gravity were proposed to explain cosmic observations that cannot be described by GR, such as missing mass problem and missing mass problem, that is the dark matter problem, or the accelerated expansion issues. And various modified gravity theories have been introduced since then. Some of them are FR gravity, Horndeski gravity, DRGT gravity, Chern-Simons gravity, Einstein-Cosmonic gravity, FTB gravity, etc. And many more are there. So in this work, we consider the Chern-Simons gravity theory, which is a four-dimensional scalar tensor theory, and it is a well-known extension of the well-known extension of GR, where the Einstein-Hilbert action is extended by considering a Chern-Simons term, that is RCS, or which is also known as the Pontryagin intensity term, and which couples to the gravitational fields through a scalar degree of freedom, which in this case is the axion matter field. This dynamical scalar field plays a significant role in the black hole space-time that we will be considering. So, because by the process of scalarization, this scalar field, or that is the axion matter field, it backreacts on the geometry of the background metric and covers the black hole with hair. So in this case, the black hole is dressed in axionic hair. So as we can see, the axion matter is coupled to the Pontryagin density term, which is defined as given by equation 2. And this is a gravitational parity violating term. RCS is a parity violating term, and it is constructed by the contraction of the Riemann tensor to the dual Riemann tensor. And the axion matter coupling parameter, that is eta, is expressed in terms of the string Regis slope, which is alpha prime equal to ms inverse square. Ms is the string scale. Now, variation of equation 1, that is the action with respect to the metric tensor, gives us the equations of motion for the Chern-Simons gravity, which is given by equation 4, where T mu nu phi is the Einstein energy momentum tensor, which is given by equation 5, and C mu nu is the Cotton tensor, which is obtained by the variation of this scalar Pontryagin density term, coupling term, and and this term gives the contribution of the scalar Pontryagin density term to the Einstein field equations. So next we have the black hole that we have considered in the Chern-Simons theory, which is given by equation 7, where A and B are the metric coefficients, and WR is the off-diagonal correction term, which depicts the possible back reaction that has been imposed on the space-time black hole space-time by the scalar field. In the study of gravitational lensing, the basic feature we have first study is the deflection angle of light, which is an essential parameter. So in this study, to understand, to evaluate or compute the deflection angle of light, we consider the Gibbons-Warner method, which was introduced in 2008 by Gary Gibbons and Warner to study the gravitational lensing theory. They treated the light rays as spatial geodesics and geodesics of the optical metric, and used the Gauss-Bonnet theorem, which is mathematically expressed as given by equation 11, where k is the Gaussian curvature of this two-dimensional orientable surface T, and kg is the geodesic curvature, and theta a is the jump angles formed between the curves. So,
Nasiba, you have 2 more minutes. Sorry.
Yeah, sure. Yeah. Gibbons and Warner, they used this method for static spherically symmetric metrics, spacetimes, and it was further developed in 2016 by Ishihara and collaborators for stationary black hole spacetimes. So in this work, we will be using the method implemented by Ishihara. And here I'll give a brief geometrical configuration of how gravitational lensing works. So if this is a lens, that is a galaxy cluster, or in this case a black hole, and we have the source here. So instead of the light rays from the source, instead of moving in this plane, it gets bent due to the gravitational field of the black hole. So here beta is the angular separation between the source and the lens, and theta is the angular separation between the image and the lens, where the image will be formed in somewhere here, and alpha d is the deflection angle. So basically, we have considered here the L lens as the black hole as the lens, sorry, and R is the receiver on Earth, and S as the distance source object. So basically, light rays generated from the source in the get bent in the vicinity of the lens object, and it results in the angle of deflection. So using the Gauss-Bonnet theorem, the deflection angle can be represented as given by equation 12, where it is here this is the line integral of the geodesic curvature and surface integral of the Gaussian curvature. So for the black hole under consideration, we know that light rays follow null geodesics, so we can consider the metric can be written as given by equation 13, where the optical metric and the one form are represented by equation 14 and 15, and the Gaussian curvature, which is defined by equation 16, can be computed for the Chern-Simons black hole space-time as given by equation 17. Next, we have to compute the surface integral of the Gaussian Gaussian curvature. And for that purpose, we need to analyze the orbit equation in the equatorial plane. And as a result, we have two equations of two constants of motion, that is the energy of the photon and the angular momentum, and the ratio of which gives us the impact parameter, which is an essential parameter to study the deflection angle. The surface integral of the Gaussian curvature is obtained as given by equation 21, and for infinite distances it can be approximated as given by equation 22. And next we have the line integral of the Gaussian curvature. For the Gaussian geodesic curvature is obtained as equation given by this equation, and path integral is obtained as given by this equation 25. So for infinite distances, again, we can approximate the line integral of the geodesic curvature given by equation 26. And finally, we arrive at the deflection angle, which is given by equation 27. And in the limiting case, a equal to 0 and eta equal to 0, where a is the spinning parameter, we arrive at the deflection angle for the Schwarzschild case. So now when we compare for possible astronomical applications, we consider the Sagittarius A star and M87 star black holes. And as we compare the results, we can see that the solid black curve is for the Schwarzschild case for both the cases, and the red, green, and blue curves are for the black hole under consideration in Chern-Simons theory for different values of the spin parameter. And we can see that after a particular value of the impact parameter, it almost overlaps with the Schwarzschild case, which gives us the conclusion that we can obtain for the Chern-Simons theory also, we can obtain observable lensing features. Next, we have another aspect of gravitational.
Sorry, Nashiba, we are shooting very much over time.
Yeah,
so can you quickly summarize? Very quickly.
Sorry?
So very quickly, can you summarize, because
Yeah,
we are
so
shooting
just 1
very
minute.
much over time.
Thank you. So for the Einstein ring, we have the lens equation, which can be rewritten for the weak field limit and as given by equation 30. And for the case of the Chern-Simons gravity, we obtain equation 31 as the Einstein ring. And in a weak field limit, we can finally obtain the Einstein radius as given by this equation. And we portray the Einstein radius as a function of the impact parameter for 3 different values of the spin parameter for both the cases of the black holes. Here we can see that the Einstein ring increases and becomes constant after a particular value of the impact parameter. Again, for different distances between the lens and the source, we obtained a similar type of conclusion that Einstein ring increases with increase in impact parameter and becomes constant. But again, with spin parameter, we see that for different values of the impact parameter, the Einstein ring radius decreases with the spin parameter for both the cases, which gives us the conclusion that we can obtain. Here we can see that as compared to the Schwarzschild black hole, the Einstein ring radius is more, means the Einstein ring radius will be bigger, so which gives us the probability to obtain better Einstein rings for future weak lensing observations. So this is the summary of my work, and thank you for your patience.
Yeah, thank you so much, Nashiba. I'm afraid I don't think we have time for any question now. So thank you so much for the talk. Maybe we can go ahead with the next speaker. Thank you. So the next speaker is Jayshree Chaudhary. Jayshree, if you're here, can you please share your screen and go ahead? Jayshree, if you're here, can you please share your screen?
Okay, okay, she is here. Jayshree, can you please unmute yourself? Jayshree, you need to unmute yourself first.
I cannot hear
Jayshree,
you clearly, Jayshree.
I'm trying. Okay, Jayshree,
Okay.
let's do
No
one
worries,
thing.
no worries.
Jayshree,
Maybe we
meantime,
go to the next speaker
next
for
speaker,
now.
yes. So Sagnik are
And
here.
we will come back to you, Jayshree, after the next speaker. So
So in the meantime, please try to resolve the issue. Okay.
Yeah, the next speaker is Sagnik Chatterjee.
Hi. Can you hear me?
Yes, I can hear you. Can you please share your
Yeah.
screen and go ahead?
Can you please tell me if my screen is visible or not?
Yes, it is. Please go ahead.
Hi, so good afternoon, everyone. My name is Shagnik Chatterjee, and I'm a PhD scholar from IISER Bhopal. So before I begin with, I would like to thank the organizers for organizing such a lovely meeting. So the topic of my talk would be hunting gravitational waves from quaking pulsars. So this is based on our recent work which we have done. You can see the archive link here. So let's begin. So for the initial setup, we consider a FLE model, which is called also called Franco model. Here we consider the core of the star to be made up of a fluid and the crust of the star to be made up of some elastic material. So the schematic diagram you can see here denotes one such neutron star or a pulsar where the core is made up of a fluid and the crust is elastic. Now, as the star is rotating at some angular velocity, obviously since both of the elements are of different material, so they would be rotating at different angular velocities. So this difference in rotation would force or develop a stress on the surface of the star or the crust of the star. So there exists a maximum threshold rotational frequency beyond which this crust can break, and this phenomena is called a star quake. And such a frequency or the threshold frequency which you can estimate is called the breaking frequency of the star. So one of the possible reasons for reaching a breaking frequency can be spin up of the pulsar due to an accretion process. And the breaking frequency can be estimated using this formula where the numerator is the maximum strain angle and the denominator is the maximum breaking strain. The figure shown here is the plot of strain angle against the polar angle. You can see here that the maximum strain angle is somewhere around 7 times 10 to the power minus 3. And for our case, what we would look forward is that we have calculated the breaking frequency for a particular case of about 580 hertz. That is, we begin with some initial frequency of a star, and the breaking frequency or the threshold frequency is 580 hertz. Now, so these involves more theoretical calculations. So for your references, I have the archive link, so I won't be going deeper into those stuff. So in our analysis, what we try to do is that we try to understand two models. So we try to analyze two models. Here, this is the model one, which we call it. We have a spherically symmetric star, and it has a magnetic mountain at its magnetic axis, and the magnetic axis and the rotational axis are not aligned together. So for such a configuration, the moment of inertia can be estimated of this form, where delta m denotes the mass of the small mountains, the capital M denotes the mass of the star, r being the radius of this spherical star, and a here denotes the mass of each of the mountains. Now, considering a spherical model is a very realistic, idealistic scenario. In more realistic scenarios, our star would not be a sphere. And in such a case, we need to consider some kind of a deformation. So in this model too, we include such kind of a deformation. And as we consider deformation, the radius in this case can be decomposed into two components. One would be the equatorial radius and the other would be the polar radius. And then this moment of inertia gets modified of this form. Here Req denotes the equatorial radius and Rp denotes the polar radius. Now, if you go ahead in calculating the gravitational wave for these two cases, each of the components is given by this analytical form, where H0 denotes the amplitude of the gravitational wave, and this can be estimated of this nature, where G is the gravitational constant, C the speed of light, IZZ denotes the zth component of the mass quadrupole moment, omega denotes the angular frequency. But the starking difference for these two models is that the amplitude for model 1 case directly depends on the mass of the mountain which we have taken here. On the other hand, when we consider our model 2, we see that it also depends upon the ellipticity or the radius ratio or the amount of distortion which our star has, which is reflected by this formula. Now, since I have told that my motivation is to hunt for gravitational waves using quaking pulsars, let's look at a scenario how this would look like. So these plots are for model 1. So the first panel shows initial configuration where we begin with a 346 Hertz star, and it has some kind of a gravitational wave, and due to spin up till it goes to 570 Hertz, there would be obviously an increase in amplitude. But from 570 to 580, which is the breaking frequency here, we would see a sharp rise in our gravitational wave, which is characteristic of a star quake. And this change in gravitational wave occurs as soon as the breaking frequency is reached, because there is a change in ellipticity at the breaking frequency. So this is for a model 1. Now we can do we can perform a similar analysis for model 2. Similarly, again, we have that deformed star, and again we have an initial configuration of gravitational wave. Then it increases due to spin up, but the increase in amplitude from 570 to the breaking frequency is very huge. So this basically shows that so far we haven't been able to detect continuous gravitational waves from the LIGO detectors. But in future, if there is a possibility, then if we will be able to observe a pulsar for a continuous gravitational wave, and we see a sudden jump in the gravitational wave amplitude, one of the plausible reasons for such a phenomena can be star quakes. Now, what we try to do is...
Sagnik, you have 2 more minutes. Sorry.
Yeah, I will wrap up. Yeah. So now what we can do is that we can change the mass of the mountains and see how the gravitational wave changes, amplitude of the gravitational wave changes. As discussed previously, for model 1, it depends on delta m, which is the mass, but we see that for model 2, initially for a particular ellipticity, we don't find much change in the initial gravitational wave, but with also decrease in the ellipticity, we would also see the masses of the mountain to affect the gravitational wave as well. Now, another valuable question which one should ask is whether the position of the magnetic mountain would also have any impact on the mass on the gravitational wave amplitude. So since model 1 is symmetric, it won't have any effect. For model 2, we can shift this mountain by some angle beta, and when you calculate, you find that the amplitude of the gravitational wave is directly proportional to cos square of this angle, cos square beta. So to summarize, what we have done is that we propose the prospects of detection of quaking pulsars from continuous gravitational waves. And in this regard, we study 2 models to understand the effects of star quakes on gravitational wave signals. The masses of the mountains as well as the radius ratios of the stars have effect on the gravitational waves, and the position of the mountains can also play a crucial role in identification of gravitational wave signal. So thank you.
Thank you very much, Sagnik. I already see, Surajit, you have your hand raised, so please go ahead with your question.
Yeah, Sagnik, in your 2 cases, what are the difference? In one case, you showed it's spherical, another case, it's ellipsoidal. So these two both has magnetic field, right? Both these cases. So how can, and magnetic field is axisymmetric. So how can in one case it's being spherical, in another case it's elliptical?
Sorry, I didn't get your question. So this is a toy model what we consider. So it,
yeah, but both these cases you have magnetic fields, right?
Yeah.
So when you have magnetic fields, magnetic field is axisymmetric, so it has magnetic pressure. So it cannot be spherically symmetric in either cases. So why do you consider one case is spherical and another case is?
So in one case, what you can consider is that the magnetic field doesn't have much an impact. So it is a very idealistic scenario, just for simplicity of calculation. But in model 2, which is a more realistic scenario, for a strong magnetic field, you would find some deformations in the star. So that has been taken into account.
And have you calculated how much magnetic field is required to detect this signal by some detectors like Virgo?
So what we did, so since these are theoretical calculations, we tried to model them using an XNS code, which uses a magnetic field. But the magnetic field, so the radius ratio was around 0.8, which is very high. And the magnetic field at the surface was somewhere around 10 to the power 15 Gauss. So this is very an extreme case.
So it's a magnetar case.
Yeah, magnetar case. So the assumption is that the magnetic field is so strong that the deformation is mainly due to a magnetic field and not due to a rotational yeah.
Thank you, Sagnik, for the nice talk. I had a couple of questions, but I think we're running very much beyond time, so maybe I'll skip that and catch you later if required. Thank you so much for your talk.
Yeah, thank you so much.
Maybe we can go to the next speaker. So Jayashree, have things been okay with you, or should we go ahead to the next speaker, or can you share your screen and try now?
Sir, my
So there is an
computer,
echo.
so I will join through mobile audio and present in laptop.
Yeah, please go ahead. Yeah, whatever is convenient. Yes.
Yes. Is my screen is visible?
Yes, I can see your screen, so please go ahead.
Hello everyone. My title of my today's presentation is Reinterpretation of Modified Theories of General Relativity. I am Jaikhomba Chaudhary from Department of Mathematics. I am an MSc 4th semester student from Bhawanipur University. This is a review work guided by Professor Phongzum Priyokumar Singh. So, outlines of my presentation are, these are my outlines. So, this is the introduction. General relativity. The theory of general relativity was proposed by Albert Einstein in 1915. It is a very successful theory of modern physics, which is a generalization of special theory of relativity and refines Newton's theory of gravity. It's a geometric property of space-time which directs the motion of objects. This four-dimensional space-time curvature is directly linked to the energy momentum of matter and radiation. Here's the Einstein field equation of ZR, which is a second-order partial differential equation. So, the main topic is the modified theories of ZR. So, why modified theories of ZR? And despite ZR is a very successful theory, we need to look beyond ZR because of its incompatibility with quantum mechanics, singularities like black holes, Big Bang, where curvature becomes infinite. Also, to explain universe in large scale, ZR needs to introduce dark matter and dark energy, but then ZR lacks direct observational evidence of dark matter and dark energy. So we need to look beyond the earth. So we need some modification. Here's the some modified theories of the earth in different direction, like adding new fields, adding invariance, adding geometry, changing dimension. We get many modified theories. Here today in my presentation, I will present some of them. The first one is branch decay theory, which is a competitor to Einstein's general theory of relativity. Branch decay theory introduces scalar field in addition to tensor field in VR, which alters the effective gravitational constant locally. So in the field equation of branch decay, we add and branch decay coupling constant omega. Here's the field equation in branch decay theory. We see here we add omega, which is a branch decay coupling constant, a dimensionless constant. So this is the field equation in case of branch decay theory. So branch decay theory is a very good choice to study dark energy. And the expansion of the universe. It can be considered as the most natural choice of scalar tensor generalization of general relativity due to the easiness of the theory. So here some works of Parmar, Singha, and others presented. They presented in their work a cosmological model in high-dimensional spherical symmetric spacetime that includes energy momentum tensors of many interacting fields of dark matter and holographic dark energy based on branch decay theory. Based on branch decay theory, they did many works like analyze the field equation under realistic assumptions consistent with cosmological observations to obtain exact solution. So specific constants that resulted in overall density parameter and Hubble's parameter value very close to the observational data. The model predicts a universe undergoing super exponential expansion. And these are the new results which we get more in theory than in general theory of relativity proposed by Einstein. The future universe will be increasingly dominated by dark energy, provided a comprehensive analysis of the physical and kinematical aspects of the parameters, including the possibility of future singularity in comparison with observational findings. Next we move to the another topic, Lyra geometry, which is not a modified gravity theory, but it's an extension of Riemannian geometry, where in Lyra geometry, adding a Gauss vector field, we get the field equation like this, which describes gravitation in geometric terms, similar to Einstein approach. So here, this is the Einstein field Lyra geometry, where we add a new it's a vector field, this Gauss vector field. Here we see this is the file. So where R mu is Ricci tensor as the Ricci scalar and these are all. So where phi mu represents the Gauss function introduced by Lyra. So this is we newly add in Lyra geometry, but in VR it is not there. Then beta is a coupling constant related to the Gauss field. So the above equation reflects how the presence of Gauss vector field phi mu modifies the gravitational field equation compared to the standard Einstein field equation in ZR. So in a work of Jaikhomba and others, they constructed a model universe within a 5-dimensional Lyra manifold. Included the string cloud interacting with standard matter and the vector field phi k. They assumed a constant displacement vector field. They reported the model behaves as a dark energy universe, particularly of the phantom energy type, and the displacement field is considered as a component of the total energy and act as dark energy. So this is the another modified theory, of ZR. This is the magnetic gravity theory.
Sorry, Jesse, you have 2 more minutes. Yeah.
Okay. So this is the another theory where in this its original format, the mimetic theory of relativity derives the general relativity by isolating the conformal degree of freedom. This is the main thing we here in this theory. They isolate the conformal degrees of freedom and with an auxiliary metric and the mimetic field. So then the field equation becomes like V nu equal to this one. This is the field equation in mimetic gravity theory, where theta nu is the stress energy tensor sourced by the mimetic field. So this is the modification. This is the modified. This is the modification in general relative here. So on a cosmological scale, especially in FRW background, mimetic fluid companion mimics the behavior of cold dark matter. So the mimetic field effectively serves the dark matter candidate within the framework of mimetic gravity theory. Here we get some findings findings of first cosmological implication of the theory. Here's the findings of mimetic massive gravity. The theory cannot self-accelerate without introducing a force, and here's more findings on this theory. So these are this. So next we proceed to the next theory. This is FR gravity theory. So FR is a type of modified ZR, generalized Einstein ZR, which is a family of theory. Actually, each family is defined by a different function f of Ricci scalar I. While ZR is based on the Hilbert-Einstein action, this is the Hilbert-Einstein action in FR gravity, and this is the standard Hilbert-Einstein action in general relativity. So here, this R is replaced by this FR, which is a family of function of Ricci scalar. So the gravitational field equation of FR becomes this. So this is the gravitational field equation in FR gravity theory. So in the work of Feyerabend, Surendra Singh, and others, we get some findings of their works. These are the findings. Obtained an isotropic model universe undergoing super exponential expansion. Predicted the model universe behaves like a dark energy model. Observed that the universe is close to nearly flat. So predicted to approach the de Sitter phase dominated by vacuum and cosmological constant finite time future. So these are some of the modified theories where we modified ZR, general theory of relativity, in different direction, and we get different and results on it. So this is my acknowledgement, and this is my references of my presentation. Thank you.
Thank you, Jayashree. So we are spot on time. So do we have any quick question here? If not, thank you, Jayashree, for the nice talk. So let's move ahead with the next speaker. Thank you, Jayashree. You can unshare your screen. Thank you. The next speaker is Rupjyoti Gogoi. If you are here, can you please share your screen and go ahead?
Yeah, am I audible?
Yes, you are audible. Please go ahead.
Yeah, thank you. Okay, is the slide visible?
Yes,
it's
visible.
Yeah, thank you. So good afternoon, everyone. So I'll be talking about ring-down gravitational waves or quasi-normal modes in five-dimensional Einstein-Gauss-model bumblebee black holes. So this is the outline of my presentation. So at first, I'll be talking about gravitational waves in general theory of relativity very briefly. So here you can see in equation 1, this is the general action of general theory of relativity. Here this R is the Ricci scalar, and the associated field equation is given by equation 2, where this capital G mu nu represents the Einstein's tensor having this explicit form, And here this G min is the metric tensor, R min is the Ricci tensor. Now, in order to see the effects of gravitational waves, we part up this background metric at very far distance here from actual source of gravitational waves, and here this S mu nu is the perturbation term, and by introducing this perturbation and considering the gravitational waves at very far distance here from actual source of gravitational waves, we can obtain this particular wave equation given by equation 6. And here we are considering T mu equal to 0 because we are considering the gravitational waves at very far distance away from the black holes. Now, what this equation says, so this says that there are 2 degrees of freedom associated with the theory, and hence there can be 2 polarization modes of gravitational waves present in this theory, and there is no scalar propagation mode of gravitational waves present in this theory, and being massless gravitational waves propagated with the speed of light through the space-time. So here in this figure you can see tensor plus and tensor cross modes of polarizations of gravitational waves. Here we are considering that the gravitational wave is propagating along z-axis. So this one is tensor plus polarization mode, and this one is tensor cross polarization mode. And the prominent sources of gravitational waves are supermassive binary black hole mergers, neutron star mergers, black hole neutron star mergers, etc. And relativity, let me discuss it very briefly. So all these drawbacks of general theory of relativity can be briefly classified into 2 main categories. The first one is associated with the observational things. So the theory disagrees with an increasing number of observational data associated with the low energy scales, associated with the accelerated expansion of the universe, galactic rotation curve, gravitational wave lancing, etc. And the second one is a kind of theoretical problem, and it says that general theory of relativity cannot be renormalizable and cannot be quantized at very high energy scales. So therefore we need to modify general theory of relativity. And since the previous speaker already discussed about different modified theories of gravity, so I will skip those things here, but briefly I will discuss how to modify general theory of relativity. So this is our field equation associated with general theory of relativity, and on this left hand side you can see the geometry part of this theory, and on this right hand side you can see the energy momentum part of the theory. So we have 2 options: we can either modify the geometry part, or we can modify the energy momentum part, or we can modify both part at the same time. So when we modify the geometry part in general theory of relativity, we may have different degrees of freedom. The number of degrees of freedom increase from 2 to 3, and therefore the polarization mode of gravitational wave may increase. For example, if you consider FR gravity in metric formalism, then you will see that there is a third polarization mode that exists in this particular theory, and basically, but if you consider a particular case, say pure R square FR gravity metric formalism, then the third polarization mode is the pure BT mode, and this is the only particular model in FR gravity metric formalism where you can have massless gravitational waves. So the propagation speed of gravitational wave changes due to the presence of massive scalar mode. The complex structures are also significantly affected by defined modifications introduced to the geometry part of the theory, and hence we observe significant variations in gravitational waves and in gravitational wave power spectrum. We also observe that quasi-normal modes are significantly affected by different modifications, whether you modify the geometry part or energy momentum part, you will observe a significant changes in quasi-normal modes or ring-down gravitational waves. And apart from these changes, there can be a lot of other changes we do not know till now. So gravitational waves, the quasi-normal modes, basically these are numerically calculated quasi-normal modes. Then you will see that these are some complex numbers where the real part of these complex numbers basically represent the oscillation frequency associated with gravitational waves, and the imaginary part basically represents the damping rate associated with the gravitational waves. So in this particular talk, I'll be discussing about Einstein-Gauss-Bonnet bumblebee theory of gravity. In one of our previous work published in the JCAP in 2022, we considered a complete bumblebee gravity where we included monopoles. That means we considered some topological defects, and we also considered quantum corrections, and constructed a complete bumblebee gravity theory, and calculated the black hole solutions from this theory and obtained the quasi-normal modes. But from the perspective of cosmological data, we have observed that this theory is not completely viable, and the theory cannot explain all the observational data obtained so far. So we try to include some higher order curvature terms into the theory. Apart from bumblebee field, we try to include some higher curvature part like FR gravity part or Gauss-Bonnet invariant part, etc. So in this talk, I will be talking about Gauss-Monod invariant part and bumblebee part together. And in this particular theory, we obtain the black hole solution given by this equation 10 and 11. So here you can see this lambda part basically represents the Lorentz symmetry breaking term, and this alpha basically represents the strength of Gauss-Monod term. And we calculated the quasi-normal modes associated with the black hole by using 6th order Pede average WKB approximation method. And we also validated these calculations by considering different methods, including physics-informed neural networks. We also considered numerical solutions, and we also considered time domain profiles and fitted those time domain profiles by using different neural networks and Marquardt-Levenberg algorithm and Prony fitting, and validated the results of 6th order Pede average WKB approximation method. And finally, we have seen that both the model parameters have similar kind of impacts on the quasi-normal mode spectrum. And then we investigated the Hodge conjecture, which is
sorry, Dhruva, you have
yeah,
you have 2 minutes. Sorry.
Okay. So this is the Hodge conjecture, and it is associated with the damping rate of gravitational waves and Hawking temperature, which is given by equation 13. And we have seen that the Lorentz violation basically respects the Hodge conjecture, while this Gauss-Monod term does not respect the Hodge conjecture. We also investigated the shadows associated with the theory, and also emission rate or emission decrease the Gauss-Monod coupling term. Then the emission rate of the black hole decreases by increasing its lifetime, and when we increase the Lorentz violation term or Lorentz symmetry breaking parameter, then the emission rate of the black hole increases and it decreases the lifetime of the black hole. So we also tried to connect the damping rate and the oscillation frequency of ring-down gravitational waves with shadow, one of the observational parameter of observational property of black holes. And this is our summary, and we have observed that higher values of the Lorentz violation parameter tend to support the validity of Hodge conjecture, while smaller values of the Gauss-Monod coupling term favors its validation. And we also found a correlation between evaporation rate and the validity of Hodge conjecture. And there are some future prospects associated with this kind of investigation, and these are some references. And these are my collaborators associated with this investigation. That's all. Thank you.
Thank you very much, Dhruva. So we have time for a few questions if people here in the audience want to ask. Okay, if not, maybe we can go ahead. Thank you, Dhruva, for the nice talk. So
yeah, thank you.
So the next speaker and probably the final speaker of this session is Olag Pratim Bordoloi. So Olag, if you're here, can you please share your screen and go ahead?
Can you see my screen?
Yes, I can see your screen. Maybe you can increase the volume a little bit.
Okay, so am I audible well?
Yes, now you're audible well. Yeah, please go ahead.
Yeah, okay, so first of all, thank you to the organizers for giving this opportunity. So basically I'll be discussing a small part of one of our recent works on the diffuse ultraviolet emissions from a dwarf galaxy called Homburg 2. So let me first begin with so what is a dwarf galaxy and why they are important to study. So dwarf galaxies, they are basically the smallest galaxies that are known in the universe, and they are very abundant in numbers. They are very abundant. So and they are considered to be the building blocks of the larger galaxies through merging processes. So these dwarf galaxies basically merge with or interact with the larger galaxies. They get merged with them, and the larger galaxies can evolve. And one of the unique characteristics of these dwarf galaxies is that they have very low metallicity environment. So that means the metal content is very, very low, which actually was the condition in the early universe galaxies. So these dwarf galaxies actually can replicate the environment of the early universe galaxies. And so it can help us in understanding the early universe galaxies, how the early universe galaxies can evolve to the present day galaxies. So it is a very useful object to study to understand these processes. So if we study the dwarf galaxies in our local group as well as in the nearby groups, then that can give us an idea about the evolution of the early universe galaxies to the present day galaxies, as well as the environment in the early universe galaxies. So in this particular work, so we have used the galaxy that we are considering or we are targeting is a galaxy called dwarf galaxy called Humboldt 2. So it's an irregular galaxy because it doesn't have any particular shape or structure like our spiral galaxies like Milky Way. So it resides in our nearby galaxy group M81. So it's a low metallicity galaxy, as I've already mentioned. So around 1.1 solar metallicity, and this galaxy is extensively surveyed through many surveys, covering a broad range of the electromagnetic spectrum. And the neutral hydrogen distribution of this particular galaxy is very unique because it contains many cavities where there is no neutral hydrogen is present. So we term them as voids. And another important feature about this galaxy is that it contains one of the brightest ultraluminous extra source, which is known as the Humboldt 2 X1. So these are some details of this galaxy. So these are some technical specifications of of Astrosat, our own India space mission, whose data we have used here. So basically, Astrosat have 5 payloads. So we have used only the UVIT instrument, that is called ultraviolet imaging telescope. So in this particular, and this UVIT has the highest resolution of all the UV telescope that is currently operating. It gives us a resolution of around 1.2 to 1.6 oxygen. So these are the observations that we have taken. So basically, we have considered observations from 8 epochs, and these are the processes that is involved in the processing of the raw images to the science-ready images. So we have used a pipeline called Joule, that is called Giant's UVIT Data Explorer, which is developed by Professor Jayant Murthy from IIA Bangalore. So these are the schematic of different. This is a schematic of different processes involved in the data reduction process. And these are the different filters at different wavelengths that we have used in our observations. And these are the final images that we have obtained through this processing and all. So the left one is the FUV image, the far ultraviolet, which is a wavelength of around 154 nanometer. And the right one is an UV image at a wavelength of around 245 nanometer. Now coming back to our objective, that what we did actually. So the plenary speaker of today's session, Dr. Rupjyoti, has already given a very good insight on the different components of the interstellar medium. So these diffuse emissions that are produced in the interstellar medium, so these are basically produced by the interstellar dust grains. So so basically in this work, we are focused on the diffuse emissions in the far ultraviolet and in the infrared, because the dust, the radiation which is scattered by the dust grains, so those are observed as diffuse emissions in the far ultraviolet wavelength. Whereas those radiations which are absorbed by the dust grains, they are again re-emitted in the longer wavelengths, mainly in the mid-infrared and the far infrared wavelengths. And so these two emissions, UV and IR, they are basically complementary to one another. So in this study, so we have tried to find out the correlation of these UV and IR diffuse emissions. So why we need the correlation study? Because it's a very important statistical method which that can determine the relation between two quantities, and that is used in many fields. So basically, I have already mentioned the scattered radiation is observed in UV and absorbed and re-emitted is observed in IR. So mid-infrared emission is basically due to the warm dust, which has a temperature of around 50 to 100 Kelvin. Although they are called warm dust, but the temperature is very, very low compared to our ordinary room temperatures. And the far infrared emissions is due to basically colder dust grain, even colder. That is, the temperature goes to around 10 to 50 Kelvin. So this correlation study will help us to identify the abundance of different grain populations at different temperatures, also which is contributing to the diffuse emission, and also it will help us to find out the dominating grains, whether it is a warm grains or cold grains that is producing the diffuse emissions. So for the data for the UV data we have used our own Astrosat data, and for IR data we have relied on the Spitzer and Herschel space telescopes. So we have considered the IR wavelengths, IR observations for 8 different wavelengths, starting from very low 3.6 micron to high 160 micron. So different the grain populations at different temperatures, they emit at different wavelengths. For example, 3.6 micron emission, that is considered to be stellar emission. There is no dust component in them. Then 4.5 to 5.8, that is the emission by hot grains. 8 micron is very interesting. That is emission by polycyclic aromatic hydrocarbons. So that's a very interesting candidate of dust grains. Then 24 and 70 micron are basically emitted by warm dust grains, whereas 100 and 160, they are basically emitted by the cold dust grains. So now, since we are looking for diffuse emissions, so we should be very careful about the selection of locations, since because we do not need any kind of point sources which can contaminate the diffuse emission. So we selected 143 locations across the galaxy, which are devoid of any point sources within a radius of 10 arcsecond. And also to make sure that no two locations overlap, so we two locations are separated from each other by at least 5 arcseconds. So out of those 143, we found only 33 which have both the UV and IR data. And we found out the intensities of those 33 locations through aperture photometry. And those locations actually divide into two groups. One is based on the neutral column density, hydrogen column density. So the threshold is 10 to the power 21 per centimeter square. So above that we have 17, and below that we have 16. Then correlation coefficient, we have used the Pearson correlation coefficient, which actually tests the linear relationship between these two quantities. So these are the results that we have obtained. So this is for high H1, I mean greater than 10 to the power 21. So we can see that the best correlation that we have obtained is for FUV and 70 microns. So that is basically responsible for the 1 dust emissions. And for NUV, we obtained the best correlation at 0.61 at 160 micron, which can represent that NUV is better correlated to the pole dust winds. And these are the correlation values for low column density locations, which we term as voids. So you do not see any very good correlation in the voids actually. So these are the correlation plots that we have obtained. So these are some of the correlation plots. So these are for voids actually, they do not show any correlation. Now the next part of this work is to derive the optical properties of the dust grain based on the modeling of this FUV diffuse emission. So this modeling will give us two important parameters. One is the albedo and other is the asymmetry factor. So albedo basically tells us what fraction of the incident radiation will be scattered by the dust grains, and asymmetry factor determines in which direction the scattered radiation will be. So this is the model that we have used. So this is a single scattering model because it is basically used for an optically thin medium, which was already tested for different galactic regions. So we have used the same model here also in extragalactic systems. So this model basically constrains the alpha and the albedo and the asymmetry factor for the dust grains. So this is the governing equation which we employ in the.
Olak, hello. You have just 1 more minute. Sorry.
Okay. And this is the Hennig-Greenstein phase function, which basically is attributed to the direction of scattering. So these are the star-forming regions, these red circles, which are basically contributing to the UV, basically the sources of UV luminosity in the region. And these are the luminosities that we have obtained for correcting for galactic as well as the internal extension of the galaxy. And so this is basically a basic schematic diagram of the model that we obtained. So this model gives us the scattered intensities for each combination of alpha and z, and we find the best fit values for this parameter based on minimum chi-square statistic. So these are the results we have obtained. So we have obtained a mean value of alpha equal to 0.2 and g equal to 0.5 for this particular galaxy. So to conclude these two different parts ago, so we have found that the 70 micron emission is better correlated to UV compared to other UV elements, which means that the diffuse emission is basically dominated by the warm dust component, and we do not find any good correlation for voids, UV correlation. Then one interesting feature is that none of these 33 locations showed emission at 8 micron. 8 micron is responsible for emission by pH molecules. So this is a very unique feature of this low metallicity galaxies because they lack these molecules. These pH molecules are not present in them. Then we found a reasonable agreement between the derived parameter values and the theoretical values. And finally, we found that the optically thick medium is responsible for the dust scattering, as seen in our galaxy also. So these are some of the references that I have used, and thank you for listening.
Thank you very much, Olak. I don't know if we have time for any question, but are there any quick questions? Okay, if not, thank you very much. I think we are at the end of this session, right, Vivek? Thank you, Olak, for the nice talk.
Thank you, Jaikhomba. So so this is the end of session 2 basically. So I know Jaikhomba, the timing difference is a lot. So but when
it's not too bad. It's not too bad.
I can see the watch over there in your background. It's close to 11 o'clock, right? So I can see the clock.
Yeah.
So thank you.
It's okay. I'm joining from Bonn, so I'll go to the office now. So
sure. Okay. Sorry. Okay then. Thank you so much. Thank you so much, Jaikhomba, for chairing the session, and thanks to all the participants.
Thank you all the speakers. Yeah.
Yeah, all the
and the
speakers who
participants.
have,
Yeah.
yes, exactly. So now let's begin the session number 3. So for session 3, we have with us Dr. Vishal Parmar from INFN, Italy. So let me give a brief introduction of Vishal Parmar. So he is a collaborator and a very good friend. He did his PhD from Thapa Institute of Engineering and Technology in Nuclear Astrophysics. And then he did a postdoc in IIT Jodhpur, and now he's planning to shift to INFN. He has not joined yet, but he will be joining soon. So, Vishal, are you there?
Thanks, Vivek, for that introduction. Can you hear me?
Yes, yes. So, you are yes. Hi, Vishal. So you can so we have scheduled you to chair the session number 3. I think all the presenters are here basically, right? Surajit Kalita from University of Cape Town, yes, and the speakers from abroad. So we thank you very much for your patience. We are going a bit late, but thanks for bearing with us. Thanks, Surajit. Thanks, Surajit. And then we have Badal from States. I think he is in India now. He mentioned that. So for Badal, it is fine. Okay, then let's start this session number 3. Surajit, if you are.
Yes, Vivek, can you hear me?
Yes, yes. So please, you can start this session. Start your presentation. And Vishal, it's over to you.
Thank you, Vivek. Thank you so much. And so we'll be having Dr. Surajit from University of Cape Town.
Yes. I hope you can see my screen.
Yeah, we can see your screen and we can hear you very well.
Yeah. So thank you very much. So this talk, I'll be talking about fast radio burst, one of my recent works that I have been doing here. And I'm a member of collaborations of various surveys that's been going on. So what's fast radio burst? Fast radio bursts are basically radio transient events. They are observed literally in the order of megahertz to gigahertz frequency range, and they are very bright bursts whose flux is of the order of Jansky. And many of them are localized to host. That means their redshifts are known. They are very far apart, and we know from which galaxy they are from, but not for all of them, but for many of these cases. And some observed to be repeating, some apparently not. That means some are observed just once and never observed thereafter, but some of them observed repeatedly, but not with periodic repeticities. So it can be any time. And as I said, they are mostly extragalactic in origin. That means originated outside our Milky Way galaxy, but only one exceptional case that's been figured out, which is a soft gamma repeater. And so far, nearly on 700 FRBs have been detected, but majority of them are from China in Canada. But there are other telescopes which also detected a few of them. But the expected rates when we have proper facility and we have all sky coverage, then we will expect about 100 to 1,000 per day. And to explain fast radio burst, there are many theories have been proposed, and you can go through of these things in this website. So this is one of the first FRB that have been observed in 2007. It's also famously called Lorimer burst. And here you can see a line, this is called dispersion sweep, which basically tells that different frequencies of the light arrive to the telescope at different amount of time. So you can see the time is different for different frequencies. And with this dispersion sweep, the dispersion measure we can calculate, and from that we confirm that they are originated outside our Milky Way galaxy. And because of these features, they have been used for many physics that have been done, for example, constraint on photon mass or measuring lots of Hubble constant or other cosmological parameters. But I'm not going through all of these things. Rather, I'll be talking about something which I used in our case, that's FRB lensing. So what's in this case, suppose there is an FRB originated at the point S and we are observing at point O, and suppose there is a black hole in its path. Because of this gravity, the light from S to O bends, and we see multiple images of the source S, and that's called gravitational lensing. So once we have this kind of difference in the path, then we need to calculate the time difference between these two rays to arrive us. And to do this, you need to define the background metric. In my case, I have used a very generic background metric, which is a modified gravity metric. Just this portion is normal Schwarzschild metric plus some additional term, and this additional term can take over many gravity theories like scalar tensor theories, or even Einstein lambda also. So if we just take this and if we calculate the time difference between these two rays, we get this kind of formula where y is basically the impact parameter, which is very closely related to the Einstein angle. Now, if I plot this delta t, we have this kind of plots where basically it shows that where psi is this modified gravity parameter. So once we increase the modified gravity parameter, the time difference between these two annulus, between two impact parameters, decreases. And I want to show that this will affect on some other physics that I'm going to discuss. So in our case, we'll be using FRB data sample, and I'm using only time FRB data sample. By the time I used, it was about 636. And the dispersion measure that I showed in the first slide primarily has three components. One is from our Milky Way galaxy, one is from our host galaxy, and one is the intergalactic medium between these two galaxies. So we generally have a very fair idea of the dispersion measure from our Milky Way galaxy. And is very much uncertain, but for some of them, it's not dispersion measure. If we use this DM we have observed from our telescope, we can calculate this DM IGM values. And once we calculate this DM IGM, it has directly related to the source redshift of this object. And if we just solve this equation, we can see that with this dispersion measure that's been observed, the source redshift is estimated in this way. And you can see it has been estimated to up to even redshift 3, which is very high redshift, because we don't have lots of astronomical objects at that high redshifts. So now what we go back to this original figure, and we calculate something called optical depth. I'm not talking about all the details, but it's basically related to some of these cosmological parameters and this area between the two annulus, and also something FPBs, which is basically primordial. Suppose that black hole, which is being deflected this light rays, it's made of its primordial case. Then how much of that primordial black hole is made up of dark matter, that's been given in this FPBH factor. So from here, for this just for one FRB, because we have so many FRBs, we can consider an integrated optical depth. And general idea is that total number of FRBs are very large compared to the lensed FRBs that have been observed. So we can safely use the Poisson distribution. So now the current fact is that no lensed FRB have been confirmed, except last one week ago there is a paper. I know, but by the time we publish this, no lensed FRBs have been confirmed. So this formula can be written in this form, where this FPBH is less than all these numbers. And if we just plot these things, we can get a constraint on these primordial mass black holes made up of dark matter. And its constraint of the order of 10 to the minus 4 to the 4 solar mass energy range. And it's shifted as we increase the modified gravity parameter. Now, if you compare this with a previous study where basically people use plasma lensing, that means there is plasma in the intervening light ray. And it's very similar, these two plots, except it looks a little bit different because of the statistics that we use. I use Poisson statistics, they use something else. But overall, they mimic exactly the same, which basically tells that FRB lensing modified gravity mimics like a scattering screen, like plasma lensing in the path of the light ray. And FRB lensing, of course, it can help in constraining primordial mass black hole fraction made up of dark matter. There are other experiments, and it's very comparable with those experiments also. And in future, there are many more experiments. One is HIRAX, it's being in South Africa, it's being planned, which will detect many more FRBs in the southern sky. And the paper we published in this case. And just one slide of this HIRAX. So HIRAX is just a radio interferometric array like this. It's been planned is of the order 256 dishes, 2024 dishes. And it can detect many FRBs and pulsars, and also it can it can detect baryonic acoustic oscillation of this dark era of this universe, and it can basically map the large scale structure of the universe. So this gives me the conclusion slide that FRBs are very interesting as they can probe the cosmological distances. And many FRBs will be detected. So all these constraints, including our FRB, all those cosmological constraints can be better. And of course, like HIRAX, as I said, it's 256 dishes can detect also like at least 1 or 2 FRBs every day on average. So thank you very much.
Thank you, Surjit, for your wonderful slide. Do we have any question for the speaker? I think none. I just have a small query on the HIRAX. So I was just wondering if all the dishes are now operational or it's still working.
No. Only this is the prototype that's being placed in hard trial. It's the prototypes. But for this current status is that I think they have planned only 2 dishes so far. But I think the end of next year, they are in the middle of next year, they are planned to at least the 8 dishes, and they are also finding out the outriggers. So they are concerning about these outriggers, which states there, which country they want to go for these outriggers.
Yes. Actually, few months back, we have the director Aries in IIT Jodhpur. So he was talking about this HIRAX and the advantage of the geographical destination which they have picked for this particular project due to their low optical pollution and such things.
Yes.
Okay. So thank you so much.
Yes. Thank you very much.
Thank you so much, Surjit, for your time. So next we have Ronaldo Lesnam from Astronomical Institute, Hokkaido University, Japan. And do we have this speaker here?
Yes, I do.
Okay. Can you
hear me?
Kindly share your screen.
Okay. Can you see me?
Yeah, we can see your screen and we can hear you. You can proceed. Thank you.
Okay, yeah, thank you so much for this organizing this nice conference. And I'm Ronaldo, and now I belong to the Tohoku, but now currently at ESO Gershing. So I will just present one of my recent work where we discover and filamentary overdensity at redshift 1.5 stressed by the O2 emitters at the cosmos field. So with the JWST and the Subaru SSSB, yeah, we study the morphology and star forming activities. So this paper is already in APJ later. So before starting, I will briefly tell about the background of. So like we know that galaxies like properties like star forming activities, morphology, and can abundances, other things like are strongly depend on the environment, especially at the local universe at the redshift 0. So like it's important to understand where the galaxies live, like their environments for their star formation, also for their quenching. So here is from the famous Springer simulations large scale structure, where we have these dense clusters, which is very high dense regions. So in the local universe, so what we can see is that this is from, I think this can be the part of the Gogoi where it's crowded city, right? So in town of the galaxy, in the local universe, most of the galaxies in the dense environment are elliptical or no or little star forming activities. Well, so we have here kind of void or very low dense region, and So it can be kind of village life where we don't have many people. So in the time of the galaxy, at the redshift 0, most of the galaxies in the local universe are spiral or star-forming activities. So the main point is that it's important to understand the galactic properties along this large scale structure, like how it's at the higher redshift, like at redshift 0.4, 1.5, and so on. So yeah, so for this, we study with the different narrowbands, emission line galaxies, and the different redshift from the Subaru hypersupercan data, and so we discover an interesting structure, as we can see here. This is a redshift 1.5, and the universe was around 9 gigayears. Yeah. So this is very extremely dense environment with 11 times higher than the field average. And you can see here this beautiful structure. And the interesting thing is that this structure is populated by the star-forming galaxies and very less quiescent or red galaxies. So it will be, I think this structure is now kind of proto-structure where active assembly of the cluster formation. So yeah. So thanks to the JWST NIACAM, which give us very good resolutions, high resolutions, we can study the morphology. So what we did is that with this structure. Oh, what is going on? Is it okay? I don't know. Can you hear me?
Yes, please proceed.
Hello? Okay, sorry. So what we did is that we use the like core and outskirts and the field, trying to understand how, like, around this very overdense regions, how is the galaxies behave, and also the field environment. And we found that those galaxies located in the core, like these very overdense regions, they are very much disturbed signature, like margin signature. On the other hand, those galaxies which are located in the field environment, they are kind of, calm, not very, like, not showing this kind of disturbed signature. So from the visual inspection, we found that there is a kind of segregation, like at the dense core, most of the galaxies are disturbed signature. On the other hand, in the field, we don't see much. So this is from visual inspection. So we do the quantitative analysis. So we do the non-parametric fitting, and Gini. So Gini is, maybe some of you may not be familiar. So Gini is like coming from, it's like, so it's measured how the light is across. So Gini 0 means like light is here in the time, like equal well is distributed in a society. Gini 1 means all the light is coming from single pixel, but in the simpler case, it can be said that only one person is having all the well in the society. And also M20, who's like the brightest 20%. And so what Gini and M20 do is that higher Gini and higher M20 means light is coming from very central region. So it shows that the galaxy is going marginal or disturbed signature. So by that, we use this Gini M20 and we check that the disturbed or marginal signature on the other. So we found that from the quantitative analysis, we found that the core galaxies are around 50%, by the field galaxies 21%. So both from quantitative and the visual inspection, we confirm that galaxies located in the core are having high disturbed signature. Yeah. So this is one reason. And next we try to see the star-forming activities, how the star-forming going on. And we found that those galaxies located in the core of the this overdense filamentary structure are showing more star-forming activities compared to the field environment. So something is going on here. So how we can interpret is that, so this is from, so our is kind of the filamentary overdensity. So because this is active phase, so still ongoing assembly. So when the gases are inflowing along this structure, so continuously gas inflow can destabilize the galaxies, which may show the disturbed or irregular galaxies morphology, what we saw in our case. And also since the gases are coming at the core, and so it triggers star-forming activities, SFR. So yeah, and there is not much environmental quenching mechanism like ground pressure stripping, which can reduce the star formation. So this is very strong overdense, very dense overdense. So they are still forming stars. So how many minutes I have left?
Only you have 2 minutes.
Okay, so I will just quickly summarize, one of the things, and this is paper is about to submit soon. And we also see at the recipe point 4 where we study the question, around the cluster, but this case, the galaxies are populated by the red galaxies, question galaxies. So it is already evolved cluster. And we try to do the recipe 0.4. We found that unlike the previous case, we found that those galaxies located in the core are having less star forming activities, and the field galaxies are forming star. And we also see the measure the size, like H alpha. H alpha means the regions where the star forming going on, and the continuum means all the light is spreading. We found that there is a truncation. So it means that those galaxies in the core are kind of truncated, and they're only in inner part is forming stars and the very less. So it is consistent with less star forming activities of the cluster core. So this may be because of the environmental quenching mechanism, like rapid stripping. So what is that when the galaxies fall into the cluster? So this is the recipe point 4. So this is already evolved cluster, as I mentioned. So there's many environmental quenching mechanism going on. So when the galaxies fall into this cluster, the gases are stripping away. The happy galaxy, when they fall, it's set. The gases are stripped. So that is why we see this truncation plus low star forming activities for the cluster galaxies. Anyway, here's a summary, and this is you can scan this code to read the paper of the discovery of the ferrometry structure, and it's in the APCL. And so we found a substantially overdensity structure. Also, we found that there is a difference between the core galaxies and the field galaxies, and this structure is kind of proto structures, like it's still active forming. So we see lots of things going on. Okay, thank you so much.
Thank you, Ronaldo, for your impressive presentation and illustrative cartoons we saw there. So we have any question from the audience? I think there is none. So I think again I will ask you a very
Yes.
Of the topic question. So how easy the JSAT has made life easy for the now when we are talking about the study of galaxy or the work as your one. So how different is JSAT compared to the other detector which you had prior to this one?
You mean like what? I don't get. Sorry. Like.
So I was wondering. So the data for this particular watch.
Yes.
So you generated JSAT satellite, right?
Yeah. So the data which I'm going use it. So we observe the data. So the data like this discovery. So it is in the Subaru. Maybe some of you may not be heard. So Subaru is very powerful telescope in the Hawaii. So we observe with that, and the very large scale structure, like this kind of field. We can see the structure, and we can map those, and also the JWST, like which is I think most of you may know. So it gives us the good resolution. So we combine both. So is it the question you asked, or like?
So actually, that was my question. That how easy the life is after we have the JWST with us.
Oh, okay. I got it now. Thanks. Well, yes. It's JWST change science. Because previously even we cannot reach to the higher redshift and this object thing. So if you don't have JWST, this is the redshift 1.5. So without the JWST, we cannot even trace this optical trace frame. So with ICST, previously it only traced the UV. So we may miss many things. So now with the JWST, we can extend to the higher redshift. So we can study lots of new things. And when the universe was formed, we can study fast galaxy. So universe changes the science, and it's write the new history of science. Yeah, it's going to write the new things of all the science, especially galaxies and other cosmology.
Yes. Thank you for that answer, Ronaldo. Thank you very much for being with us and talking about your work. So next we have Reznlin from Gogoi University, Assam. And she'll be talking about factual analysis of photoplantation. So we have two speakers here. Yeah, so we can.
Can you hear me?
Yeah, we can hear you and we can see your screen.
Hello.
You may proceed.
can you see my slides?
Yes, we can see your slide.
Yeah. Good evening, everyone. So,
Oh,
yeah.
yes.
Shall I continue? Okay. Yeah. Good evening, everyone. I'm Nazionale Singha from a research scholar from Gogoi University, Department of Applied Sciences. Today, I'm going to give a talk or work on the title "Fractal Analysis of Photoplanetary Disk Images" in this national conference, Physics Frontier 2024. So these are the outline of my talk. Then in the introduction, you can see on the right-hand side, you will see the image of photoplanetary disk. These images were actually observed by ALMA Observatory, and it was released as a D-Sharp data release. The data release consists of images from May to November 2017. You can go to detail in the first reference. You can check. Also, then again, from these photoplanetary this, you can see that the first prominent features that we saw is like the annular gaps. These annular gaps are the signature usually for signature for planets. So from the width of this gap, we can estimate the planet mass. In my previous work, I have used like fractal analysis or the nonlinear tool. It's a nonlinear dynamical tool that for classification of variable stars. So the same kind of an idea we want to apply in this study. So the methodology here, how are we planning or the approach here? So first and foremost, we take the original image from the from SO website. It is available, freely available, public. So we turn the colored image into grayscale image and then pre-process it, like denoising and normalization, etc. we have done. Then after that, we pre-process the fractal, means we calculate the fractal components like the Hausdorff exponent and regularization dimension here using the fractal analysis on the grayscale image. Then we get the Holder exponent and the regularization dimension. Then from these figures, we can extract some features that can explain or that can help in machine learning models, integrating them as a feature to filter and also help in improving the traditional model, the existing models. So fractal analysis, in fractal analysis, the Holder exponent regularization dimension is given by these equation. In the Holder exponent here, the mu, actually it calculates the distribution of each pixels in an image when a ball of size is covered over that. So if the size tends to 0, then we get the Holder exponent. Similarly here, regularization dimension, it's similar to the Holder exponent, just that one component, like 1 plus that, is added to it. So next, in the results here, we have seen the first object, that is HD141430006 here. It's given in A, and then B is the Holder exponent of this image, and C is the regularization dimension. See that it is actually the y-axis is flipped. Okay, so here you can see that in A, the orange rectangles that we saw here, it's very bright, and this bright pixels is actually dark, very dark here. So in Holder exponent, every bright pixels are converted into dark images, means black, and then this when you see it in the regularized dimension, that means they are highly dense. So these are like very orangey in color. And also like the kind of like a ring here, you can see it's also available in, it's also like projected in the regularized dimension. Similarly, the red rectangles here, you can see that the black pixels here in the original image, which is you can see like the little bit grayish color or grayish pixels are surrounding the black portions here. So these are highlighted in the Holder exponent. These gaps are actually very bright in the Holder exponents, and if you compare it with the regularized dimension, you can see that the white portions here denotes the gap, and surrounding them you can see that there are some kind of materials or dense medium that is surrounding them, like in these region. Okay, so these are the features that are like extracted from here. Again, you can see in the next object also similar, like the SR4, you can see similar things are available here. So in these regions, like in the regularized graph that you see here, you can see that in these regions we can estimate, or we can say that a planet planet can, or a density medium is very high here, so structures can be present in these areas. Similarly, in AS205, the object here, see the image here is not very clear in the original image, but when you check at the Hubble exponent here, see the ring structure that is like very grayish, like very low resolution grayish image here. But in the Hubble exponent, you can see that it's very, very black in color, very dark. And also in this region, you can see the black, the gaps that is here, it's available in this region. It's shown as gray, black and gray, which is also when you see in the regularized dimension, you can see that the boundary of it is like the boundary of the gap. This is the gap, so this is the boundary of that gap, is the intense pixel, and also some structures that is before that. Like in this area, there are some structures. Okay. Similarly, here also you can see that these areas, which are a little bit higher in density compared to the rest, like the black portion here. So these are more emphasized in this area. The estimation is more emphasized, and also you can see in this regularized graph also it shows some structures in this area. So in this area, like high chances of finding a planet of probable mass or dense compact clumps can be found in this area, because as we know that when planet orbits, it clears out the dust in this, when it is orbiting, it is clearing out the dust of the matter along its way. So similarly in here also, in AS27, you can see similar features can be found. Again, here also. Then in this figure, that is HTLUP, it actually shows one of the negative thing here. One is that from the image, you can see that the two structures are actually very different structures. They are actually not attached here. But in the regularized graph, you can see that there are some structures shown here a little bit. So this can be the false positive that they are showing in the regularized graph or projecting from the original image. This may be because the original image is not that of a high resolution. So it's the computer, or when we run a model, it is actually getting confused between the high intense pixel and the little bit lower intense pixel. So again, in these regions, you can see that little bit of blackish color is blackish pixels are present here, and here also in this image, that is B, you can see it's completely here it is showing completely black, but when we see in a high resolution image, we see that there are a little bit of structures formation here. There's a little bit of grayish color in here, so which is actually shown by these areas. So that means that then there are a little bit of density profile or density dense medium in this area. So here in the discussion part, you can, as I've shown before, that the over the region where density is high, it's actually high at whenever there is a gap edge. At the gap edge, then the gap rises. The gaps and the rings, which are the axisymmetric structures, they are actually due to the planet clearing the dust of the material, and also that this which is the non-axial symmetric structures, they are like arcs or vortex where the material clumps is present. So sorry, let me go back. Yeah, like in this area, the material clumps are present in this area. So these are the material clumps. And in the first image, you can see that this actually is an arc. It's a very high intense profile. It can be a vortex also, which we don't know. We have to like literally literature review we have to do for this object to be sure, cross review it. Then come back to the conclusion. Here in the conclusion, we can say that from the analysis we have done, Fourier analysis actually are a very good candidate to capture the features. Not only protoplanetary this, but any kind of features it can capture. It can capture intricate features that are present within the image or a time series data. Then it can also like detect them. It can show several like patterns over the image or time series data. It is very dominant at that. So, so from this analysis, the work that we have done here, we can actually integrate the Fourier analysis that we have done here. We can integrate it to machine learning models and to detect and automate them, and so that we can improve the traditional models in accuracy and reliability to distinguish or acts as a filter, first initial filter of protoplanetary disk images, like whether the objects should be go for further studies or not for planet, for example, like searching of a planet, etc. Thank you.
Thank you for the talk. Do you have any questions? Okay, I think so. We'll proceed to our next speaker. We have Rwanda from Guwahati University, Assam, and she'll be talking about what makes the planetary gap in a protoplanetary disk wide. So, do we have a speaker here?
Rwanda, are you there? You can see you in the list, participant list, but
if that is the case, can we?
Oh, okay, Rwanda, you were there. Okay.
Yes.
Okay. So, can you quickly share your screen? Start the presentation.
Is my screen visible?
I think we cannot see it yet.
Not yet.
Okay. Share.
Now it's there. Yes.
It's visible.
Yeah, it is visible, and you can proceed, please.
A very good afternoon to everyone. My name is Rwanda Mavida, a PhD scholar under the guidance of Professor Ishankul Saikia in the Department of Applied Science, Guwahati University. The title of my presentation is What Makes the Planetary Gap in the Protoplanetary Disk Wide. So here a glimpse of the overview that I'm going to talk in my presentation. In the introduction, I will be introducing what is the protoplanetary disk and the planetary gap, and moving on to the methodology that we have adopted in our study. Then I'll move to the results and the discussion, where I'll be talking about the morphology plot and the azimuthally average density profile, and last but not least, the conclusion. So before going into the obvious question of what are these planetary gaps, first I will introduce what are these protoplanetary disks. So as you can see in figure 1, this is the simulated protoplanetary disk, which is around a 1 solar mass star embedded with a given size planet. So basically these are rotating disks which is found around young newly formed stars. They are made up of 99% of gas and 1% of dust. Recent astronomical observation have established the presence of structures in protoplanetary disks such as gaps. So what are these planetary gaps? Planetary gaps in protoplanetary disks are basically the region where the material is being cleared out by the planets in their orbits, and the many factors are affecting this planetary gap formation, one of which is the gravitational interaction between the star, planets, and materials in the disk. And in scenario where there are 2 planets in the disk, due to the orbital resonance, the excited spiral density wave enhances are enhanced, and which in turn help in rapidly creating the gaps formation. And this is the image of an HL Taurus protoplanetary disk, which was taken by ALMA telescope. So moving forward into the methodology, to simulate the interaction within a protoplanetary disk, we have utilized the 2D hydrodynamical simulation, which is provided by Farco 3D code, which is developed by Pablo and Masset. This code actually solves the Navier-Stokes equation, which helps us in understanding the dynamic of fluid flow in this disk. Equation 1 actually is the continuity equation, which ensures mass conservation, and equation 2 is the momentum equation, which accounts for the force acting on the fluid. The momentum equation includes terms for pressure, viscous stress, and gravitational potential. The gravitational potential is actually the contribution from both the stars and the planet. Here U is the velocity vector, rho is the density, P the pressure, T is viscous tensor, and phi is the gravitational potential. We also assume the isothermal equation of state, where C is the isothermal
sound speed. Now, the disk density varies with radial distance as shown in equation below. Therefore, with the increase in the distance from the central star, the surface density decreases. For a simulation, we have considered a Jovian and Neptunian-sized planet where the disk extends from 0.3 to 4 astronomical unit. And the simulation was run for 5,000 orbit for the inner planet, which is placed at approximately 1 astronomical unit around the solar mass star. We have considered different models for a study with different position of a pair of planets, which is given in the table alongside. Also, the disk parameters such as the aspect ratio, sigma naught, alpha viscosity, sigma slope density, and the flaring index ratio and the eccentricity is given in this table. Moving to the results and discussion. Previous study of a single planet have highlighted that more massive planet generates stronger shock. Therefore, the planetary gap is directly proportional to the planet mass. And also the size of the gap depends on the location of the planet. Therefore, planetary gap is directly proportional to the radial distance of the planet. But in our study, we have plotted the morphology plots of the disk, which is represented in polar form. Here, the x-axis denote the azimuthal angle, and the y-axis denote the radial distance of the planet. And the white cross here is the position of the Jupiter-sized planet, and the dark cross or the black cross here denotes the position of a Neptune planet. In our results, we found that when a more massive planet is placed in the inner part of the disk that is near to the central star, we find that the gap which is cleared by the planet is more narrow as compared to the model 4, where the massive planet is placed in the outer part of the disk and the less massive is placed in the inner region of the disk. And this result is also consistent when we change the planetary separations. The gap is again narrowed when the massive planet is in the inner part of the disk and wide when it is in the outer region of the disk. Also, similar results we observe when we take this pair of planet and place it in farther regions from the central star. We have also plotted the azimuthal average density profile. Here, the model where the Jupiter is in the inner part of the disk and the Neptune is outer part of the disk is given by the blue curve, and the X mark denotes the planet's position. And we see that when the less massive planet, that is in Neptune planet, is in the outer region of the disk, the inner disk is actually highly dense. Similar, we can see in the next model too, that when the less massive planet is in the outer region of the disk, the inner disk is actually highly dense, and this is because the outer planet which is less massive, the final mass through the gap and eventually into the disk, which maintain the high density of the inner disk. And also from the gap here, we can see that when the less massive is placed in the outer region, we see that the gap is narrowed as compared to the model where the Jupiter planet is placed in the outer region. The gap is much wider. Similar results in the alongside models.
Ribanda, you have
and because of the funneling effect, we can see that when the outer planet is placed in the outer region, we see that the gap is actually distorted, and as compared to the M4 model where the gap is more uniform. And also the substructure, we can see substruction and asymptotic substructure is more stretched out in M3 as compared to M4 models. So on concluding my presentation, I would like to mention the key findings of our results. The first is, which is already as well established, that is a heavier planet readily open a gap in protoplanetary disk, and the gap is actually wider. The gap width is actually influenced by the position of the accompanying smaller planet, and wider gap is actually observed when the massive planet is positioned in the outer disk. The probable application here is that in estimating the mass of the planet from the gap width. As we know, the mass estimation of planet is done from the gap width. Our results highlight that there might be an underestimation or overestimation of this mass if the second planet is not observed in the observation. Generally, when a non-asymmetric structure are present in the disk, It implies the presence of the second planet, and hence care should be taken, as we discussed earlier, for planet mass estimation. And here is a future work. We're going to extend the work to 3D simulation and also investigate the impact of other physical and thermal parameters. Thank you.
Thank you, Ravanda, for your wonderful talk. So the floor is open for question from audience. So if you have any question, please ask. Oh, all right. I think there is no question from audience. Ravanda, I just a small question. So these simulations, are these open source simulations, or you have developed your own setup?
No, it's an open source.
The open source.
Yeah, they are open. The codes are open source.
All right. All right.
Okay. Okay, thank you.
Thank you, Ravanda, for your wonderful.
Can I stop sharing? Oh, okay, thank you.
Okay, stop. And next we have Dr. Parvati Sahu from Bhadrak Autonomous College, Odisha, and she'll be talking about wormhole construction and modified gravity theory. So if we have a speaker in the audience.
Yes, sure.
Yeah.
Thank you.
You can share this screen.
Yes, sure. I think it's visible.
It's visible and we can hear you, so you can.
Wait a minute, let me to reach the top. Okay. Good afternoon, everyone, and thank you for giving me this opportunity. I would like to thank mostly Professor Vivek Thapa. Well, so I'm going to talk about wormhole construction in modified gravity theory. So yep. So these are the topic outlines what I'm going to cover here. And first I should discuss about what is wormhole. So when we are hearing this term, basically it's mostly a very fascinating term in this scientific community. So in general, if you want to make it understand, so let's take one piece of paper as you can see in this figure. If you fold that paper, instead of going one end to another end, let's fold and make a shortcut way to reach from one end to another end. That is what it is represented here. So this concept of wormhole is basically based on this what idea. So as you can see, if we go for the Einstein's general relativity, so what is the particular definitions of wormhole? So it's basically a topological passage-like structures connecting two distant parts of the same universe, or you can go for the different universe. So as you can see in the figure, so this one part is one part of the universe, and this is another part. And then if you want to make it connected, and this is the tunnel and bridge, what we can say here, this is known as the wormhole throat, and this open part, two parts, is known as the mouth of the throat. In more details, if you go, this is one universe, that is another universe, and how this movement can be possible through this wormhole. That is basically the idea of the wormhole. And another thing is in this nowadays that black hole are also very popular and famous. But I want to make one point clear here. Wormhole and black holes look similar, but they have some point of things like singularity. As you can see here, in black hole, what will happen? It has event horizon and singularity. But if you talk about the traversable wormhole, it don't have that things. So that the difference between black hole and wormhole are based on the horizon and the singularity, right? So if you go for the types of wormholes and all, there are several types of wormholes, and mostly those who have theoretically invented or theoretical discussed about this. So basically that is known as according to their names. But in physics, if you have, there are wormholes are traversable, non-traversable, one way and two ways. So here, if you come to the one way wormhole, that will be that category. This type of wormhole can be called as black holes. So if we will have one way, and that means if you enter and will not come out, whatever it will come to the near to that mouth, it will pull inside and it will stay there and we cannot come out. That is what your black hole properties. So now if you see here, the two-way wormhole. So in this figure, you can see here this part, which will attract the things, and then it will have the event horizon and the singularity. If we remove this horizon and this singularity, then it will make a wormhole, two-way wormhole, or if traversable possible, then we will say it is traversable wormhole. So now coming to here, we are talking about traversable wormhole, and the most popular type of this wormhole is Morris-Thorne wormhole, and it was given by Morris-Thorne in 1988. And then this is what the spherical symmetric matrix, what we are going to define the wormhole matrix, we can say here. And here we have two metric potentials, which is known as shape function and redshift function. Shape function defines the shape of wormhole, and redshift function gives the gravitational redshift. And R is known as the radial coordinates. And this coordinate will be a non-monotonic, and it decreases from minimum to the throat. And then again it will attain the minimum value at the throat, and again it will increases from 0 to not to infinity. So now coming to the minimum set of conditions. So when we are discussing about the wormhole constructions, or you can say the wormhole solution constructions, then that metric potential, shape function and redshift function should satisfy some minimum set of conditions, and these are the four set of conditions. So what are those conditions? We can see here at throat, the shape function must satisfy this property, and then shape function should satisfy these flaring out conditions to avoid the horizontal problem. And most importantly, to make the wormhole to be traversable, the redshift function should be finite everywhere, and that will make sure that the horizon will be absent. So as you say here, if horizon is not there, then it can be traversable. So what are the fundamental properties of the wormhole solution? So basically, in solutions like Einstein field equation solutions, that must have satisfying the energy conditions. But in case of wormhole, the null energy condition should violate here. So wormhole geometry depends upon the existence of exotic matter. That existence of exotic matter causes the null energy conditions violation. So now coming to what is that exotic matter. So exotic matter, which is not same as the dark matter, it has different things, and it contains negative energy density and large negative pressure and mass. Okay. So now coming to the modified gravity theory, which is the base of the model. Here we have taken the Russell modified gravity. So basically, modified gravity is, if you know few modified gravity, they are not consistent with the conservation laws. So here, if we take the modifications in the trace energy tensors and modify in this form, then this will be obey the conservation law. So in that case, by taking this Russell modified gravity, so we have obtained the field equation will be looks like this, and after implementing the Russell parameters, then the final field equation in Russell framework will be given. It will be looks like this. So using that and then taking the trace energy momentum tensor, so we have the set of field equations, which is given in these equations, and in this field equations we have four equations and more unknowns. So now what we'll do here, by implementing some ad hoc physical conditions, we'll get some type of wormhole. So for example, if you take some that if the throat is filled with phantom fluid or Chaplin gas or Casimir gas, so accordingly there are type of wormhole. So now in order to solve that field equations, we have assumed one first other condition. We have taken the redshift function is constant. That means it will be finite everywhere and will not face any horizontal problem. So for in that simplicity, in that way, after getting these field equations, then we have taken one new form of the shape function.
Dr. Parvati, you have 2 minutes.
Yes, sure. So using this shape functions, we have obtained, and one more thing, that shape function should satisfy all the minimum set of wormhole conditions. In that case, this is the figure of that. And using that shape functions, this is the wormhole what we have constructed, and this is the embedded functions graph of that wormhole. And now here we found one interesting, when you are taking the modified gravity, that the energy conditions is violated, but not completely violated. It is partially violated. As we can see here, only one part is getting violated, not all. So this is the And then we have measured the exotic matter. That is how we are getting very less amount, and which is because of the energy condition violation in partial. So the coming to discussion point, when we are taking the modified gravity approach to construct the wormhole solutions, the main motto is that to avoid the energy condition violation while constructing the wormhole. So here we have taken that case, and then we found the throat which is filled with the phantom fluid and which behaves the dark energy era and phantom fluid. That's or we can say it is one part of the phantom wormhole. So these are the few references, and thank you for listening. And if there are questions, please.
Thank you so much for your talk, and the floor is open for question now. I think we have no question from the audience, so I thank the speaker for the wonderful talk, and we move on to our next speaker. And so in place of Naswita, we have
Actually, hi. So thank you, Dr. Sahu, for a beautiful talk. So actually, in the next one, we will, since I think Janasri Bora, she's not in the list actually. She's not a participant list. She has not joined yet. So let's move on to Badal, next presenter, Badal Bhalla. Badal, are you there?
Yes, if we have Badal, so we can proceed with him.
Yes,
yes,
exactly.
I'm here.
Badal, are you there?
Yeah. Okay. Okay. Let's. Vishal, please carry on.
So Badal, if you are there, please. Yeah. We can see your screen.
Okay, can you see my screen?
Yeah, we can see your screen.
Okay.
So you
yeah,
can. Thank you.
Yeah. Hi everyone. Good afternoon. I'm Badal, and I'm a graduate student at University of Oklahoma. And the next 10 minutes, I'll tell you about gravitational wave signatures of physics understanding model, and I'll briefly go through two different topics, two very similar topics, and one of which is on archive. So do check it out. So we know that gravitational waves have been detected, and these are the ripples in the fabric of space-time that carry a wealth of information. It's been almost a decade since we have detected the first gravitational wave. In this work, I'll be looking at gravitational waves from binary and spirals, and we'll use that to probe dark force or dark mediators, and we assume that the spiraling objects of binaries accumulate dark charge. This introduction of the dark force between the merging objects modifies the gravitational waveform, which we can study through multi-messenger observations. There's a reason that I'll tell you later why we need multi-messenger observation. In addition to this, the gravitational waveform is also modified when it travels through a halo of ultralight dark matter that forms a Bose-Einstein condensate. So for gravitational waves, the BEC behaves as a transparent medium with a non-zero refractive index. This non-zero refractive index has a huge impact on the propagation of gravitational wave that we'll look at. So basically, I'll be talking about two different things. One would be how you can study the dark force acting between two black holes with gravitational waves, and the second is how the gravitational waveform is modified when it travels through a Bose-Einstein condensate dark matter halo. So for the dark force, we consider Yukawa force mediated by a particle of mass mv. We assume that the dark force only acts between the two black holes. There is a very good reason for that assumption, and all the other compact objects like neutron star, white dwarf, brown dwarf, they do not experience it. The dark force has a Yukawa form, which is given by this equation. So here alpha dash is analogous to the fine structure constant. So it's basically the charge, the dark charge of the black hole. Q1 is the amount of dark charge. Sorry, alpha dash is the strength of dark force. Q1 and Q2 are the dark charges on black hole 1 and black hole 2, or is the separation between two black holes. And then you have mv, which is the mass of the mediator. Yes, the reason only black hole is charged under this new dark force is because well, black holes can carry charge. So we consider a midi charged dark matter fermion interacting by exchange of vector mediator. So this is a particle physics model. So you have a dark matter fermion, which is millily charged. Now, millily charged dark matter fermions are viable dark matter candidates, and there's a huge phenomenology people have done on millily charged fermions. One interesting aspect of having a millily charged dark matter fermion is that black hole during its formation or due to accretion can accrete the charge, these fermions, and carry the charge that they have accreted. Now this this can happen in standard model as well, but it is badly violated because you have a very large charge to mass ratio in the standard model. But with this millily charged dark matter fermion, you can play with the parameters, and you can have a small charge to mass ratio. For example, if you have the mass of the millily charged fermion to be the proton mass, and the charge to be 10 to the negative 18, the charge of the electron, then you can have a maximally charged black hole. With maximally charged black hole, I mean that the charge to mass ratio of the black hole is almost 1. And this is the reason we consider the black hole to be charged and all the other compact objects do not be charged. But this is our assumption, and people have done other studies as well. Now, in the presence of dark force, the orbital frequency is modified. If you look at this term, this equation right here, so gm1 plus m2 over r cube is the usual Keplerian velocity. And with the addition of the dark force, you have additional terms. So alpha tilde dash is basically the strength of the dark force normalized to gravity. And one interesting aspect of this is that the Compton wavelength of the mediator, or basically the mass of the mediator, is determined by the characteristic length scale of the binary. So here we see that we have an exponential separation, and this exponential separation goes away when you have mv is approximately equal to r, and mv is roughly 1 over lambda, which is the Compton wavelength. This means that different binary systems can probe different mediator masses. And this mediator masses span a huge parameter space from 10 to the power negative 22 electron volt to somewhere around 10 to the power negative 12 to 10 to the power negative 10. Now, on the left hand side, when the mediator mass is around 10 to the power negative 22 electron volt, you can basically study this through supermassive black hole binaries, which have been detected by nanograph. The characteristic length of supermassive black hole is around few parsecs, I believe. I don't remember. For neutron star binaries, on the other hand, the separation is not too large, and you can have or you can probe mediator masses of order 10 to the power negative 12 electron volt. In this work, we will focus on extreme mass ratio spirals, that is somewhere between supermassive black hole binaries and neutron star binaries. And we'll look at the mediator masses of order 10 to the power negative 16 electron volt. Well, what is an extreme mass ratio spiral? So extreme mass ratio spiral is an spiral of a compact order 10 stellar mass object into a massive black hole, which emits millihertz gravitational waves. So you have, we all know there is a supermassive black hole at the center of almost all large galaxies, even in Milky Way, which is Sag. And these supermassive black holes can capture stellar mass objects, which could be a black hole. And this stellar mass object, if you could see on the figure here, this object, which is M1, will basically orbit M2 for several years before it directly plunges into it. This system emits millihertz gravitational waves, while the usual black hole binaries, they emit order few hertz gravitational waves. We expect LISA to detect few EMRIs per year. LISA is a future gravitational wave detector, which is laser interferometer space antenna. So it's a space mission. And the interesting point about EMRI is that because of the long observation time, the system, like a single EMRI can emit gravitational wave for several years, and that could be detected by LISA throughout its time. And this offers us to precisely measure a few physical quantities like the mass of the central black hole, the mass of the secondary black hole, the charge, the spin, and in this case, we'll see the dark charge of the objects. But as I mentioned in the introduction that we need to conduct a multi-messenger study, the reason is that the total force in the presence of the dark force is given by this equation on top. So you have this additional term of the dark force. Now this looks the same as this equation right here. So basically, rescaling the mass of the binary components can imitate the effects of the dark force. So from the single observation, you cannot calculate both the mass and the dark charge. We don't know, like without the gravitational wave observation, we are not very sure about the masses of the black holes that have merged. And this is precisely the reason we look at EMRIs, because one of the object in extreme mass radiation spiral is the central supermassive black hole. And fortunately, there are other ways to calculate the mass of the supermassive black hole. And I'll basically go through 3 such multi-messenger studies. When I say multi-messenger, it could be a graviton-graviton multi-messenger, or it could be a graviton-photon multi-messenger. For the first one, we can have a multi-messenger study with XMRI-EMRI combination. So this is a example of a graviton-graviton multi-messenger study. XMRI stands for extremely large mass radiation spiral, which is basically the spiral of a excuse me, which is basically the spiral of a white dwarf or brown dwarf into a supermassive black hole. Now,
Badal, you have
this sorry.
You have 2 minutes to.
Okay, I'll just hurry. Yeah, so this is basically inspired of a white dwarf or brown dwarf into a central supermassive black hole, and the uncertainty associated with the mass here is 10 to the negative 3%. You can also have photon graviton multi-messenger study. I have 2 photon graviton multi-messenger studies here, and in both the cases, the uncertainty is of order 10%. Now with that, we can calculate the time evolution of the orbital frequency. This is something that can be observed with the gravitational wave detector. The equation is right here, and G is basically the term that carries information about the dark force. We assume a 10% uncertainty in the mass measurement of the compact object, which comes from the population level studies. And here is the evolution of frequency. So we observe the EMRI for order 10 years. And this gray shaded region is basically the mass rescaling. So with a multi-messenger study, you can explain anything within this gray shaded region with the rescaling of the mass. But outside this gray shaded region, the region is broken. So if you have a frequency evolution that lies outside the gray shaded region, it basically indicates that there is a dark force acting between the 2 objects. So here I've shown 2 different figures for 2 different multi-messenger studies with different uncertainty in the central black hole mass. And you can probe the strength of the dark force of order 0.1 to 0.2 and like that. So we do a likelihood analysis to basically study how sensitive the future gravitational wave detectors are to this dark force, and basically we show on this plot right here what's the future sensitivity with different multi-messenger studies, and here I've shown what multi-messenger studies we have considered and what's the sensitivity here on the plot. Now I'll very quickly go through a different topic which is about the ultra light scalar. So we consider a scalar dark matter field that is described by this Lagrangian right here. So we have a kinetic term, mass term, and we have a self interaction between the dark matter field. In the presence of repulsive self interaction, the dark matter can form Bose-Einstein condensate on a galactic scale, and the reason we introduce the self interaction within the dark matter is to stabilize the BEC core. And in general, this BEC core will consist of a solitonic core, which would be around the center of the galaxy, and then there would be a normal NFW halo surrounding it. The radius of this core depends on the Lagrangian parameters like the mass and the strength of the repulsion, strength of the repulsive self interaction. Now, if if gravitational wave propagates through a BEC dark matter halo, it can excite the massless phonon modes in the ground state of the BEC wave function. Now, the interesting point here is that the BEC offers a lot of phonon modes in the ground state. And this effect is analogous to the light traveling through an optically transparent medium. So when light travels through an optically transparent medium, its velocity changes from that in the vacuum. And you can have different dispersion relation, or you can have refraction, reflection, or all that stuff. And basically, you have a non-zero refractive index now for gravitational waves inside the BEC medium, which is given by this equation right here. Please note that this has a parametric dependence on the strain and the frequency of the gravitational wave, which is to the power 4, which is very useful. The speed of the gravitational wave is thus modified, and it's now given within the dark matter halo to be equal to C/Ng. What this does is that because this refractive index depends on the gravitational wave frequency, so the gravitational wave emitted during the different phases of black hole merger, basically in spiral merger, they have different velocities when they travel through this optically transport through this BEC dark matter halo. And what it does is it modifies gravitational waveform. So for the inspiral phase, it basically has a lot of time delay compared to the merger phase, and you almost have an inverted chirp. So this, the top figure right here, is basically the gravitational wave we have observed, and in the absence of BEC dark matter and the presence of BEC dark matter, it would look something like this down here. And with this, you can basically probe the parameter space of the ultralight dark matter. So on the y-axis, we have the self-interaction, and on the x-axis, we have the mass. And this gray shaded region is not allowed. It's forbidden because so here the relaxation is too slow. So basically, you will not form a BEC in Hubble time. And here the core radius would be too large. This white region here is what is allowed, and we see that the future gravitational wave detectors such as Cosmic Explorer and LISA can give us information about or it can probe this region right here. So I'll conclude my talk by saying that gravitational wave offers a unique opportunity to study physics beyond the standard model. And in this talk, I went through two very similar different cases, basically exploring dark forces and exploring BEC dark matter. So with the dark forces, we saw that EMRIs can be used to probe it, and EMRIs are sensitive to a range of mediator masses, but we need an independent mass measurement to break the degeneracy of the effect of the dark force with a simple rescaling of the binary component mass. Gravitational waves can also serve as the probe of ultralight dark matter that conform Bose-Einstein condensate, since BEC acts as an optically transparent medium, resulting in a modified waveform that can be detected with future gravitational wave detectors. Thank you.
Thanks, Badal, for the exciting talk. So the floor is open for questions. So we are slowly running out of time. So if we have questions, we can.
I have a hi,
Yes.
Badal. So I have a small question actually. In
Yes.
figure number 10, page number 10, I suppose. Like, but yes, so
This
you
one, yeah.
mentioned about this slide, right? Also here,
Yes.
the upper slide is with, I can't see the exact.
Maybe I'll zoom it. Can you see it now?
Yeah. So upper slide is for the there is no BEC name, right? And how?
Yeah, there is no BEC.
And for the lower curve, there is also in the presence of BEC name, right? So can you explain why is this particular how this signature affected? Like, how is this affecting it basically in very short? Very short.
So if you look at this, so we start from the spiral phase and then we go to the merger phase. The frequency is increasing, right?
Yes.
And if you see that the refractive index is actually depending on the frequency of the gravitational wave. So smaller the frequency is, more is the refractive index, which means the slower would be the velocity of the gravity. So basically, this gravitational wave right here will travel much slower than this right here. So
Okay.
this arrives late while this arrives early. And that's
Okay.
why the gravitational wave modifies.
Mhm. Okay. I understand. Okay,
Okay, does
thank
that
you.
answer your question, or should I explain more?
No, fine. Yes, that
Okay.
answers that. Thank you.
Yeah.
Badal, I have a very small question. So in this,
Yes.
you started with the approximation that you are considering the dark matter. So is it for the simplicity, or you have a reasoning behind it? And are your results immune to the changing if you change that particular approximation?
I'm sorry, I didn't hear you. Can you say that again?
Can you hear me now?
Yeah, I can.
So I was asking you that in the starting, you started with the approximation that you are considering dark forces within only two black holes, right?
Yes.
So is it for that approximation for the sake of simplicity, or you have a reasoning behind it?
Yeah, so I said, right, because if you consider many charged dark matter fermion, you can have maximally charged black holes. Now you can also accrete this dark matter fermion, like neutron stars or other compact objects can accrete it, but you will not get a maximally charged one. So the best case scenario is black hole being charged, and plus for extreme mass radiation spirals, where you can have the degeneracy between the rescaling of the mass and the dark force to be broken, you need the black holes to be charged. That's the reason. And as I said, the people have done the other studies as well. So people have already done when a neutron star gets dark charge. People have also done when supermassive black hole bodies have the dark charge.
All right. Okay.
Yeah.
So thank you, Badal. So do we have any other question? All right. So thank you, Badal, for the exciting talk, and thank you for
Thank you.
us.
Thank you, organizers.
Okay, so we move to our next speaker. We have Dr. Anshuman from Tezpur University. So do we have the speaker in the list?
Hello. Can you hear me? Okay, thank you. So I'll share my screen.
So a quick announcement. Okay. There's an echo. So after this talk, after Dr. Borgohai's talk, Janestri for us, she has joined recently. Okay, so hers will be the last one. Will it be fine, Janestri Bora?
Yes.
Okay, fine. So yours will be the last one. You should be the one after Anshuman Borgohai. Okay,
no problem.
Okay, Vishal, please carry on.
Okay, so Dr. Anshuman, yeah, you can see us that, and you can please.
Hi. Thank you. So yeah, I'm Anshuman Baruah. So I recently completed my PhD from Tezpur University, and firstly I thank the organizers for giving me this opportunity to talk on our work. So I'll be talking about star formation in the nearby dwarf galaxy groups. Just remove this. Okay. So this is a very recent work that I've been involved in, and this is an ongoing work. So without any delay, before going into the topic, so let us try to understand why dwarf galaxies are important. So dwarf galaxies, they are important because they challenge the existing cosmological predictions of our universe. So there are inconsistencies such as the missing satellite problem, which is very well known. There is a cusp core problem, the 2-week tail problem, and a few others. So dwarf galaxies, they are typically of the masses, stellar masses of 10⁹ solar mass or less. Then their sizes are a few parsecs to a few kiloparsecs in diameter. For comparison, our Milky Way is around 30 kiloparsecs in diameter, and the stellar mass is around 10⁻11 solar mass. So other special characteristics about dwarf galaxies is that they are very common objects in our universe. So this is a plot of stellar mass functions at different redshifts, and from here it is evident that dwarf galaxies are quite abundant in our universe. Then secondly, these are considered to be the basic building blocks of massive galaxies that we see around us today, and most importantly, they are considered to be the primary sources of ionizing radiation in the very early universe. Now, what are the challenges that we observe in the case of dwarf galaxies? Firstly, they are technologically challenging to observe in the higher redshift because they are intrinsically very faint, and they are also very compact. So that is the very basic challenge that that is observed. Then there is the dark matter distribution, which is not very well understood in the case of dwarf galaxies. Then there is a lack of consensus in explaining the connection between the diversity of dwarf galaxy morphologies. Then there is a downsizing effect in the that is observed in the case of dwarf galaxies, which says that the low mass galaxies they are beginning to, I mean, most of the star formation it's happening in the case of dwarf galaxies in the present day universe, but this is at odds with the lambda CDM scenario, where the smaller galaxies they are considered to have formed first, and then they combine to form the massive galaxies. Then there are theoretical predictions which suggest that this hierarchical scenario, where low mass galaxies they combine to form the bigger ones, this scenario is scale free. But to prove this, there is a lack of observational evidence. So I mean, in order to decipher the picture of galaxy formation and evolution, a very accurate mass assembly history of the dwarf galaxies is quite important at all cosmic times. Now, coming to the sample that we have used in our work, these are dwarf galaxy groups. So we have picked a sample of dwarf galaxy groups which are in the nearby universe of around redshift 0.03, which is quite local. Then this sample, this belongs to a sample of isolated dwarf galaxy groups which have been discovered in the recent past in around 2017. So these are the I mean these provide the very first evidences of dwarf galaxy groups in our which contain only dwarf galaxies in a group in our nearby universe. So the important thing that which comes up is that this will provide a very unique window to study the hierarchical growth scenario in the case of dwarf galaxies. Then another thing that we can get from this is that these dwarf galaxies, since they are, I mean, according to the lambda CDM model, since dwarf galaxies are combined to form the massive galaxies, so this system they can be considered, I mean, they might be very young systems where these dwarf galaxies they will combine to form the very, I mean, massive isolated galaxies in the field. And to study these galaxies, we make use of the UVIT on board AstroSat. So this is a ultraviolet imaging telescope, and we propose observations for 2 of the dwarf galaxies from the Tiny Titan survey. And we use FUV observations because FUV emission from the stellar photosphere, it traces the star formation over the past 100 million years or so. And this is emitted by the massive O and B OB type of spectral type of stars. Then yeah, so once we have obtained the observations for FUV observations for these galaxies, we reduce the L1 data, level 1 data using the tool CCD Lab, and then our final science 3D images they had exposure times of around 5 kiloseconds. Then we perform the astrometric solutions using IRAP, and then I'm showing an example of a PSF modeling for one of the galaxy groups, which gives a PSF FWHM of around 1.2 to 1.7 arcsecond FWHM. In addition to the FUV observations, UVIT observations, we have used SDSS optical data. Then we have used the Galax NUV data as well, and then we have used Spitzer infrared observations in the 3.6 and 4.5 micron. So I'm showing over here the 2 dwarf galaxy groups. At the first column, it shows the pointing that we have observed. In the middle column, there is a comparison between the UVIT and the Galax observations. So the difference in the resolution is quite evident here. So in the case of UVIT, it's around 1.2 or 1.5-ish arc second ESF, and in the case of galaxy, it's around 5 arc second of WHM. So I mean, that's one of the biggest advantages that we have in the case of UVIT observations. Then on the right handmost plot, this is a false color image of FUV and the R and the Z band, G and R band imaging from the SDSS. So these are this is one of the groups which has 5 dwarf galaxies, and this dwarf galaxy group it has 4 dwarf galaxies. So coming to the data analysis, so we have obtained the fluxes of these galaxies. Okay, thank you. So we have done the broadband SED modeling of these galaxies by constructing the SEDs using the multi-band observations that we have in our hand. Then we proceed to obtain the color maps. So color maps indicates it's basically a difference of FUV. It's basically a difference between the broadband magnitudes of 2 filters. So we have used the FUV and R band observations to obtain the FUV minus R color index. So we have used this color. So FUV minus R represents a color. So we have used this because it can trace young stellar populations within 1.5 gigayear or so. So yeah, so this is the second thing that we have done. Then thirdly, we have tried to identify clumps in these galaxies. So the clumps in galaxies, they are quite important because they are indicators of coal gas accretion from their surrounding medium, and which is proven in the case of very high redshift galaxies. So such a scenario has been observed in the case of nearby star-forming dwarf galaxies as well. Now to identify these clumps, we have employed a method where we blur the combined G, R, and Z image of the galaxy using a kernel which will be equivalent to an average PSF in the G, R, and Z, and then we subtract this blurred image from the original image. So we are left with, in the bottom you can see that we are left with the clumps which which are quite evident from the imaging. So these are the different clumps that we have identified. So this is these are only the clumps in the image that we have identified. We are yet to confirm whether these belong to the host, whether this is a foreground or whether this is a background object. So coming to our results and discussion, from the SED modeling, we have obtained stellar masses. These are the very preliminary results that I am showing over here. So we have obtained the star formation rates, the stellar masses, and the DN4000 index. So while comparing the star formation rate and the stellar mass with the pairs and triplets of galaxies that has been studied in the previous studies, we see that these galaxies, they are similar to the main sequence star forming galaxies. So in the plots, these are marked by red diamonds. So first one is a star formation rate versus stellar mass plot, and the second one is a specific star formation rate versus stellar mass plot. And yeah, so the DN4000 index, so this is around 1-ish. So this is basically an indicator of the age of the stellar population, basically the mean stellar population in the galaxies. So one value around 1, it represents a young stellar population. And yeah, so the color maps that we have obtained, the FUV minus R color maps. So we have converted the image into the FUV image into FUV magnitude image, and the R band image into R band magnitude image, and then we just did a mathematical subtraction of the images, and then we are left with the FUV minus R maps. So a blue color, I have provided a scale over here. So blue color indicates a smaller value, and which is basically indicates a young stellar population. And from the preliminary results, what you can see is that, so this is in the first group, BG01. So this is the most massive group here, massive member of the group. So there are this blue color, it is an indicator of young stellar population in the outskirts. And similarly in the second group, as if you can see my cursor, So this galaxy is the most massive galaxy in the group. And yeah, so young stellar population is observed in the outskirts of these galaxies, and this is an indicator that these are actively growing their stellar disk by a very recent ongoing star formation. But this is a very preliminary result, and we still need further analysis using other color indices as well. And yeah, thirdly, coming to the clumps. So
I think the time is over, so please try to wrap up.
Yeah, so this is, yeah, so I'll just take one more minute. And these are the clumps that we have observed in these galaxies. So we see that these galaxies, they are quite rich in clumps. And yeah, so we need to do further analysis to model the star forming clumps in these galaxies, and which this will be a future. This will be done in the future part of the work. And coming to the summary and conclusion, so what we've done is that we have obtained a few observations for a sample of nearby dwarf galaxy groups, and we have modeled the broadband SEDs of these galaxies. And from the SED modeling, we find that these galaxies have a very young main stellar population, and based on the FUV minus R color maps, these indicates that at least the most massive galaxy, it is actively growing its stellar disk. And yeah, apparently the galaxies, they are quite rich in clumps, and this will be further studied. And yeah, so for in the future, we will do further multiband morphological decomposition to study their structural evolution, and also use different color indices to study the stellar population in these galaxies, and of course, yes, modeling the clumps to derive their physical properties. So that's all from my side. Thank you for listening.
Thank you, Anshuman, for the wonderful talk. Yeah. So the floor is open for question if you have any question from the audience. Okay, so I think we do not have a question from audience. So thank you so much, Dr. Anshuman, for your time and being with us today. And
thank you.
For the last talk of this session, and most probably for today, we have Dr. Jatna Sharif, and she'll be. Do we have this speaker in the list?
Yes, I'm here.
So kindly.
So my skin is visible?
Yes, your skin is visible. Okay. You may please proceed, Dr. Wood. Thank you so much.
Okay, yeah, thank you. So good afternoon, everyone. First of all, I would like to thank the organizers for giving me a chance to discuss my research work with you all. And in this presentation, I am basically going to discuss a particular type of compact star, that is quark star, in the context of flash-tail gravity, which is a non-conserved energy momentum gravity. And this work is based on our recent publication in Classical and Quantum Gravity, which was done in collaboration with Dr. D.J. Gogoi, Professor S.K. Mora, and Dr. G. Mustafa. So many presenters of today's presentation has already discussed about compact stars. So I'm not going to discuss the basic things about compact stars, but let me tell about why we need to study the compact stars. Basically, the compact stars are compact stars give us the platform to study, test, or constrain new physics or alternative theories of gravity under extreme conditions that cannot be generally realized from any Earth-based observatories or laboratories. So such type of compact stars give us an wonderful platform to do so. So in this study, we are basically studying compact stars in the context of Russell gravity. So before moving to the Russell gravity, first let me introduce some basic things about general relativity. And in general relativity, we use the metric as given by equation 1. And when we consider the star to be made up of some perfect fluid, then we can define the energy momentum tensor as given by this equation. Now, in general relativity, the conservation of energy momentum states that it is equal to 0, and it is shown in the yellow box. And we have the Einstein field equation as given by equation 2. And this equation basically connects the geometry and matter part of the universe. Now, using this field equation, one can derive the basic stellar hydrostatic equilibrium equations for GR, and these stellar hydrostatic equilibrium equations are popularly known as TOV equations, and these two equations are the TOV equation that is shown in these two blue boxes. Here P is the pressure and M is the mass, and these two equations basically determines the how pressure gradient with respect to radial distance r and mass gradient. So in the case of Russell gravity, the basic difference between Russell gravity and general gravity is that the conservation law that holds in the case of general gravity does not hold in this theory. So we have the new conservation law as given by this blue color box equation. Here, when this term alpha tends to 0, we can restore our general relativistic conservation law. So in Russell proposal, we can find the field equation as given by this equation. Here the term K and alpha are the Russell gravitational coupling constant and Russell parameter. And with this field equation, one can derive again the modified version of the TOV equations. And these equations are shown in these two yellow highlighted box. And here the y tilde and x tilde are the effective quantities that are related to pressure and momentum by these two relations. Now, in this relation for effective quantities with respect to the momentum and pressure, we have defined some new parameters, that is alpha 1, alpha 2, and alpha 3. And this alpha 1, alpha 2, and alpha 3 are can be given as like this equations. And here the term eta is the Russell parameter, and in our study we will vary this Russell parameter to see the effect of Russell gravity on the structure of compact stars. Now, to solve such type of TOV equations, that is basically these two yellow boxed equations, we need to define some boundary conditions, and also we need some equation of states. So in this particular study, we are considering two equation of states. The first one is the Stiffer MIT back model equation of state, and the other one is the CFL phase equation of state. So with this equation of states and proper boundary conditions, we can solve the TOV equations to know more about the stellar structures. Now, an interesting property related to the study of compact stars is that some of them can echo the gravitational waves falling on their surface. And however, there are some basic criteria to emit gravitational wave echoes. And the first criteria is that the compact stars should feature a photon sphere around their stellar surface. And the compactness of stars, such compact stars should lie between some limit, and these limits are known as the photon sphere limit and Bose-Dal limits. Here 1/3 represents the photon sphere limit and 4/9 represents the Bose-Dal limit. So when we have such type of compact stars fulfilling these two criteria, they are good emitters of gravitational wave echoes. So this figure graphically represents how echo happens. And when we allow gravitational waves from distant matter object to fall on the surface of a star, then they eventually get trapped between the photon sphere, and multiple refraction and refraction occurs. And from these refracted waves, we can determine the echoes of gravitational waves. So to do so, we can use these two equations for characteristic echo time scale, and using the value of the characteristic echo time scale, we can determine the gravitational wave echo frequencies. So coming to our numerical results part, first we have solved the TOV equations as I have mentioned already. And the first fifth panel is for the MIT back model equation of state, and the next panel is for the CFL phase equation of state. And in these two figures, we have considered the different values of Russell parameter, and in the Russell parameter value eta is depicting the stars in general relativistic case. So we have noticed that for both this equation of states, all the stellar configurations are compact enough to echo the gravitational wave falling on their surface, as they are crossing the photon sphere limit in these two equation of states. Also, we have constrained this mass radius curve using some recent observational data, which are shown in this color blocked figures. So these are the predicted radius for different values of Russell parameter eta for different star candidates. And this table is for the MIT back model equation of state, and this one is for the CFL equation of state. So the variation of mass with respect to the Russell parameter eta is shown in these two figures, and we have noticed that the maximum mass varies for both equation of state, gradually decreasing in nature. This mass variation is, and similarly, the whereas for the case of radius variation, it is gradually increasing for both the equation of state. And these are the variation of compactness for different values of Russell parameter eta for with respect to the pairing gap of the CFL phase equation of states. And we have noticed that for smaller value of Russell parameter, that is negative value of Russell parameter, we have obtained star with maximum compactness, and star with minimum compactness are obtained with Russell parameter, positive value of Russell parameter. And also we have computed echo frequencies, and the echo frequency variations are shown in these two diagrams. And we have noticed that with increasing value of Russell parameter for both equation of state, we have obtained gradually increasing gravitational wave echo frequencies, and these echo frequencies are in the range of kilohertz. So these are the results that we have obtained from this our study. And as I have mentioned already, for negative value of Russell parameter, we have obtained star with less radius, and for the case of positive Russell parameter, we have obtained star with more radius, and similarly for the case of CFL phase equation of state. So we can summarize our work as like general relativity, Russell theory also permits stable stellar structures, and they can also produce echoes of gravitational waves. And negative values of Russell parameter results in more compact stellar configuration and a lower gravitational wave echo frequency. And when we increase Russell parameter, both compactness and stellar configurations and echo time decreases gradually. And echo frequencies for these two equation of states are in the range of 9 to 27 kilohertz for both cases. And one important thing that we have noticed that the equivalence of Russell theory to Einstein theory is refuted, as we have noticed many deviations, many significant deviations in the physical properties of the considered compact stars. So these are some of the references, and thank you for your kind attention.
Thank you so much for your presentation.
Yeah.
And so
Can I stop sharing now?
And if we have any question from the audience. So I think we have not. So I just have a small question. So for the calculation of the quark and quark star, so have you also considered for the hadronic matter or only the quark matter inside this star?
Only quark matter. I have considered only quark matter.
And that is in the one in the CFL and the phase, and one is using the MIT model.
Yes, one in MIT.
All right.
So I have one follow-up question regarding the question Vishal asked. So what do you think will be the case if you consider hadronic matter? Will there be any significant changes in the physics, or it's insignificant?
I think it will give some significant results, but I have not checked yet. But I think it may give some significant results.
Okay.
Yeah.
Okay, thank you then.
Yeah, thank you.
Okay, so thank you all the speakers and all the participants who have been there and who have been patient enough, because we are sort of almost 30 to 40 minutes late.
Yeah, we are a bit late actually. We are going late. Yeah. So let me thank yes.
Thank you so much, Dr. Vivek, for inviting me today, and I request you that next year when you organize this conference again, do it in offline mode so that we can visit.
I don't know about you. You will be in Italy by then. But I don't know. But we'll definitely invite
If you will invite me,
definitely.
If you will invite me, I have a reason to visit.
Yeah. Okay. Thank you, sir. So okay. So tomorrow we have a line of speakers. for tomorrow's presentations and plenary sessions. So we will have like Debojyoti Datta from High Energy Physics, then followed by Jibanjyoti Das, Professor Jibanjyoti Das from Nuclear and Radiation Physics, and followed by Dr. Saina Adhikari from IET Norway, and Dr. Kamal Saharia from Bhattadev University, who will be speaking on plasma physics. So thank you all for sticking till the end, and we hope to see you tomorrow. Okay, thank you all the participants, all the speakers, for the interactive session, interactive presentations, and nice Q&A sessions. Okay.
Thank you so much. Thank you. And
Thank you. Okay.